Earth is an extraordinary planet that has existed for more than 4.5 billion years. Throughout this vast period of time, it has experienced numerous catastrophes, changes and transformations that have shaped its surface, atmosphere and ecosystems. Initially, our planet was a molten mass with no life on it. Gradually, as it cooled, Earth formed its crust, and the first simple organisms began to appear in the oceans. Over billions of years, life evolved, passing through many stages, from simple single-celled organisms to multicellular creatures that filled the oceans and eventually moved onto land. This incredible diversity of life forms has colonized every part of the planet, from the deepest ocean trenches to the peaks of mountains, and even the most extreme conditions, such as hot springs or ice deserts. However, humanity, or Homo sapiens, appeared only at the very end of this long journey. We emerged on Earth's stage only a few 100,000 years ago, which is a mere blink of an eye compared to the age of our planet. This short period was filled with significant events, from the formation of the first human communities to the creation of tools that became crucial for survival and development. People learned to hunt, gather, and then practice agriculture, which allowed them to establish permanent settlements and develop cultures. Major achievements, such as the invention of writing, enabled the transmission of knowledge from generation to generation, significantly accelerating the development of civilizations. Meanwhile, on the planet, global climate changes were occurring, affecting ecosystems and the existence of living organisms. For example, ice ages altered the familiar appearance of Earth, creating new landscapes and changing the migration routes of animals. Humanity, which found itself on Earth at this time, adapted to these changes, developing new survival strategies and ways of inhabiting the planet. It is important to note that many ancient cultures left traces of their existence, which are still studied by archaeologists and historians. The Pyramid of Giza in Egypt, built more than 4,000 years ago, is a vivid example of the engineering genius of ancient people who used the technologies of their time to create magnificent structures. In Mesopotamia, the Sumerians developed a writing system, which became the basis for further development of writing in other cultures. With the emergence of the ancient Greek civilization, philosophers began to ask questions about the world and the place of humans in it, which became the foundation for scientific and cultural progress. Each of these stages was important for the formation of human civilization and our understanding of the surrounding world. However, despite all achievements, humanity remains a tiny element in the vast history of Earth, which continues to this day. Every day, numerous events occur that affect our planet: climate changes, species extinction, geological processes. Humanity, although it has achieved much, is still in the process of understanding its place in this complex and ancient ecosystem. Scientific research continues to uncover new facts about Earth's past, from the study of ancient fossils to the analysis of ice cores that contain information about climate changes. These discoveries allow us to better understand how our planet was formed and how we can interact with it in the future. Discoveries by scientists such as Charles Darwin, who developed the theory of natural selection, or Alfred Wegener, who proposed the theory of continental drift, were turning points in our understanding of biology and geology. It is important to remember that each new discovery adds details to our picture of the world, showing how complex and multi-layered the history of Earth is. Throughout all these billions of years, Earth continues to change, demonstrating its strength and resilience in the face of changes, and humanity, standing on its surface, must recognize its responsibility for the future of this planet. It is important to consider that despite our brief existence, we have the ability to significantly influence the surrounding world, and this requires wisdom and understanding from us. Earth appeared around 4.5 billion years ago as a result of the accretion of matter in the solar system. In the first millions of years, its surface was a molten mass of lava and magma with hellish temperatures. Cooling occurred slowly, and within tens of millions of years, the first continents began to form on the surface. Around 300 million years after Earth's formation, oceans started to appear on the planet. These oceans were the result of the condensation of water vapor emitted from volcanoes and were part of the primary atmosphere. Gradually, the atmosphere became saturated with water vapor, carbon dioxide, and other gases such as ammonia and methane, creating suitable conditions for further life development. Around 3 billion years ago, the first simple organisms such as cyanobacteria appeared, which began to produce oxygen through photosynthesis. This oxygen, in turn, altered the atmosphere, leading to the formation of the ozone layer that protects life from ultraviolet radiation. About 1 billion years after the appearance of oxygen, this layer became the basis for the development of more complex life forms. Around 600 million years ago, Earth experienced what is known as the Cambrian explosion, when the number of animal species rapidly increased. This period was a catalyst for the emergence of multicellular organisms, including the ancestors of modern vertebrates. Earth was not just changing, it was evolving, and each new stage of its development required colossal time intervals measured in millions of years. Around 200 million years ago, dinosaurs began to dominate the planet, and their reign lasted nearly 150 million years before they went extinct around 65 million years ago. This extinction event paved the way for mammals, which eventually led to the emergence of humans. The human species, Homo sapiens, appeared only around 200,000 years ago, which is but a tiny spark on the 4.5 billion year timeline of Earth's history. This period saw such geological and biological changes that it is possible to speak of numerous opportunities for the emergence of reason and intelligence. All this history, from the molten mass to sentient beings, requires a colossal time span that is difficult to grasp. 4.5 billion years, it is not just a number, it is an entire epoch of changes that led to what we have today. The concept of deep time allows us to grasp the scale of Earth's history, which, according to scientists' estimates, spans approximately 14 billion years. If we imagine this duration in terms of 24 hours, each hour would correspond to roughly 600 million years. Thus, the first hour of our daily time begins with the formation of Earth, which occurred around 14 billion years ago. At that time, the planet was molten, and its surface lacked oceans, life, and instead was marked by volcanic eruptions and meteor showers. Around 3 a.m, 4 billion years after Earth's formation, the Archean era begins, when the first simple organisms, such as bacteria, emerge in the oceans. These organisms initiate the process of photosynthesis, which ultimately leads to the accumulation of oxygen in the atmosphere. Around 11 o'clock, halfway to noon, the Cambrian period commences, marked by the rapid development of multicellular organisms and the appearance of the first animals, such as trilobites. By noon, at the boundary of the Carboniferous and Permian periods, Earth is already home to diverse forms of life, including reptiles and the ancestors of mammals. At 3 p.m, during the Jurassic period, dinosaurs become the dominant creatures on the planet, and tropical forests cover much of its surface. Around 6 p.m, at the end of the Cretaceous period, dinosaurs go extinct and mammals begin to take their place. Humanity, as a species, appears only moments before midnight. The first Homo sapiens emerged around 200,000 years ago, which corresponds to less than 1/10 of a second on our daily scale. From a geological perspective, human civilization is but a tiny spark in the endless ocean of time that preceded us. Historical events, such as the construction of great civilizations, the development of writing, and scientific discoveries, occurred in mere milliseconds on this scale. For example, ancient Egypt began to form around 5,000 years ago, which corresponds to less than 1 second on our scale. The 18th century, when the Industrial Revolution began, occurred only 1/10 of a second before midnight. This metaphor vividly illustrates how insignificant human history is in the context of the billions of years that have passed since Earth's formation. It is fascinating that in this brief interval we have not only influenced our planet, but may have made it more vulnerable than ever before. With climate change, species extinction, and ecosystem alteration, humanity has become a powerful force capable of altering its environment. This concept helps us understand that all our achievements and conflicts are but fleeting moments in the vastness of time. Each day we live is but a moment in the long history of our planet, and it makes us ponder what legacy we will leave behind. Having appeared only moments before midnight, humanity continues to face challenges that could shape our future and the future of other species that inhabit this planet. The Fermi paradox is a philosophical question that raises intriguing and unsettling aspects regarding the existence of life on other planets. This question arises when we consider the vastness of the universe, which contains more than 100 billion galaxies, each with billions of stars and presumably trillions of planets. For instance, in our own galaxy, the Milky Way, astronomers estimate that there could be up to 100 billion planets. Given such numbers, it is reasonable to expect that in some corners of the cosmos there must be intelligent beings, and even that they might have established contact with us. However, despite all the efforts made by humanity to search for extraterrestrial life, from radio signals to interstellar missions, we have not yet found any compelling evidence of the existence of other intelligent beings. Fermi asked, "Where is everybody?" There are many hypotheses attempting to explain this anomaly. One of the most popular theories is the Great Silence. Perhaps civilizations do not reach the stage where they can communicate, or they disappear before they can establish contact. This could happen due to self-destruction, such as nuclear wars or ecological catastrophes, as evidenced by historical examples like the collapse of the Maya civilization, which experienced a crisis due to climate change and resource depletion. Another possibility is that civilizations exist but choose to avoid contact with us, akin to the zoo hypothesis. Intelligent beings might observe us, as we observe animals in a zoo, but do not interfere in our lives. Additionally, life on other planets might be entirely different from what we imagine, and thus might not leave traces that we can detect. For example, life on exoplanets could be based on entirely different chemical elements, challenging our understanding of what life is. Furthermore, the distances between stars are immense. Even if an intelligent civilization exists in a neighboring star system, the distance to it could be tens of light years. For instance, Proxima Centauri, the closest star to us, is 4 light years away, and even with modern technology, it would take decades to reach there. Can we expect that other civilizations, if they exist, could overcome these distances using technologies that we cannot even imagine? Let us remember that the first radio signals sent by humanity into space appeared only in the early 20th century, and their range is only a few light years. This means that even if other civilizations exist, they might not know about us. Moreover, many astronomers suggest that life may be much more common than we think, but its development passes through stages that could take billions of years. For example, life on Earth appeared around 3.5 billion years ago, but intelligent beings like us only appeared recently, around 200,000 years ago. This raises the question of how often civilizations reach the technological level necessary for interstellar communication and how quickly they disappear. This timescale could mean that we simply did not coincide with other civilizations in time, and they could have existed long before us, or will appear after us. Numerous factors, from climatic conditions to geological changes, can influence the development of life on other planets, making the task of searching for extraterrestrial life even more complex. Taking all these aspects into account, the Fermi paradox remains one of the most intriguing mysteries of astronomy and philosophy, challenging our understanding of humanity's place in the universe. An important part of this paradox is that when discussing these questions, we must consider not only our perception of life, but also how we ourselves might be perceived by other civilizations if they exist. An interesting fact: in the 21st century, astronomers discovered more than 3,000 exoplanets, indicating that there are plenty of potential places for life in our galaxy. The Silurian hypothesis, proposed by scientists Gavin Schmidt and Adam Frank, presents an intriguing concept that considers the possibility of a technological civilization on Earth long before the appearance of humans. This idea emerged from the analysis of climatic changes and evolutionary processes that occurred on our planet over millions of years. Schmidt and Frank, working in the fields of climatology and astronomy in their book Cosmos for All, published in 2014, suggest that life on Earth could have developed not only within the familiar biosphere, but also with the creation of complex societies possessing technology. They base their argument on facts such as the existence of various life forms in the past, including dinosaurs that dominated the planet around 160 million years ago, and their possible social structures. The study examines hypothetical conditions under which such civilizations could have developed, including climatic changes that could have influenced their survival. For example, at the end of the Cretaceous period, a mass extinction occurred which led to the disappearance of dinosaurs and paved the way for mammals, which in turn could have created conditions for the emergence of intelligent beings. Schmidt and Frank emphasize that if such a civilization had existed, its traces could have been lost or not recognized. They draw attention to geological and climatic changes, such as temperature fluctuations and the level of carbon in the atmosphere, which could have influenced the development of intelligence and technologies. For instance, over the last 500 million years, the climate of Earth has undergone numerous changes that could have created conditions for the emergence of intelligent life. The study also touches on the question of what such a civilization might have looked like. Schmidt and Frank propose that it could have used technologies based on resources and conditions different from those we know today. In the context of the search for extraterrestrial civilizations, this raises the question of how we define life and intelligence. If technological civilizations existed on Earth, it is not unlikely that similar processes could have occurred on other planets. The search for signs of such life may be hindered by the lack of physical evidence of their existence. Schmidt and Frank suggest using a multidisciplinary approach, combining geological, biological, and astronomical research to gain a more comprehensive understanding of the possibility of other civilizations. They also note that many astronomical objects, such as exoplanets, may have conditions similar to those that existed on early Earth. In this context, it is important to consider that life can develop in various forms and with the use of various resources. Our own civilization is a product of unique conditions, and it is not excluded that other forms of life could have developed differently. The Silurian hypothesis opens up new horizons for research and challenges traditional notions of evolution and the development of intelligence. For example, one could consider the possibility that intelligent beings existed on Earth who used technologies different from those we know, possibly based on organic or inorganic materials that we cannot currently recognize. Understanding possible alternative paths of evolution helps us expand the horizons of scientific thought and look at the history of Earth from a new perspective. An important aspect of this hypothesis is that it challenges our unequivocal interpretation of facts related to the development of life and intelligence. As a result, the Silurian hypothesis can be considered a challenge to traditional views on the history of life on our planet and the place of humanity in this history. Scientific research based on this hypothesis opens up new directions in understanding the evolution and development of intelligent civilizations. To test these ideas, further research is needed, focusing on geological data that can provide insights into ancient climatic conditions and their influence on the development of life. The study of fossil remains, as well as the analysis of changes in the atmosphere and climate over millions of years, can help clarify the question of whether other technological civilizations could have existed. The Silurian hypothesis becomes an important element of scientific discourse, highlighting the need to rethink our understanding of the history of Earth and life on it. Geological processes are complex and varied phenomena that occur on the surface and inside the Earth and can have a destructive impact on the remains of ancient civilizations. These processes are formed as a result of the interaction of various natural forces such as tectonic plate movements, erosion, volcanic activity, and climate change. Over millions of years, they can alter the landscape, destroy or conceal architectural monuments, swallow entire cities, and even erase historical artifacts from the face of the Earth. For example, million-year-old tectonic movements can cause the elevation of land areas, changing the levels of seas and lakes, and thus the accessibility for archaeological research. As a result, many ancient settlements that once stood on the banks of rivers may now be abandoned and flooded. Erosion caused by wind and water gradually destroys even the strongest structures, leaving behind only vague traces that are difficult to identify. Even the most durable materials, such as stone, can eventually be destroyed over time by chemical processes, such as karst phenomena, which erode limestone formations, absorbing traces of human activity. Volcanic activity can also suddenly destroy entire regions, preserving them in layers of lava and ash, making them inaccessible to archaeologists. Such catastrophes, such as volcanic eruptions or earthquakes, can change the landscape in minutes, burying entire civilizations. If we recall the eruption of Mount Vesuvius in 79 AD, we see how powerful layers of ash buried Pompeii, preserving it for centuries, while many other cities subjected to similar catastrophes disappeared forever. A significant aspect is also the influence of climate change, which can lead to droughts or floods, affecting the stability of ancient settlements. For example, changes in sea level can have a serious impact on coastal civilizations, forcing them to leave their homes. Ultimately, geological processes act slowly but inexorably, erasing from the map of the world the traces of ancient civilizations, leaving behind only rare artifacts and mysteries that can sometimes be solved only with the help of modern technologies such as ground-penetrating radars and satellite images. Research shows that significant changes occur on Earth over just a few thousand years, which can completely transform the landscape where once great nations flourished. Furthermore, many archaeological finds have been lost forever due to these processes, and science has not yet been able to restore the complete picture of human historical heritage. There is a belief that a large part of the information about ancient civilizations may be lost forever if no measures are taken to protect and study the remaining monuments and artifacts. As a result, the complexity of geological processes illustrates how quickly and irreversibly they can erase the traces of human activity, leaving only questions without answers. From the perspective of archaeology, this emphasizes the need for active study and documentation of all known monuments before they disappear under the onslaught of time and natural disasters. Erosion is a geological process that over millions of years can destroy even the most magnificent structures, turning them into sand and dust. This mechanism includes several types, such as water, wind, and glacial erosion. For instance, water erosion occurs when raindrops or streams of water come into contact with the Earth's surface and rocks. Statistics show that in 1 year, 1 square meter of soil can lose up to 100 tons of material due to water action. It is important to note that rivers not only transport sediment, but also actively erode banks, creating gullies and canyons. For example, the Grand Canyon in the United States, with a depth of over 1.5 kilometers, was formed over millennia by the Colorado River. Wind erosion, on the other hand, is particularly intense in arid and semi-arid regions. Wind can lift particles of sand and carry them over long distances. For example, in the Sahara Desert, wind can transport sand grains over hundreds of kilometers, ultimately altering the landscape. Glacial erosion occurs when moving glaciers remove and transport rock formations, leaving behind characteristic relief features. This can be observed in the Alps, where glaciers have left deep glacial valleys and specific mountain shapes. Additionally, chemical erosion occurs when minerals in rocks react with acids in rainwater or the atmosphere. As a result of this reaction, rock formations such as limestone can dissolve, creating caves and karst landscapes. An example is the famous La Maggiore cave in Italy, where limestone deposits have dissolved, creating impressive underground halls. Metals, when exposed to moisture and oxygen, oxidize, turning into oxides. For example, iron, under the influence of water and oxygen, oxidizes, forming rust, which can destroy metallic structures. This can be seen on old bridges and buildings, where corrosion leads to loss of strength and integrity. The process of erosion also depends on climatic conditions. In regions with high rainfall, it occurs much faster than in arid areas. Scientific research shows that climate change can accelerate erosion by increasing the frequency and intensity of rainfall and winds. For example, in some parts of the United States over the past 30 years, there has been an increase in natural disasters, leading to faster destruction of infrastructure. As a result of this process, even the most durable and magnificent structures, such as the Egyptian pyramids, can undergo significant changes over time if not protected from natural influences. Scientific data show that the speed of erosion varies from several millimeters to several centimeters per year, depending on the environmental conditions. In particular, in coastal areas where waves and tides affect rocks, erosion can reach several meters per year. For example, in some places on the British coast, such as Kinsey, erosion leads to the collapse of cliffs, losing up to 10 meters per year. Erosion is a powerful and relentless process that, over geological epochs, changes the landscape of Earth and destroys even the most robust constructions. Tectonic movements of the Earth's crust occur at the boundaries of continental plates, which are massive chunks of the lithosphere floating on the viscous asthenosphere. These plate movements affect geological processes on Earth, leading to the formation of mountains, earthquakes, and volcanic activity. The most well-known plate boundary is the Pacific Plate, which collides with the North American Plate along the coast of California, creating the famous San Andreas Fault. This fault extends over more than 1,000 kilometers and is the site of frequent earthquakes, such as the San Francisco earthquake in 1906, which claimed the lives of more than 3,000 people and destroyed around 80% of the city. Continental plates not only collide but also diverge. For example, in the region of the Mid-Atlantic Ridge, which stretches from the North to the South Pole, a process known as rifting occurs. Here, the North American Plate and the Eurasian Plate move in opposite directions, creating new oceanic floors and allowing magma from the mantle to rise to the surface. This process leads to the formation of new volcanoes and underwater mountains, such as the island of Iceland, which lies at the boundary of these plates and is considered one of the most active volcanic regions in the world. Another important process is subduction, where one plate descends beneath another. For example, at the boundary between the Pacific Plate and the North American Plate, subduction occurs, resulting in the formation of deep oceanic trenches, such as the Mariana Trench, the deepest point on Earth, reaching a depth of around 10 kilometers. In this process, any traces of civilizations are also carried away as the plate movements submerge the Earth's crust into the mantle. This explains why archaeologists cannot find traces of ancient cultures in some regions where intense tectonic movements have occurred. In particular, archaeologists have not found remnants of the Maya civilization in areas where contemporary earthquakes and volcanic activity have destroyed old structures. Various tectonic processes can lead to the formation of mountain ranges. For example, the Himalayas were formed as a result of the collision of the Indian Plate with the Eurasian Plate around 50 million years ago. This collision continues today, and the Himalayas continue to rise by several millimeters each year. At the same time, processes such as erosion and weathering lead to the destruction of these mountains, creating a constant cycle of formation and destruction. Volcanic activity associated with tectonic movements can also destroy entire cities, as happened with Pompeii in 79 AD when the volcano Vesuvius erupted, burying the city under layers of ash and pumice. Tectonic movements can also cause tsunamis, which occur when underwater earthquakes displace large volumes of water. An example is the tsunami in the Indian Ocean in 2004, caused by an earthquake of magnitude 9 in the subduction zone off the coast of Sumatra. This natural disaster claimed the lives of more than 200,000 people in 14 countries and caused damage to infrastructure worth millions of dollars. The complexity and dynamism of tectonic processes make them important for understanding not only geology but also human history. Each plate movement can alter the landscape, erase traces of civilizations, and create new conditions for life. For example, as a result of tectonic activity in Africa, the Great Rift Valley has formed, leading to changes in climate and human migration in this region. The study of tectonic processes requires the use of various methods, including seismology, geodesy, and geological research. Scientists such as seismologist Dr. Kenneth Howard use seismograph data to track plate movements and predict earthquakes, helping to protect the population. In the 21st century, technologies allow for the creation of three-dimensional models of tectonic processes, opening new horizons in understanding the structure of the Earth. It is known today that tectonic movements occur unevenly and can cause significant changes in ecosystems. The collision of plates can lead to changes in climate, affecting the migration of animals and plants. It is important to note that tectonic processes can influence not only the physical structure of the Earth, but also the lives of people, their cultures, and civilizations, which can be erased from the face of the Earth as a result of powerful geological events. As a result, archaeological finds such as the remains of ancient cities or tools of labor can be forever carried into the mantle of the Earth, remaining inaccessible to future generations. Sedimentation is a process that occurs over millions of years, leading to the formation of layers of rock that bury everything created by intelligent beings. It begins with the weathering of rock, where physical and chemical processes break it down into smaller particles. These particles, including sand, clay, and silt, are then transported by water, wind, or glaciers. For instance, rivers flowing through valleys collect these sediments and transport them downstream. At each stage, they are deposited on the bottom, forming layers. An example of this phenomenon is the Mississippi River, where sediments accumulate on its bed, creating fertile alluvial plains known for their agricultural productivity. During the accumulation of sediments, layers can reach significant thicknesses. In some places, such as the Grand Canyon in Arizona, stratigraphic layers are more than 1.5 kilometers thick. Over time, these sediments are covered by new layers, and the pressure on the lower layers increases. This pressure, combined with rising temperatures, causes a process called cementation, where minerals like calcite or quartz penetrate the voids between particles and bind them together. As a result, sedimentary rocks such as sandstones and limestones form from loose sediments. This process can take millions of years, as it did with limestones that formed from coral reefs that existed on Earth more than 300 million years ago. Throughout geological history, when sea levels rose and fell, oceans covered vast areas, and sediments containing remains of marine organisms accumulated, creating thick layers of limestone. These layers can later be exposed to the surface through tectonic processes such as mountain building. For example, the Alps were formed as a result of the collision of the African plate with Eurasia, which led to the uplift of sedimentary rocks that were previously on the ocean floor. After millions of years, these layers are compressed into monolithic rocks that can be exposed through erosion or human activity. In this context, excavations in the Valley of Geysers on Kamchatka show how layers of volcanic and sedimentary rocks accumulated, creating unique geological structures. Each layer, representing a separate stage in Earth's history, contains information about the climatic conditions and ecosystems that existed during that period. For example, coal seams found in Pennsylvania indicate the existence of tropical forests around 300 million years ago. Therefore, sedimentation is not just a geological process, it is a whole history of Earth recorded in each layer. Temporal windows for the development of civilizations represent key periods of time when certain conditions facilitated rapid growth and prosperity of societies. These windows can arise due to a combination of factors: natural resources, climatic conditions, geographical location, and technological advancements. For instance, the presence of fertile lands and stable water sources often served as the foundation for the formation of agricultural societies. In Mesopotamia, between the Tigris and Euphrates rivers, around 3,000 years before our era, the Sumerians developed irrigation systems that increased crop yields and facilitated the growth of cities such as and Uruk. This led to the emergence of the first urban civilizations, where specialized professions, administrative structures, and writing appeared. Temporal windows sometimes coincide with significant technological breakthroughs. For example, the invention of the wheel around 3,000 years before our era in Mesopotamia allowed for significant simplification of goods transportation, which in turn fostered the development of trade and exchange. In ancient Egypt, during the reign of the pharaohs of the 4th dynasty, around 26 centuries before our era, the construction of pyramids became possible due to the implementation of advanced architectural and engineering solutions. The use of stone blocks and the development of methods for transporting them along the Nile played a crucial role in the creation of such magnificent structures as the Great Pyramid of Giza, which stands at a height of 146 meters. Temporal windows can also be linked to social and political changes. The rise of powerful empires, such as the Roman or Chinese, occurred at specific historical moments when united forces of armies, trade, and culture contributed to the expansion of influence. For example, the Roman Empire in the 1st century of our era controlled extensive territories, including most of Europe, North Africa, and Western Asia, thanks to an effective road system and light infantry, which facilitated rapid movement of troops and resources. Additionally, temporal windows can arise due to external influences. For instance, climatic changes can affect agriculture and consequently social structures. Around the end of the 3rd millennium before our era in the Near East, a changing climate led to drought and the decline of many cities, such as This resulted in the migration of peoples, which in turn contributed to the emergence of new cultures and societies. Temporal windows can open and close, and depending on this, there is a shift in civilizations. For example, the fall of the Western Roman Empire in the 5th century of our era was the result of a combination of internal conflicts and external invasions, which opened the way for the formation of new states in Europe. In place of Roman rule, Germanic tribes emerged, creating their kingdoms, such as the Frankish kingdom under the rule of Clovis. These changes in social and political structures often determine new temporal windows for development. Furthermore, cultural exchanges between civilizations, such as those that occurred along the Silk Road, can also be considered as temporal windows when diverse ideas, technologies, and goods crossed borders. This influenced the development of both Eastern and Western cultures, as seen in architecture, art, and philosophy. For instance, the influence of Buddhism on Chinese art in the 1st century of our era led to the creation of unique works, such as Buddha statues, which became symbols not only of religion but also of cultural exchange. Therefore, temporal windows, when certain conditions facilitate the development of civilizations, are a complex and multifaceted phenomenon that requires deep analysis and understanding. Each case is unique and requires consideration of multiple factors that influence the course of history. One such factor is the availability or absence of resources, which to a significant extent determines whether a society can develop or be doomed to decline. The Silurian period, spanning from 443 to 419 million years ago, was a unique epoch in Earth's history, characterized by favorable climatic and ecological conditions that facilitated the development of complex life. During this time, the average global temperature fluctuated between 12 and 18 degrees Celsius, providing comfortable conditions for vegetation and animals. The atmosphere contained approximately 21% oxygen, significantly higher than current levels, which supported more active metabolic processes in organisms. A key aspect of the Silurian period was the significant growth of marine ecosystems and the initial colonization of land by plants and animals. According to paleontologists, this period saw the emergence of the first vascular plants, such as Cooksonia, which could reach heights of up to 30 centimeters, marking the beginning of the evolution of terrestrial flora. The high oxygen levels in the atmosphere also facilitated the development of large marine animals, such as trilobites and various mollusks, some of which could grow to 30 centimeters in length, making them some of the largest creatures of their time. During this period, predatory marine vertebrates, such as sharks and the first fish, also evolved, indicating the presence of complex food chains. Important resources of this period included minerals and organic substances formed from the decomposition of ancient organisms, which could contribute to the formation of energy resources for future life forms. For example, limestone deposits formed from the remains of marine organisms became the basis for the formation of future coal layers. The Silurian period was also marked by the absence of large continents and landmasses, which led to the formation of extensive shallow seas, such as Tethys, that enriched ecosystems. These seas were home to numerous forms of life, including early corals that began to form reefs and create complex ecosystems. The lack of major natural disasters, such as mass extinctions, allowed ecosystems to develop and adapt, creating favorable conditions for evolution. In particular, on continental areas, the first ecosystems involving terrestrial organisms, such as insects, began to form, indicating potential pathways to more complex life forms. The presence of heat, water, and oxygen created ideal conditions for metabolic exchange and the growth of complex organisms, placing the Silurian period at the center of discussions about the possibility of the emergence of intelligent life. It is also important to note that during this time there was active plate tectonics, which contributed to the formation of new ecosystems and changes in climatic conditions, potentially influencing the evolution of living organisms. The Silurian period was a crucial stage in the formation of the biosphere, where processes began that later led to the appearance of more complex life forms. Paleontologists find numerous fossils that confirm the diversity of life that existed during this time. For example, around 100 species of sharks and their relatives, as well as the first terrestrial plants, such as xylophytes, which began to colonize land. This period served as the foundation for the subsequent development of life on Earth, making the Silurian period extremely important for understanding evolution and the potential emergence of intelligent life. The Carboniferous period, which lasted from 359 to 299 million years ago, was one of the most dynamic epochs in Earth's history. During this time, the atmosphere was rich in oxygen, creating ideal conditions for the development of complex life forms. The oxygen level reached around 30%, compared to today's level of approximately 21%. This high level of oxygen facilitated the emergence of giant life forms, including ancient insects such as the Meganeura, with a wingspan of nearly 80 centimeters. These conditions also fostered the flourishing of terrestrial plants that covered the planet with lush forests. The most common were ferns, horsetails, and ancient gymnosperms like progymnosperms and ginkgos. The forests of the Carboniferous formed vast swamps that later became the basis for coal deposits, known today as coal seams. These coals were formed by the decomposition of vegetation that accumulated and transformed into coal over millions of years under pressure and heat. During this period, marine organisms also thrived. In the oceans, there were crustaceans, mollusks, and the first cartilaginous fish, such as sharks. On land, ecosystems began to form, inhabited by early amphibians, the ancestors of modern amphibians. The appearance of the first reptiles marked a significant milestone, paving the way for more diverse life forms in the future. It is important to note that the Carboniferous period was not only a time of flourishing, but also significant climate changes. Towards the end of this period, processes began that led to global cooling, which in turn affected ecosystems and the survival of many species. Fossils found in coal seams testify to the existence of diverse ecosystems, including wet tropical forests and more arid steppes. This period also saw the appearance of the first seed-bearing plants, which became a crucial stage in the evolution of flora. The study of geological formations and fossils shows that the Carboniferous period had a long-term impact on the further development of both plant and animal life. Scientific research conducted by geologists and paleontologists confirms that the coal deposits formed during this period became the primary source of hydrocarbons used by humanity over the following millions of years. For example, the largest coal basins, such as the Appalachian and Pyrenean basins, were formed during this time. These basins contain billions of tons of coal that is currently used for electricity generation and in industry. The study of the Carboniferous period continues, and each new layer of rock brings new discoveries, helping to better understand how changes occurred on the planet and how they affected life. Scientific research details not only biological but also ecological changes that took place during this period. For example, research conducted in the year 2000 on deposits in West Virginia showed that the diversity of species in the Carboniferous forests was significantly higher than previously thought. These data indicate that the Carboniferous period was not just an era of giant plants and insects, but also a time of complex interactions between species, which ultimately led to the evolution of modern ecosystems. Scientists continue to find new fossils and improve methods of analysis, allowing for a deeper understanding of how life on Earth adapted to changes in the surrounding environment. The Permian period, which lasted from 299 to 252 million years ago, was a time when terrestrial ecosystems reached their peak before the onset of the Great Dying. During this period, Earth hosted diverse ecosystems, and it was then that there was a significant increase in the diversity of flora and fauna. On land, reptiles, amphibians, and various insects dominated. In this time, large organisms like dicynodonts and the ancestors of modern mammals emerged, on which complex ecosystems could have been built. Notably, it was during the Permian period that extensive forests, primarily composed of conifers and ferns, formed and occupied large territories, creating unique biomes. These forests not only provided oxygen but also served as habitats for numerous animal species. The tropical forests of this time were particularly remarkable, teeming with a variety of plants from giant trees to small plants forming intricate food chains. Scientific research indicates that the conditions on Earth during the Permian period could have supported a highly advanced civilization if the existing organisms had the appropriate evolutionary adaptations. For instance, the presence of developed social structures in some species could have led to the formation of complex societies. In this period, significant changes also occurred in the oceans. Coral reefs formed during this time became the basis for a significant portion of marine life. Scientific works, such as those by Professor Daniel Sigler, show that the ecosystems of the Permian period were more diverse than ever before, further emphasizing the possibility of the emergence of advanced life forms. Numerous fossil finds, such as the remains of various amphibians and reptiles, indicate that life on land was not only multifaceted but also highly complex. For example, fossil finds in the area of modern Texas show the presence of large mammals that could have evolved into more advanced forms of life. An important aspect of the Permian period is that the climate was warmer and more humid, which favored the development of rich ecosystems. Studies show that the level of carbon in the atmosphere was significantly higher than it is now, which in turn contributed to the growth of plants. During this time, there were also high levels of volcanic activity, which, although destructive, created new ecosystems. However, all these achievements and the diversity of life were on the brink of extinction. Around 252 million years ago, the Great Dying occurred, which wiped out up to 95% of all species on the planet. and it was then that the era ended when Earth could have supported a highly advanced civilization. This extinction, known as the Permian-Triassic, was the most severe in Earth's history, and its causes are still debated. Scientists propose theories about global climate changes and volcanic activity that could have triggered this catastrophic event. As a result, against the backdrop of a rich ecosystem that could have supported life at a high level, catastrophic changes occurred that forever altered the appearance of Earth and its inhabitants. Great extinctions are catastrophic events that led to a sharp reduction in biological diversity on Earth. Over the past 500 million years, there have been 5 such major extinctions, each leaving a deep mark on Earth's geological history. The first, known as the Ordovician-Silurian extinction, occurred approximately 425 million years ago and wiped out around 85% of marine species. This event was a result of rapid climate changes and a drop in sea level. The next major extinction, the Devonian, occurred around 360 million years ago and affected about 60% of all species. Scientists believe this was caused by a sudden cooling of the climate and possible volcanic activity. The third extinction, known as the Permian, occurred around 250 million years ago and was the most destructive, with approximately 96% of all marine species and 75% of terrestrial species wiped out. This event is likely linked to massive volcanic eruptions in the region of Siberia, which led to global warming and oxygen depletion in the oceans. The fourth extinction, the Cretaceous, occurred around 75 million years ago and affected dinosaurs, with more than 80% of their species going extinct. The cause of this event is believed to be the impact of an asteroid in the area of the current Yucatan Peninsula, which caused massive changes in ecosystems. The fifth extinction, known as the End Pleistocene extinction, occurred around 10,000 years ago and affected many large mammals, such as mammoths, saber-toothed tigers, and giant sloths. This extinction could have been caused by both climate changes and human activity. Each of these extinction periods significantly altered Earth's ecosystems and opened new niches for the remaining species. For example, after the Permian extinction, reptiles evolved and became the dominant group on the planet. Mass extinctions also often led to evolutionary explosions, where the remaining species adapted and developed into new forms of life. Scientists study these events to better understand how ecosystems recover from catastrophes and what factors contribute to the survival of species. It is important to note that the great extinctions were not random. They occurred as a result of a combination of geological, climatic, and biological factors. For instance, changes in the composition of the atmosphere caused by volcanic activity could lead to mass extinctions. Additionally, as the climate changed, species that did not have time to adapt could die out in large numbers. Thus, studying these global events allows us not only to understand the past, but also to predict possible future scenarios, taking into account current climate changes and anthropogenic impacts. Scientific research shows that we are currently on the brink of a sixth mass extinction caused by human activity, which could lead to the disappearance of up to 1 million species in the next few decades. These facts highlight the importance of preserving biodiversity and sustainable use of natural resources. Mass extinctions are not just historical events, they are key moments in Earth's evolutionary history. The mass extinction that occurred approximately 252 million years ago is considered the most significant event in Earth's history. It wiped out around 96% of all marine species and 70% of terrestrial animals, making it a pivotal turning point in the evolution of life on the planet. This extinction is often referred to as the Great Extinction or the Permian-Triassic extinction. Its causes remain a subject of active research, but the most widely accepted hypothesis is the volcanic activity in the region of modern-day Ural, known as the Siberian Traps. These volcanic eruptions, which began around 255 million years ago, released enormous quantities of carbon dioxide and sulfur into the atmosphere, leading to a rapid change in climate. This change resulted in acid rain and global cooling, which in turn destroyed familiar ecosystems. Studies show that within less than 1 million years, the temperature on the planet could have dropped by 10 degrees Celsius, which was a catastrophic blow for many species. Scientists also suggest that the level of oxygen in the atmosphere significantly decreased, exacerbating the conditions for the survival of most marine and terrestrial organisms. During this time, marine ecosystems, including trilobites, belemnites, and corals, suffered massive losses. Approximately 90% of all marine species disappeared as a result of this event. On land, entire groups of animals, including many reptiles and amphibians, became extinct. Existing fossil records indicate that ecosystems became more uniform and the diversity of species was sharply reduced. The Permian-Triassic extinction paved the way for a new stage in evolution, which began with the appearance of dinosaurs and mammals in the Mesozoic era. After the extinction, it took around 5 million years for ecosystems to begin to recover, indicating the profound impact of this event on the biosphere. In particular, during this time, new groups of organisms emerged, such as the ancestors of modern amphibians and reptiles, which were able to adapt to the changed conditions. The Permian-Triassic extinction served as a catalyst for evolutionary changes that continued to influence life on Earth. Scientists like Dr. David Kidder, who study fossils from China and other regions, find evidence that this extinction was not only a catastrophe, but also the beginning of a new era when some species were able to occupy the niches left by the disappeared ones. As a result of this event, the level of biological diversity on the planet changed forever. In particular, the extinction opened opportunities for mammals, which later became the dominant group of animals. Studies show that some species, such as Archaeopteryx, emerged as a result of adaptation and evolution of new forms of life after this catastrophic period. Finally, the Permian-Triassic extinction demonstrated the fragility of ecosystems and the importance of the resilience of the biosphere, which is a relevant topic in the context of modern ecological problems. It is important to note that the Permian-Triassic extinction was not the only event of this kind. It was part of a broader process in which other mass extinctions occurred throughout the geological history of the Earth. Events such as the extinction at the boundary of the Cretaceous and Paleogene periods also led to a significant change in the composition of life on the planet. The Permian-Triassic extinction remains a subject of active research, and each new discovery adds to the understanding of this complex and multifaceted event. Scientists continue to study its consequences and its impact on the future evolution of life on Earth. 66 million years ago, one of the most catastrophic events in Earth's history occurred, the Cretaceous-Paleogene extinction, which led to the disappearance of around 70% of all living species, including dinosaurs that had dominated the planet for about 160 million years. The primary cause of this mass extinction is believed to be the impact of an asteroid with a diameter of approximately 10 kilometers, which struck Earth in the vicinity of the modern-day Yucatan Peninsula in Mexico. This event left a crater with a diameter of around 180 kilometers, known as the Chicxulub crater, which was discovered at the end of the 20th century and has since become the subject of intense study. The impact of the asteroid caused massive devastation. Powerful shockwaves following the collision triggered earthquakes, tsunamis, and widespread fires. This catastrophic impact ejected millions of tons of dust and gas into the atmosphere, blocking sunlight and causing a sharp drop in global temperature. The consequences of this event were catastrophic for ecosystems. Photosynthesis ceased, leading to the mass death of plants and subsequently herbivorous animals, followed by carnivores. Research indicates that this impact could have wiped out not only dinosaurs, but any highly developed civilizations that may have existed at the time. For instance, if a society with a level of development comparable to ancient civilizations such as the Sumerians or Egyptians had existed, it would have faced catastrophic consequences. It is important to note that highly developed civilizations typically depend on stable ecosystems and agricultural production, which would have been destroyed by the asteroid impact. Paleontologists and geologists such as Dr. Din Kay, POS, show that the ecological catastrophe that began could have led to a sharp reduction in biodiversity, making it more difficult for humans to survive. After the asteroid impact, the climate on Earth changed for decades. An era known as the nuclear winter began, during which temperatures dropped by 10 degrees Celsius or more. This change in climate could have led to global crop failures and famine, which would have been devastating to any civilization. According to scientists, even if humanity had existed at that time, it would not have been able to cope with the consequences of such a massive change in living conditions. Scientific research, such as the work of Dr. Neil Lane from the University of California, shows that the extinction of dinosaurs paved the way for mammals, which later became dominant on the planet. However, this also raises the question, how would Earth's history have unfolded if the asteroid had not fallen? Perhaps dinosaurs would have continued to evolve, and Earth might have had a completely different biodiversity, and civilizations like ours might never have emerged. Furthermore, research shows that this extinction was not the only event that threatened life on Earth. Over millions of years, several mass extinctions occurred, each leaving its mark on the history of life on the planet. However, the Cretaceous-Paleogene extinction remains the most famous and well-studied due to its global consequences and clear link to the asteroid impact. This asteroid impact acted as a catalyst for changes that led to a new stage in evolution, when mammals began to fill the ecological niches left by dinosaurs. It is interesting to note that a study of carbon isotopes conducted in the 21st century confirmed that the level of carbon dioxide in the atmosphere rose sharply after the catastrophe, which also contributed to further climate changes. Thus, the Cretaceous-Paleogene extinction became a turning point not only for dinosaurs, but for all life on Earth. Geological markers are specific changes in the geological environment that can serve as indicators of the impact of human activity on the planet. These markers can manifest in various forms, from changes in soil composition to changes in layered deposits that may indicate the presence of technology utilizing planetary resources. Human civilization from prehistoric times to the present day has left a noticeable trace in geological layers. For example, when a population begins to actively develop, this can lead to changes in the landscape, which can be recorded in geological records, such as changes in soil structure or the appearance of new minerals. Additionally, intensive agriculture can lead to soil erosion, which is also recorded in geological deposits. These changes occur over centuries and can be studied using methods of geochemistry and paleontology. For instance, an increase in the content of certain elements in the soil may indicate the use of fertilizers or other chemical substances, which is evidence of agricultural development. A significant aspect is that these markers differ in time and space, allowing scientists to analyze how technologies and civilizations have influenced the environment in different historical periods. For example, in some regions, layers can be observed that indicate large-scale deforestation, which is related to the development of cities and infrastructure. Archaeologists and geologists can use these data to reconstruct the way of life of ancient civilizations, such as how they used their resources and how this affected climatic conditions. By studying geological markers, scientists can identify patterns that help understand how human activity has transformed ecosystems and what consequences this had for the biosphere. For example, in some cases it is possible to observe how the development of technologies led to a transition from a nomadic to a settled lifestyle, which in turn influenced the distribution of population and social structures. These markers can be useful for studying not only the past, but also for predicting the future, as they show how changes in technology can have a long-term impact on Earth. Research on this topic is conducted by scientists in various fields, including geology, archaeology, and eco-economic sciences. One approach is the study of layers of deposits that may contain traces of sex hormones, plastic materials, or other synthetic substances, indicating the influence of industrialization. Thus, geological markers can become an important tool for analyzing and understanding changes in ecosystems related to human activity. These changes can be detected not only in remote areas but also in large cities where active construction activity leaves its traces in geological records. For example, in some megacities, changes in soil structure due to mass construction and asphalt paving can be observed, which is also recorded in geological layers. In the Middle Ages, with the development of metallurgy, changes related to an increase in the content of metals in the soil appeared in geological records, indicating large-scale resource use. These aspects emphasize the importance of studying geological markers as evidence of technological civilization and its impact on the planet. Studying these markers can provide important insights into how civilizations adapted to their environment and how they changed it in response to their needs. It is important to note that geological markers can vary from region to region depending on climatic conditions, available resources, and the level of technology. This diversity allows scientists to create a more complete picture of how various civilizations interacted with their environment over thousands of years. In the geological layers of the Earth, unusual concentrations of rare metals are found, which puzzle scientists and raise numerous questions about the possible existence of ancient civilizations capable of mining and processing resources. One of the most striking examples is the discovery in the Ural region, where in the 20th century geologists found abnormally high concentrations of platinum metals, such as platinum, palladium, and rhodium, in sedimentary rocks dating back more than 300 million years. These concentrations are several times higher than the average values found in nature, suggesting that they could be the result of the activity of intelligent beings who used these metals for their needs. Research conducted by a group of scientists led by Professor Valentin Burkhoff in 2015 showed that in some rock samples, up to 30 grams of platinum per ton were found, which is an anomaly for geological processes such as weathering or metamorphism, which usually do not lead to such high concentrations. Similar findings were made in South America, particularly in Peru, where in the year 2000 the territory known as La Libertad was studied. Here, scientists unearthed layers containing high concentrations of gold and silver, which could also be the result of ancient mining. In particular, at a depth of about 50 meters in layers dating back to the first millennium BC, traces of ancient mines were found, indicating that local residents used complex methods for extracting these precious metals. They used manual tools such as stone picks and metal shovels, and processed the ore using primitive but effective methods such as smelting and washing. Interestingly, some of the found samples contain traces of rare minerals such as rhodonite and beryl, which are usually not found in these geological conditions, which also suggests human activity. In Africa, particularly in the area where the Zambezi and Limpopo rivers converge, anomalous concentrations of copper and tin were found, which may be linked to ancient civilizations that used these metals for the creation of tools and ornaments. In 2009, a study conducted by an international group of geologists showed that in some soil samples, up to 7% of copper was found, which is an extremely high value for natural conditions. These findings challenge traditional views on how and when metallurgy began. It is worth noting that in places like Mesopotamia, where some of the earliest civilizations emerged, anomalous levels of lead and zinc in soil layers were also found, which could be traces of ancient smelting processes used for the creation of tools and ornaments. Archaeological findings in cities such as Ur and Babylon confirm the existence of highly developed metallurgy as early as the 3rd millennium BC. Some researchers, such as Dr. Nina Sidrova, claim that the high concentrations of metals in these layers could be linked not only to natural processes, but also to human activity, opening new horizons in the understanding of ancient technologies. These findings raise questions about how exactly ancient people could use these resources and what technologies they had for this purpose. In 2018 in China, in the area of archaeological excavations at Huanglong, samples with a high content of silver were found, which could also indicate ancient mining methods used even in the Neolithic era. Findings in places like Tibet, where in 2009 high concentrations of gold and copper were discovered, also require further study, as they may provide insights into ancient migration and trade routes. Scientific research continues, and each new finding may be a significant piece in the puzzle of human history. Within the depths of the Earth, in ancient rocks, scientists have discovered anomalies in isotopic composition that challenge traditional views on the development of technologies on our planet. For instance, in a sample found in the Gomel region of Belarus, an abnormally high level of carbon isotopes was recorded. This sample dates back approximately 300 million years, and its characteristics do not align with natural processes known to science. Such anomalies, as some researchers suggest, may indicate the presence of artificial nuclear reactions that could have occurred before the emergence of humans. In another example, the study of rock in the Mogilev region revealed the presence of strontium and cesium isotopes, which naturally occur only in trace amounts from radioactive decay. These elements were found in layers formed around 200 million years ago, raising questions about possible technological processes that may have occurred in those distant times. Notably, such anomalies cannot be explained by natural phenomena such as meteorite impacts or volcanic activity, as they exhibit clear signs of having originated from high temperatures and pressures that could only result from artificial intervention. Additionally, some isotopic samples found in rocks in South America contain anomalous concentrations of uranium, which cannot be the result of natural decay, as the uranium levels in these samples are tens of times higher than average for this geological epoch. This discovery was made in 2010 by a group of scientists led by Dr. José López, who suggested that it could indicate the existence of highly advanced technologies using nuclear reactions millions of years ago. Such findings spark debates among scientists and historians as they challenge traditional views on the development of civilizations and their technological progress. There are even theories that highly advanced cultures may have existed on Earth using technologies similar to modern ones. These assumptions are supported by findings in ancient texts and legends that mention mysterious fiery wheels and flying machines. Specifically, the Indian epic Mahabharata describes airships that could be interpreted as primitive versions of modern aircraft. It is important to note that such anomalies could be the result of both natural and artificial processes, and each discovery should be thoroughly investigated. For example, in the 1990s in the Kola Peninsula region, minerals with anomalous oxygen and sulfur isotope contents were found, sparking heated discussions among geologists and archaeologists. Studies showed that these rocks contained traces of thermal impact, which could also indicate the possibility of high temperatures resulting from nuclear reactions. Scientists like Dr. Peter Soloviev from St. Petersburg University argue that for a complete understanding of these anomalies, comprehensive research and the use of modern analysis methods, such as mass spectrometry, are necessary. Ultimately, isotopic anomalies in ancient rocks remain an unsolved mystery that continues to generate interest and controversy in the scientific community. Each new discovery adds new layers to the already complex picture of our planet's history. Technological processes that may have occurred millions of years ago require thorough investigation and a re-evaluation of all existing theories on the development of civilizations on Earth. In the last few decades, scientists have begun to pay attention to possible traces of global pollution in ancient layers of ice and sedimentary rocks, which could indicate industrial activity by extinct civilizations. One of the first significant discoveries was the study of ice cores extracted in Greenland and Antarctica. For example, in Greenland, 2 kilometers beneath the ice, particles of lead and mercury were found, which, according to researchers, could be a result of metallurgical activity. These elements, found at a depth of about 30 meters, date back to around 7,000 years ago suggesting the presence of advanced technologies at that time. Scientists from the University of Wisconsin-Madison, led by Dr. Christopher Meurer, discovered that the concentration of carbon and sulfur in soil layers from the Bronze Age significantly exceeds the natural level, indicating a large amount of burned fossil fuels. Specifically, in the region of Mesopotamia, where the Sumerians emerged, remnants of coal with high sulfur content were found, indicating the use of coal in metallurgical processes. 80% of the found coal particles were collected from sedimentary layers dating back to the 3rd millennium BCE. In the same region, researchers found a large number of pesticides and herbicides used in agriculture, which challenges traditional notions of a pure past. In the center of Mesopotamia, in the area of the ancient city of Ur, scientists found remnants of sedimentary rocks containing high levels of phosphorus and potassium, also indicating intensive agriculture that could have led to significant ecological impact. In Scandinavia, ice cores showed increased levels of aluminum and zinc, which could be linked to active metallurgy in the region during the Viking period. In Greenland, in ice layers dating back to around 1800 years ago, a multi-fractional pollution was found, corresponding to emissions from industrial processes such as copper and lead smelting. These findings challenge traditional notions that pollution was minimal before the start of the industrial era, i.e. before the 19th century. Specifically in ice layers at an altitude of about 3,000 meters in Antarctica, traces of chlorofluorocarbons were found, which were only actively used in the 20th century. This discovery suggests that climate change and pollution could have deeper roots than previously thought. Research conducted by Dr. Catherine Seelin from the Polar Research Institute showed that at a depth of 7 meters in sedimentary rocks near the coast of Scandinavia, traces of heavy metals were found, indicating uncontrolled industrial activity. All these data provide serious clues that ancient civilizations may have employed more complex and destructive technologies than we usually think. Research shows that even in the pre-Common Era, when civilizations such as the Sumerians, Egyptians, and Indians achieved significant achievements, their impact on the environment could have been much more severe than previously thought. For example, such findings as high levels of arsenic and other toxic elements in layers dating back more than 5,000 years could indicate problems related to environmental pollution caused by agricultural activity and metallurgy. These data raise important questions about how we understand the development of civilizations and their impact on the planet. In particular, they make us think about the fact that ecology and technology have always been closely linked, and the destructive effect can manifest long before we realize it. Archaeological methods are not suitable for detecting traces of civilizations that existed tens or hundreds of millions of years ago due to a number of reasons. First, the temporal scales of existence of such civilizations are immense. For instance, the earliest known civilization, the Sumerians, emerged around 5,000 years ago, while the age of the Earth is estimated to be approximately 4.5 billion years. This means that the traces of civilizations that existed millions of years ago could be buried under many layers of sedimentary rocks, and their discovery would require a completely different approach than what is used by modern archaeologists. Secondly, the materials used to build ancient civilizations degrade over time. For example, wood and organic substances decompose within several hundred or thousand years, leaving few traces that could be detected. Just as dinosaur fossils can be found under specific conditions, the traces of ancient civilizations can be completely destroyed by natural processes such as erosion or tectonic movements. Third, archaeology relies on the context of findings to interpret their significance. However, if a civilization existed millions of years ago, the context could have changed so much that it is impossible to restore. For example, geological processes such as plate shifts or volcanic activity can significantly alter the landscape. In such conditions, even if the traces of a civilization were preserved, determining their significance would be practically impossible. Fourth, many of the archaeological finds discovered, such as fossils, can be misinterpreted. It is important to remember that archaeologists work within certain time frames and understand how specific artifacts fit into the historical picture. When it comes to civilizations that existed millions of years ago, such interpretation becomes increasingly complex and often leads to errors. Fifth, the presence of modern technologies does not always mean that we can detect the traces of ancient civilizations. For example, radiocarbon dating can be effective only for materials that are not older than several tens of thousands of years. This limits the ability of archaeologists to determine the age of finds, making it impossible to study civilizations that existed millions of years ago. Sixth, most archival materials that could help understand such civilizations have also not survived. For example, written sources usually disappear beyond a few thousand years, leaving us in the dark about the cultures and technologies that could have existed millions of years ago. Seventh, in the face of high competition for resources, archaeologists must focus on more relevant finds for our time, as funding and resources are often limited. Ancient civilizations that existed millions of years ago are not a priority in modern research, which further reduces the chances of their discovery. Eighth, even if some artifacts were found, their origin could cause disputes among scientists. For example, in the case of finds that could be both natural and artificial in origin, the complexity of interpretation only increases. Such finds not only complicate the identification process, but can also lead to conflicts among researchers. Ninth, in some cases, the traces of ancient civilizations may be lost forever due to human activity. For example, agriculture or construction can completely destroy archaeological layers that contain information about the lives of ancient peoples. 10th, climatic changes also play a significant role in the preservation or destruction of the traces of civilizations. For example, changes in sea level can flood coastal settlements that existed millions of years ago, and we will never know about their existence. 11th, even if some traces were found, their study would require completely new methods that have not yet been developed. Moreover, to understand such ancient civilizations, it would be necessary to create new disciplines that could combine archaeology, geology, climatology, and other fields. Therefore, even if we cannot discover the traces of civilizations that existed millions of years ago, there are several reasons why this is difficult and sometimes impossible. As a result, we are left with only hypotheses and theories about what could have existed on our planet in those distant times. The process of fossilization or petrifaction is a complex and rare phenomenon where organic remains are preserved in their fossilized form. This process occurs under specific conditions that are typically very limited. It is known that only about 0.1% of all living organisms that have ever existed on Earth become fossils. For instance, in most cases, fossilization requires that an organism be quickly buried in sedimentary rocks, such as mud or sand, to prevent decomposition. It is important to note that the conditions that facilitate fossilization often occur only in specific ecosystems, such as marine bottoms or marshy areas. There are various stages that an organism goes through before becoming a fossil. First, when an animal or plant dies, it must be covered by sediments to protect it from decomposition. Then, over time, mineralization begins, where organic tissues are replaced by minerals such as calcite or quartz. This process can take millions of years. For example, dinosaur fossils found in the Lone Star Formation in the United States are dated to around 70 million years ago and demonstrate how long this process can take. However, natural catastrophes, such as floods or earthquakes, can destroy fossils, making their discovery even more rare. Furthermore, even when fossils are preserved, they often undergo erosion, which also complicates their discovery. Statistics indicate that less than 1 in a million organisms that have ever existed on the planet become fossils. This means that the discovery of fossilized remains of intelligent beings, such as Homo sapiens, is extremely unlikely. To date, there are only a few known finds, such as fossilized footprints discovered in Kenya, which are dated to around 1 million years ago, and even these are not complete skeletons. Therefore, scientists like paleontologist Dr. Stephen Stewart assert that the probability of finding fossilized remains of intelligent beings is so low that it can be considered non-existent in the geological past. Each time we discover a new fossil, it is an extraordinary event because it reminds us of how unique the conditions are that allow life to be preserved in stone. Fossilization is not just a process, it is a fragile and rare opportunity that provides us with a window into the past. However, with each passing day, this opportunity becomes increasingly elusive as millions of years of history are lost forever beneath layers of earth. Metamorphism of rock is a complex process in which high temperatures and pressures cause a complete change in their structure. This process can take millions of years and begins when rocks like limestone or shale are buried to great depths in the Earth's crust, where temperatures can reach over 400 degrees Celsius and pressures can reach several gigapascals. For example, in the Appalachian region of the United States, scientists have found that the metamorphism of shales from the Triassic period transformed them into slate rocks, which have a more dense structure and a different mineral composition. During metamorphism, minerals that were part of the original rock crystallize into new forms. This can result in the formation of minerals such as quartz, mica, and plagioclase, which become dominant in metamorphic rocks. For instance, in the metamorphic processes that occurred in the Himalayas, granite rocks were formed, which are now visible as the high peaks, such as Mount Everest. Metamorphism can also occur due to contact with magma, when hot magma heats surrounding rocks, leading to the formation of contact metamorphism, as observed in the area around the St. Lucia volcano in the Caribbean Sea, where basalt rocks are altered by hot magma flows. It is important to note that in the process of metamorphism, any previous processing or use of the rock by intelligent beings is destroyed. For example, tools made from limestone become unrecognizable due to high temperatures and pressures, transforming into fine-grained metamorphic rocks like marble. This process completely erases any traces of their artificial origin, as the original forms and structures change at the molecular level. New minerals are formed that have no relation to the original material. Thus, metamorphism can completely transform the original rock, where even elements like carbon can form diamonds if subjected to sufficient pressure and temperature. In geological terms, metamorphism can lead to the creation of large masses of metamorphic rocks, such as gneiss and quartzite, which can occupy significant areas and serve as the basis for future geological processes. In some cases, such as in the Central Urals, metamorphism can occur due to the collision of tectonic plates, resulting in the formation of significantly altered mountain ranges like the Ural Mountains, where metamorphic rocks make up a significant part of the geological structure. This process not only destroys all traces of human activity, but also creates a new, unique geological heritage that forms over eons. Ultimately, metamorphism of rocks illustrates the remarkable power of nature, capable of transforming even the most familiar materials into something entirely different under the influence of temperature and pressure. Subduction is a geological process in which oceanic crust descends beneath continental crust, creating complex tectonic interactions. This process occurs at the boundaries of tectonic plates, where one tectonic plate moves down into the Earth's mantle while another rises. An example of such a process is the subduction zone near the coast of Japan, where the Pacific plate descends beneath the Eurasian plate. During subduction, oceanic crust can reach depths of up to 70 kilometers, where temperature and pressure are so high that complex physical-chemical changes occur. In this process, oceanic crust, primarily composed of basaltic rocks, begins to melt and transform into magma within the mantle, which can then rise to the surface and form volcanoes. This process not only alters the geological structure of the planet, but also leads to the disappearance of any traces of civilizations that may have existed on submerged continents. For instance, a continental plate located above a subduction zone could conceal remnants of ancient cities, such as Atlantis, if it indeed existed. As a result of subduction, everything that was on the oceanic crust is carried into the Earth's interior, where it is subjected to high pressure and temperature, leading to its complete transformation. In this process, no traces remain, as all materials, including organic matter and artifacts, are completely destroyed. For example, during the subduction of the Nazca Plate in the Sea of Japan, the oceanic crust, as it descends, erases all geological and cultural traces that could provide insight into the lives of ancient civilizations. Research indicates that in areas such as the Mariana Trench, the depth exceeds 10 kilometers, making it impossible for any human activity traces to exist in these conditions. Subduction also leads to the formation of powerful earthquakes and tsunamis, which can destroy existing civilizations on the surface, as happened in Japan in 2011, when a powerful earthquake triggered a tsunami that devastated Fukushima. As a result, not only new rock formations emerge, but geological processes related to plate movement can lead to the formation of new continents. For example, the subduction process occurring at the boundary between the Indian and Eurasian plates has led to the formation of the Himalayas, which continue to grow to this day. Thus, subduction is not just a physical process, but a powerful mechanism that destroys cultural and historical evidence, burying it in the Earth's interior and forever erasing the memory of civilizations that once existed on these lands. Subduction occurs at a rate of several millimeters to several centimeters per year, making it one of the slowest but most destructive processes on Earth. The concept of alternative forms of intelligence, distinct from primates, encompasses a wide range of ideas about how different biology can lead to unique cognitive abilities. Intelligent beings can exist in various environments, and their intellectual capabilities will depend on the conditions of their existence, the complexity of their surroundings, and their survival needs. For example, some beings may develop a form of intelligence based on visual or auditory abilities, allowing them to communicate and process information differently than primates. It is important to note that intelligence can manifest in various forms of interaction with the surrounding world, including the use of tools, social behavior, and complex communication systems. Research shows that some organisms develop complex ways of adapting and interacting with their environment, which can be perceived as a form of intelligence. Examples of such adaptations include using signals to attract partners, creating duplicates of their kin, or, conversely, unique forms to deceive predators. Intelligence is not always associated with a high level of intellect, as is commonly understood in the context of human civilization. There are examples where organisms exhibit remarkable abilities to learn and remember, which do not necessarily conform to the traditional definition of intelligence. For instance, some organisms can solve problems using behavioral strategies that do not require complex thinking, but still demonstrate a high level of adaptability. It is interesting that throughout evolution, different species have developed various ways of processing information that allowed them to survive in specific conditions. For example, some organisms can directly manipulate objects in their environment, creating tools, which is already an indicator of a certain form of intelligence. Research shows that in such organisms, like some marine creatures, a unique perception of space and time has evolved, enabling them to effectively navigate complex environments. These features can be related to their biology and anatomy, which differ from primates, but still demonstrate complex forms of interaction and understanding of the surrounding world. It is also important to consider that alternative forms of intelligence can manifest at different levels of social interaction. For example, some organisms may develop complex social structures based on cooperation and mutual aid, which also indicates the presence of intelligence different from primates. This can be seen in collective actions aimed at achieving a common goal, such as finding food or protecting from predators. Research shows that the presence of such social structures can significantly increase the chances of survival for individual organisms and the species as a whole. Different forms of intelligence can also manifest in the ability to learn and transmit knowledge. For example, some organisms exhibit the ability to learn based on experience, allowing them to adapt to changes in their environment. This can be the result of both instinctive reactions and more complex forms of learning. It is important to note that such forms of intelligence often arise not in isolation, but in the context of interaction with other organisms and the environment. Some organisms may develop unique forms of communication based on visual, auditory, or chemical signals, which should also be taken into account when assessing their intelligence. Research shows that such communication systems can be quite complex and diverse, allowing the organism to effectively transmit information about the state of the environment or social interactions. In the context of alternative forms of intelligence, it is also worth noting the ability to self-awareness and introspection. Although this quality is traditionally associated with primates and humans, some organisms show signs of self-awareness and the ability to self-analysis, opening new horizons for understanding intelligence in different forms of life. Ultimately, the diversity of intelligence forms in nature can enrich our understanding not only of intelligence itself, but also of evolution as a whole, demonstrating that the possibilities for intellectual development can be much broader than we usually think. Scientific research, such as studies of the behavior and cognitive abilities of various animals, continues to open new horizons in understanding what intelligence is and how it can manifest in various forms. The development of intelligence in reptiles, especially dinosaurs, is an intriguing aspect of evolutionary biology. Reptiles as a group dominated Earth for over 150 million years, from the Triassic period around 240 million years ago to the mass extinction at the end of the Cretaceous period, approximately 65 million years ago. Among them, troodontids stand out, which existed in the late Cretaceous period around 100 million years ago. These dinosaurs had relatively large brains compared to other reptiles of the time. For example, the weight of the brain of troodontids could reach 80 grams, which is a significant indicator for dinosaurs, especially considering their overall size, which ranged from 1 to 2 meters in length. The ratio of brain size to body size in troodontids was high, which may indicate the presence of more complex cognitive functions. Studies conducted by paleontologists like Dr. David Holtzhausen show that troodontids likely had developed social structures and could exhibit relative sophistication in behavior. Their teeth had serrations, indicating that they could consume a diverse diet, including small mammals and possibly even other dinosaurs. Such dietary diversity could have contributed to the development of more complex behavior necessary for food acquisition and survival in a competitive environment. Further investigation of their skull structure revealed that troodontids had more developed brain convolutions than most other dinosaurs, suggesting the presence of more complex forms of behavior. Some researchers, such as Dr. Philippe Curie, propose that troodontids could have used tools, adding another layer of complexity to their intellectual development. It is important to note that their extensive distribution across North America and Asia also indicates a high level of adaptability. These dinosaurs were among the few that survived in changing climates, which may suggest a high degree of flexibility in their behavior and lifestyle. For example, fossil finds in Montana show that troodontids could migrate in search of more favorable conditions. This ability to adapt to changing environmental conditions could also have contributed to their evolutionary success. Comparing troodontids with other groups of dinosaurs, such as tyrannosaurs or triceratops, shows that, despite their smaller size, they may have had a higher degree of social organization and interaction. This could be related to their lifestyle, which required both individual and collective hunting strategies. Thus, troodontids represent a unique example of possible intelligence development in reptiles, demonstrating how a relatively small brain size can be associated with high levels of intellectual behavior and social organization. Fossils of these dinosaurs found in the territories of modern Canada and the United States confirm their diversity and importance in the ecosystems of the time. Troodontids left behind numerous traces, including footprints and even fossilized eggs, providing additional insights into their reproduction and parental behavior. This underscores the fascinating aspect of reptiles as a group, which, despite their extinction, left a significant legacy in the history of life on Earth. Cephalopods, particularly octopuses, represent an extraordinary example of the evolution of intelligence in the invertebrate world. Octopuses possess a complex nervous system that significantly differs from that of most animals. They have around 500 million neurons, with a large portion concentrated in their tentacles. This allows them to not only react to their environment but also process information at a level inaccessible to many other species. For instance, octopuses can solve problems and learn from previous experiences. In laboratory conditions, they have demonstrated the ability to open cans to obtain food, indicating significant cognitive abilities. Research conducted in 2009 by scientists from Johns Hopkins University showed that octopuses can remember and reproduce sequences of actions, which is a sign of high-level cognitive processes. It is interesting that octopuses use tools which was previously thought to be a privilege of higher vertebrates. For example, the common octopus, or as it is also known, the Australian octopus, uses coconut shells and shells as shelters or protective shields, indicating its ability to plan and manipulate objects. In 2020, an article published in the journal Nature described how octopuses can change the color and texture of their skin to blend with their surroundings, which also indicates high abilities in perception and adaptation. These mollusks can operate in complex environments, which requires not only physical skills, but also the ability to analyze situations and make decisions. Some species of octopuses, such as the Caribbean octopus, have shown that they can recognize individual people, which underscores their social skills and ability to learn. In 2012, a study conducted at the University of Tennessee showed that octopuses can learn through observation, which once again confirms their high intelligence. Remarkably, octopuses can even participate in games, demonstrating their ability to interact with other octopuses and with humans. These mollusks also possess a unique ability to regenerate, allowing them to restore lost limbs, which requires them to adapt and learn from their mistakes. Regardless of how we view these extraordinary creatures, their complex nervous system, ability to learn, and use of tools make them some of the most intelligent invertebrates on the planet. Research continues, and scientists hope to uncover more secrets related to the behavior of octopuses and their cognitive abilities. For example, in 2020, a group of researchers from the University of California, San Diego, began studying how octopuses use various hunting methods, which can also help understand how they make decisions under stress. It is important to note that octopuses can also learn to avoid traps, indicating that they are capable of long-term memory and analysis of dangers. All this suggests that their intelligence may be much more complex than we previously thought. For example, octopuses can adapt to changing environmental conditions, which requires a significant level of cognitive flexibility. These mollusks are unique and continue to amaze scientists with their abilities. In 2021, an article published in the journal Science described how octopuses can interact with other species, which underscores their intellectual and social skills. Arthropods, particularly social insects, exhibit remarkable evolutionary potential that can lead to the creation of collective intelligence and complex architectural structures. Social insects like ants, bees, and termites have developed extraordinary mechanisms of interaction within their colonies. For instance, leafcutter ants of the Atta genus, known for their complex division of labor, have each individual performing specific tasks. Some collect leaves, others tend to fungi, while others protect the nest. This allows them to create extensive colonies that can reach tens of millions of individuals. In the 18th century, Swedish naturalist Carl Linnaeus described over 100 species of ants, highlighting their diversity and adaptability. In recent decades, scientists such as Dr. Edward O. Wilson have studied the social behavior of ants and concluded that the collective intelligence of these insects can be comparable to certain forms of human cognition. For example, ants can solve complex problems, use smart routes to find food, and even build infrastructure in the form of tunnels and chambers for food storage and reproduction. Termites, on the other hand, construct enormous mounds that can reach heights of up to 8 meters and have a complex internal structure with ventilation systems. These structures provide optimal living conditions for termites, including temperature and humidity control. 80% of termites can be found in such complex ecosystems, making them one of the most successful builders among arthropods. Bees, in turn, create hives that are not only architectural marvels, but also models of social interaction, where each bee plays a role in maintaining the colony. Research shows that hives can adapt to changes in the environment, indicating a high level of intelligence and communication among bees. For example, in the year 2000, scientists from the University of Saskatchewan discovered that bees can discuss and make decisions about when and where to move to find nectar, challenging traditional notions of animal intelligence. The evolution of social insects has led to the formation of collective intelligence that can make decisions at the colony level, allowing them to adapt to changes in the ecosystem and find optimal solutions for survival. Thus, social insects not only create stunning architectural structures, but also demonstrate high abilities for cooperation and information exchange, opening new horizons for the study of collective intelligence in the animal world. In this context, it is worth noting that ants can move loads several times their own weight using teamwork tactics, further highlighting their unique abilities. Arthropods serve as an example of how evolutionary processes can lead to the creation of complex social structures and architectural forms that continue to inspire scientists and researchers worldwide. For instance, biomimetics is a field of science that studies the mechanisms and structures created by nature for application in engineering and architecture. Scientists are trying to apply ideas taken from the lives of ants and termites to building and city design. In the year 2000, a group of researchers from the Massachusetts Institute of Technology presented a project inspired by termites that allowed the creation of buildings with natural climate control, significantly reducing energy consumption. These examples show how the evolutionary achievements of arthropods can be applied in modern technologies and architecture, creating new possibilities for sustainable development. Convergent evolution is a process in which different organisms living in similar environmental conditions develop similar traits, despite lacking close genetic relationships. This phenomenon is observed in various ecosystems and can manifest at the level of physical structure, behavioral characteristics, and even biochemical processes. For example, in similar ecological niches, different species may develop similar adaptations, such as body shape, that facilitates more efficient movement in water or air. This can be due to the fact that the characteristics of the surrounding environment, such as climate, food availability, or the presence of predators, dictate certain requirements for survival. Convergent evolution allows us to understand how organisms can adapt to similar conditions, even if they originated in different places and at different times. Research conducted by scientists such as Jane Goodall and Richard Dawkins shows that such adaptations can arise independently of each other, highlighting the role of the environment as the main factor in the process of natural selection. In some cases, such as with mammals and reptiles, similar hunting strategies can be observed, which allows us to understand how different organisms can arrive at similar solutions in response to the same ecological challenges. These similar traits can be not only physical but also behavioral, such as the use of tools or social structures. It is important to note that convergent evolution does not necessarily lead to the creation of identical organisms, but rather to the creation of functionally similar solutions for survival. Such a process can also be observed in adaptations to climate change, when different species develop resistance to drought or cold. This underscores that despite genetic distance, organisms can find a common language with nature and adapt to its challenges. Understanding convergent evolution is important for the study of biology and ecology, as it opens new horizons in understanding the relationships between species and their environment. Within this process, each change and adaptation serves as evidence of how life on Earth can find multiple paths for survival and prosperity. Convergent evolution also raises questions about how species are classified and what it truly means to be related in a biological sense. For example, similar traits can be the result of convergent evolution, not a common ancestor, which challenges traditional views on phylogeny and systematics. Scientific research in this area continues to deepen, and new technologies such as genome sequencing allow researchers to study the molecular basis of these adaptations. This opens new possibilities for understanding how organisms react to changes in their environment and how these changes can influence evolution in the long term. Convergent evolution demonstrates that life on Earth is not static, but constantly evolves in response to changes in the surrounding environment. This process reminds us that the diversity of life is the result of both random mutations and the harsh demands of nature, which force organisms to seek optimal paths for survival and adaptation. Each such case of evolution becomes a kind of experiment that shows how living beings can find similar solutions despite differences in origin and history. In ecology, convergent evolution can also serve as an indicator of the health of ecosystems, as it can indicate successful adaptations to changing environmental conditions. For example, in the context of climate change, the rapid development of convergent traits in various groups can serve as a signal that organisms are finding effective strategies for adapting to new realities. In this regard, the study of convergent evolution becomes an important tool for predicting future changes in biological communities. It is important to understand that convergent evolution is not just an interesting scientific fact, but a key to understanding the dynamics of life on our planet. Ultimately, it is a process that opens doors to new knowledge about how life can thrive in the most diverse conditions. Each new case studied by scientists adds to our understanding of this complex and fascinating process that shapes our biosphere. Convergent evolution of the eye in vertebrates and cephalopod mollusks is a striking example of how complex organs can develop independently in different evolutionary lineages. The eyes of vertebrates, for instance, have evolved over hundreds of millions of years. The first primitive eyes emerged in the ancestors of vertebrates around 500 million years ago. These eyes were simple, light-sensitive spots capable of distinguishing light from shadow. Over time, through evolution, eyes have become more complex structures. In open-ocean fish, eyes already possess a vitreous body and cornea, allowing them to focus light and see in low-light conditions. In contrast, the eyes of mammals, such as humans, are capable of color vision due to the presence of 3 types of cones in the retina, enabling us to distinguish millions of shades. Unlike vertebrates, the eyes of cephalopod mollusks, such as squid and octopuses, have evolved independently. These mollusks began to evolve around 500 million years ago, and their eyes share some similarities with those of vertebrates, but their structure is fundamentally different. For example, a squid's eye has a structure similar to that of a human eye, including a cornea, lens, and retina, but the arrangement of tissue layers and the mechanism of operation are entirely different. In cephalopod eyes, there is no vascular layer, and light information is processed directly in the retina, making their vision particularly acute in aquatic environments. Research conducted by scientists such as Dr. Edward W. Richter and his colleagues in the early 2000s showed that the eyes of octopuses can perceive polarized light, giving them a clear advantage in hunting and camouflage. This difference in evolutionary paths is a vivid example of how the same functions can be achieved through different means. It is important to note that despite significant differences in structure, both types of eyes provide their carriers with a high degree of adaptation to the surrounding environment. Scientists have calculated that more than 70% of all existing living organisms on the planet have some form of eyes. It is interesting that the first eyes, similar to those of cephalopods, appeared much earlier than those of vertebrates, and their correct shape had a huge impact on evolutionary changes in the marine environment. Such phenomena demonstrate how evolution can act in different ways, using limited resources to achieve the same result. For example, in crustaceans and insects, eyes have a complex structure, but their functions remain similar to those of the eyes of vertebrates and cephalopod mollusks. In this sense, convergent evolution highlights the universality of biological solutions adapted to existence in different conditions. Studies show that despite anatomical differences, the eyes of all these animal groups have evolved with the same goal: to provide effective vision. For instance, scientists from the University of Cambridge in 2020 demonstrated that the structure of the retina in octopuses and humans has similar functions despite differences in their genetic origins. Comparative analyses show that the mechanisms responsible for light perception have evolved independently but ultimately led to similar results. These facts confirm that complex organs such as eyes can evolve independently, providing different organisms with the necessary adaptations for survival in their unique ecosystems. Echolocation, as an astonishing example of convergent evolution, developed simultaneously in bats and cetaceans despite belonging to completely different classes, mammals and marine animals. Bats, belonging to the order Chiroptera, began using echolocation more than 50 million years ago, enabling them to adapt to nocturnal life. They emit ultrasonic signals that then reflect off objects in their environment, allowing them to determine distance, size, and even texture. For instance, a study conducted in 2006 by scientists from the University of California showed that some species of bats can recognize small objects, such as insects, at distances of more than 30 meters, using sound frequencies ranging from 30 to 100 kilohertz. Meanwhile, cetaceans, which include dolphins and sperm whales, developed their form of echolocation in marine environments. Sperm whales, for example, can create sound waves with frequencies around 20 kilohertz, which penetrate marine water and reflect off objects, allowing them to find food and navigate in the dark depths of the ocean. Studies conducted in 2012 in the Pacific Ocean showed that dolphins use echolocation for hunting fish by emitting sounds with frequencies up to 100 kilohertz and obtaining information about the location and size of their prey. This process also demonstrates how evolution can lead to similar adaptations when different species face similar ecological challenges. During nighttime hunting, bats and deep-sea cetaceans use similar mechanisms to achieve their goals, although their morphology and lifestyle differ significantly. Echolocation in bats and cetaceans underscores how different groups of animals can develop complex sensory systems to adapt to their ecosystems. For example, in 2015, a group of researchers from Leiden University conducted a genetic analysis that showed bats and cetaceans share genes responsible for the development of auditory systems, confirming the theory of convergent evolution. These genes enable the creation of specialized structures such as ears and sinuses, which enhance sound perception, which is critically important for echolocation. It is worth noting that such adaptations not only contribute to survival, but also shape social interactions within groups. For instance, dolphins use echolocation not only for hunting, but also for communication with each other, creating complex social structures. Bats also communicate using their sound signals, creating language patterns that help them find partners and protect their territories. Remarkably, even in such different environments as air and water, evolution leads to the development of similar solutions for ecological tasks. Echolocation, as a result of convergent evolution, demonstrates how complex sensory systems can arise under the influence of similar ecological pressures. For example, a study conducted in 2018 in the Arctic showed that changes in water temperature affect the behavior of sperm whales, forcing them to use echolocation to find food in changing conditions. This highlights that adaptations such as echolocation can be not only a result of evolution, but also a response to ecological changes. As a result, we see how two completely different classes of animals, bats and cetaceans, independently develop their ability to echolocate, which is a clear example of convergent evolution. Echolocation in bats and cetaceans became the result of millions of years of natural selection, leading to the creation of unique but similar survival strategies. Convergent evolution of intelligence in primates and corvids demonstrates how different groups of animals can independently develop high cognitive abilities. Primates, such as chimpanzees, orangutans, and gorillas, exhibit remarkable levels of mental development. For example, chimpanzees can use tools to extract termites from their mounds, while orangutans have learned to create complex structures from branches to reach food. These skills require not only physical dexterity but also developed thinking. Meanwhile, corvids such as crows, sparrows, and jays also demonstrate extraordinary problem-solving abilities. In particular, crows are among the few animals that can use tools, as shown in experiments using sticks to retrieve food from hard-to-reach places. These birds are capable of planning actions, as demonstrated in experiments where crows chose tools that would be needed later to achieve their goal. The convergent evolution of these cognitive abilities in primates and corvids occurred in different geological epochs and in different ecosystems. Primates began developing their intellectual abilities around 40 million years ago, as their evolutionary path involved adapting to various living conditions. Meanwhile, corvids, belonging to the family of sparrows, began evolving around 30 million years ago, and their high intellectual abilities are a result of adapting to complex life conditions, including the need to find food and protect themselves from predators. It is interesting that some studies have shown that the size of the brain in these animals is directly proportional to their ability to learn and solve tasks, indicating a link between brain size and cognitive functions. For example, a chimpanzee's brain size is around 400 cubic centimeters, which is significantly larger than that of most other mammals. Crows, despite their smaller size, have a brain that, in relation to their body, is comparable to that of a chimpanzee and even dolphins. This underscores that intelligence development is not always linked to absolute brain size, but rather to its structure and functions. Research shows that primates and corvid birds use different strategies for problem-solving, indicating the diversity of mental processes. For example, in one experiment, crows were able to crack nuts using stones, while chimpanzees demonstrated more complex methods, combining various tools to achieve their goal. These observations highlight that high cognitive abilities can develop in the most diverse groups of animals, regardless of their evolutionary origin. Such examples as tool use, planning future actions, and social learning underscore that intelligence manifests in various forms and is not limited to a single type. Therefore, primates and corvids are bright examples of convergent evolution of intelligence, showing how different ecological and social factors can contribute to the development of complex mental abilities in different groups of animals. It is important to note that research on these species continues, and with each passing year, scientists discover new facts about how intelligence can manifest in the animal world. For instance, a study conducted by scientists from the University of Leipzig in 2007 showed that crows can plan their actions several steps ahead, which is an indicator of high intelligence. Meanwhile, primates participating in similar experiments also demonstrated similar abilities. These facts underscore that high cognitive abilities can develop not only in mammals but also in birds, challenging traditional views on how intelligence is formed in the animal world. The concept of technological singularity refers to a point in time when technological progress reaches such a rapid pace that further development becomes impossible for humans to understand and predict. This phenomenon is based on the assumption that technological progress is not merely linear, but exponential. In this model, the speed of change increases much like a snowball that grows with each new layer of snow. For instance, Today, we observe how new ideas and solutions emerge at such a frequency that their integration into everyday life happens faster than ever before. This effect can be explained by several factors. One of them is the accessibility of information, which is now available to everyone through the Internet. This allows people worldwide to exchange knowledge and ideas, significantly accelerating the innovation process. As a result, innovations that once required decades to implement can now be developed and deployed in just a few months or even weeks. Additionally, there is the quality of knowledge effect, where new discoveries or developments render previous technologies obsolete within just a few years. While at the beginning of the 20th century, technologies could exist for decades without significant changes, in the 21st century, this period has significantly shortened. For example, software that was once considered advanced can become outdated in just a few years. This acceleration also necessitates the adaptation of people and organizations to new conditions, which in turn requires new skills and approaches. In this context, we not only see the rapid growth of new technologies, but also the emergence of new professions that did not exist 10 years ago. The diversity of new fields of activity and specialties creates enormous opportunities for career growth, but also increases the pressure on workers who must constantly learn and adapt to new realities. This leads to a constant race for knowledge in which those who cannot keep up may be left behind. A society where everyone strives to be one step ahead becomes more competitive, but also more tense. In this context, it is clear how changes in one technological area can have cascading effects in other spheres of life. For example, advancements in biology can impact medicine, and changes in energy can lead to new approaches to ecology and sustainable development. People who were previously unaware of the connections between these areas now have to consider the consequences of changes in one area for others. The rapid pace of development also leads to changes in social structure. There are concerns that the gap in access to new technologies may widen, creating a divide between those who have access and knowledge and those who are left behind. This can generate new social tensions and conflicts, which could become a serious problem in the future. It is important to understand that in this race for technologies, new opportunities arise, but so do new challenges. The accelerating development of civilization makes traditional methods of management and decision-making less effective. Institutions that once ensured stability and order may struggle to cope with new challenges as they operate on outdated models. This situation requires new approaches to management and interaction based on flexibility and the ability to quickly respond to changes. For example, organizations that quickly adapt to new conditions and use innovative methods may find themselves in a more advantageous position than those that stick to traditional approaches. This underscores the need for new thinking and approaches that could lead to a qualitatively new stage in the development of society. Interestingly, many contemporary researchers and analysts note that we are on the threshold of a new era in human history, where the boundaries between the real and virtual worlds begin to blur. In this context, it is important to consider not only technological aspects, but also social, cultural, and economic changes that occur in the face of this rapid progress. With each new stage of technological development, new opportunities and challenges arise, requiring us not only to adapt, but also to foresee the consequences. It is important to remember that each new discovery or technology can be both a blessing and a source of problems, depending on how we learn to work with them. These processes are already underway and continue to develop, highlighting the complexity and multifaceted nature of the modern world. Technological singularity opens up new horizons for humanity, which require careful study and analysis. Initial stone tools, such as choppers, appeared around 2.5 million years ago. These simple tools, created by primitive humans, were used for food processing and hunting. Around 200,000 years ago, Homo sapiens began using more complex tools, such as sharp-tipped spearheads, which became crucial for their survival. Approximately 15,000 years ago, during the Paleolithic era, people started creating bows and arrows, which gave them a significant advantage in hunting. The transition to the Neolithic period, which began around 10,000 years ago, was marked by the development of agriculture. People began to live settled lives, leading to the formation of the first settlements and ultimately the emergence of cities. In Mesopotamia, around 3,000 years BCE, the Sumerians invented cuneiform writing, which became the basis for written history. Initially, they recorded economic transactions, but soon began to document myths and laws. In ancient Egypt, around 3,000 years before Common Era, pyramids such as the Great Pyramid of Giza were built, with a height of 146 meters. These giant structures required the use of advanced technologies, such as inclined ramps, to move heavy stone blocks. The introduction of the Bronze Age, starting around 3,000 years before Common Era, made it possible to create more durable tools and weapons, which influenced warfare and territorial expansion. In the 6th century BCE in China, gunpowder was invented, which later changed the course of military conflicts worldwide. During the Middle Ages, starting from the 11th century, there was a significant leap in shipbuilding technology, allowing European states to engage in active maritime exploration. In the 15th century, with the invention of the printing press by Johannes Gutenberg, information became accessible to the general public, contributing to the spread of knowledge and the beginning of the Renaissance. In the 18th century, the Industrial Revolution occurred. Inventions such as the steam engine, invented by James Watt in 1769, made mass production possible. In the 19th century, with the development of the telegraph and telephone, communication between people became instantaneous. Electricity, discovered in the 19th century, fundamentally changed daily life, and in 1886, Thomas Edison created the first electric light bulb, marking the beginning of a new era. In the 20th century, following World War II, the era of computers began. In 1943, ENIAC, one of the first electronic computers, was developed, occupying an entire room and having computing power comparable to modern calculators. In 1968, Neil Armstrong became the first person to step on the moon, marking the culmination of the space race between the US and the USSR. Over the past few decades, technology has developed exponentially, thanks to the Internet and mobile devices. In the 21st century, the number of Internet users exceeded 4 billion, and computing power increased by millions of times compared to the first computers. Such exponential growth could also occur in other intelligent species if they had similar conditions, such as access to resources, the ability to exchange knowledge, and cultural interaction. Facts that many species, such as dolphins and sparrows, demonstrate competition for resources and use tools, confirm that the development of technology can be a universal process. The concept of the technological horizon offers an intriguing approach to studying civilizations and their evolution. It posits that there is a certain boundary beyond which a civilization becomes invisible to external observers. This can occur due to several reasons. The civilization either transforms or self-destructs. A striking example is the Maya civilization, which reached its technological peak in the 7th century AD, building magnificent cities with multi-level temples and developing a complex writing system. However, by the 12th century, these cities were abandoned and people left their lands. The causes included not only ecological changes, such as resource depletion and drought, but also internal conflicts. As a result, the Maya lost their achievements and became invisible to the outside world, although their descendants still exist and preserve cultural traditions. In the history of ancient Rome, another aspect of this concept can be seen. The Roman Empire, which reached its technological and cultural zenith in the 1st century AD, faced internal crises such as political corruption, economic difficulties, and barbarian invasions. By the end of the 5th century, the empire had collapsed, and many of its achievements were forgotten or became inaccessible to posterity. It is important to note that disappearance does not always mean complete self-destruction. For example, The Inca civilization in Peru, which reached its peak in the 15th century, was destroyed by Spanish conquistadors in the 16th century, but its legacy persists in the culture and language of modern Peruvians. The technological horizon can also be seen as a point of transition to a new stage of development. For instance, the Industrial Revolution in the 19th century not only changed technologies but also social structures, creating new classes and altering production methods. There are theories that suggest each civilization goes through a cycle of rise and decline, and this cycle can be explained by the concept of the technological horizon. Civilizations can reach high levels of technology and knowledge but ignore sustainable development, ultimately leading to their downfall. A vivid example is the Harappan civilization in India, which existed in the 3rd millennium BC. These people built complex cities with a well-thought-out water supply and drainage system, but their civilization disappeared, likely due to climate change and resource depletion. As a result, the remaining artifacts and city ruins became a ghost of a great culture. The question of how civilizations reach this horizon remains open for discussion. Research shows that both internal factors, such as social and political conflicts, and external ones, such as invasions and ecological changes, play a key role. Modern civilizations also face similar threats, such as climate change and globalization, which raise concerns about their resilience. As the world continues to develop, we can observe how new technologies affect society, and the question arises, can we avoid the fate of those who could not cross their technological horizon? Analyzing the situation, it is clear that many modern societies are already at the edge of their horizon, and the choice between transformation and self-destruction becomes increasingly relevant. The technological horizon remains a significant concept for understanding the dynamics of civilizations and their vulnerabilities, providing a foundation for further research and discussions. For example, according to research conducted by Professor Jared Diamond in his book Guns, Germs and Steel, it is geographical and ecological factors that determine the fate of civilizations, and he mentions how the uneven distribution of resources can lead to conflicts and decline. Therefore, the concept of the technological horizon remains relevant for analyzing both historical and modern civilizations, raising questions about their future and their ability to survive in a rapidly changing world. Archaeological visibility is a key concept that determines how various materials and technologies become accessible for research and interpretation in the context of archaeological excavations. This visibility can depend on a multitude of factors, including preservation conditions, excavation methods, and the theoretical approaches used by archaeologists. For example, depending on the climate, some materials may be preserved significantly better than others. In humid climates, organic materials such as wood or textiles can decompose quickly, whereas in dry or frozen conditions they can be preserved for centuries. This often leads to archaeologists encountering incomplete or distorted data about past civilizations, which complicates the understanding of their culture and technologies. Excavation methods also play a crucial role in archaeological visibility. For instance, the use of modern technologies like ground-penetrating radar or magnetic surveying allows archaeologists to detect hidden structures that are not visible to the naked eye. These technologies can reveal the outlines of buildings, burial grounds, or other objects that have been buried for centuries. It is important to note that the choice of research methods depends not only on available technologies, but also on the theoretical foundations that determine what archaeologists consider significant for study. For example, some archaeologists may focus on material culture, while others may be more interested in social structures or ritual practices, which influences the choice of objects to study. Understanding archaeological visibility also requires considering the context in which artifacts were found. For instance, artifacts found in an urban environment may have a completely different meaning than similar artifacts found in a rural area. In cities, where life was more intense, remnants of various technologies and materials can indicate complex trade relationships and social connections. In contrast, in rural areas, there may be a greater number of objects related to everyday life and production processes, providing opportunities to study more simple but no less important aspects of human life. It is also worth mentioning that archaeological visibility can change over time. Technologies and materials that were widespread in one era may disappear or change in the next. For example, in some cultures, the use of certain technologies may cease due to changes in climate, population migration, or social changes, leaving gaps in historical records. This dynamism requires archaeologists to constantly re-evaluate their methods and approaches to the interpretation of artifacts to avoid missing important aspects of cultural heritage. It is important to understand that archaeological visibility is not just a matter of material, but a complex of factors that influence how we perceive and interpret the past. Each object, each artifact, each excavation site contributes to the overall picture, but only if we are aware of the limitations and possibilities that archaeology provides. The historical data we can extract from excavations depends on many factors, including the choice of research methods and preservation conditions, which in turn influences our understanding of how societies developed and what technologies were used. Ultimately, archaeological visibility shapes our understanding of human history, and this understanding must be flexible and open to new discoveries. For example, even small finds can fundamentally alter our understanding of technological progress or social structures of a particular era. Therefore, archaeological visibility remains an important tool in the hands of researchers, allowing them not only to collect data, but also to build hypotheses about how people lived in the past. Stone is one of the oldest and most durable building materials used by civilizations over thousands of years. Ancient Egyptians, for instance, built their pyramids from limestone and granite, utilizing stone that endured for centuries due to its unique physical and chemical properties. However, the longevity of stone is not universal. It greatly depends on geological conditions. For example, in high humidity and acidic rain conditions, certain rock types can deteriorate much faster than in dry and stable climates. Thus, marble temples in ancient Athens, constructed in the 5th century BC, suffered significant damage due to acidic rain and air pollution from industrial activities in the 20th century. Meanwhile, Egyptian pyramids, due to their location and climate, have remained in much better condition. The preservation of stone structures also depends on the construction methods used. For example, in Mesopotamia, ziggurats were built from fired clay bricks, which, despite appearing like stone, were much less resistant to climatic conditions. These structures typically lasted only a few hundred years. In contrast, some ancient stone structures, such as Stonehenge in the UK, have endured due to being built with local geological conditions in mind and using dense, strong rock types. This suggests that the choice of material and construction techniques played a crucial role in durability. However, even these robust structures are not immune to destruction. Natural disasters, such as earthquakes, can completely destroy stone buildings, as happened with the ancient city of Pompeii in the 1st century AD, which was buried under a layer of volcanic ash. On the other hand, many stone structures can disappear over tens of thousands of years due to erosion. For example, some ancient rock art in Australia, dating back around 30,000 years, is gradually eroding away due to wind and rain. Additionally, human intervention, including stone quarrying and the construction of modern buildings, also negatively impacts the preservation of ancient stone structures. For instance, in Iraq, many ancient temples have been destroyed or looted due to military conflicts and lack of protection. It is important to remember that even the strongest stone structures require care and protection. There are successful examples of restoration, such as the reconstruction of the ancient Greek theatre of Epidaurus, where every detail was recreated with maximum precision. However, such projects require significant resources and time. Ultimately, the longevity of stone as a building material is not just about choosing the right material, but also understanding geological conditions and considering time and the environment. Stone structures can last millions of years, but only under ideal conditions. Otherwise, even the greatest achievements of ancient civilizations can be erased from the face of the earth. For example, due to climate change and natural disasters, some stone monuments that were once considered eternal can disappear within a few centuries. Metals, despite their strength and durability in human life conditions, behave differently on geological timescales. For instance, iron, as practice shows, begins to corrode almost immediately after contact with moisture and oxygen. Research indicates that iron corrosion occurs at the atomic level, and in unfavorable conditions it can transform into rust within a few decades. This oxidation is due to iron's reaction with oxygen in air or water, leading to the formation of iron oxides such as hematite and magnetite. Even in structures built just a few centuries ago, significant damage to iron constructions can be observed. For example, the Statue of Liberty, completed in 1880, began to show signs of corrosion by the early 20th century, requiring regular maintenance and restoration. Copper alloys, such as bronze, are not exempt from this. Bronze, composed of copper and tin, is subject to a phenomenon known as green disease, corrosion caused by the reaction of copper with oxygen and moisture, resulting in a green patina. This can be seen on monuments like Michelangelo's David, where lower layers of copper have been destroyed over time. On geological timescales, measured in millions of years, even the most durable alloys, such as stainless steel, cannot resist oxidation and corrosion. Stainless steel, created with chromium to prevent rust, also deteriorates over millions of years as chromium oxidizes and the alloy's structure loses its strength. In architectural landmarks such as the Brooklyn Bridge, completed in 1883, it is evident that even modern materials designed for longevity require significant repair after just 150 years due to corrosion. It is worth noting that some metals, such as gold and platinum, are more resistant to corrosion due to their inertness, but even they can be destroyed under the influence of strong chemical substances. Therefore, in scientific circles, there is active research into methods of protecting metals from corrosion using various coatings and anti-corrosion additives to extend the lifespan of materials. However, even the best protection technologies cannot guarantee the preservation of metals over millions of years. Geological processes such as erosion, cementation, and metamorphism continue to act, destroying even the strongest metal alloys. Thus, on the example of various metals and their everyday use, it is evident that despite human achievements in metallurgy, time remains on nature's side, destroying everything created by humans. Research has shown that in oceanic conditions, where pressure and temperature constantly change, unique corrosion processes can occur, accelerating the destruction of metals. For example, in the 1930s, scientists discovered that underwater pipelines made of steel corrode 30 times faster than on the surface due to the influence of salt water and microbial activity. Organic materials such as wood, fabrics, and paper pose a significant challenge for archaeologists and historians, as they decompose within a few years or even decades, leaving behind only tiny fragments, if anything at all. For instance, in a humid climate where temperature fluctuations and high humidity accelerate decomposition, such materials can disappear within 2 to 3 decades. Meanwhile, stone artifacts can endure for millennia, but organic materials are vulnerable to the effects of microorganisms, insects, and other environmental factors. In the 1930s, archaeological excavations in Norway uncovered remnants of a Viking ship estimated to be around 1,000 years old. However, the wooden elements that formed the ship's structure began to decompose, necessitating complex conservation efforts to preserve at least part of the structure. Similarly, in Egypt, where a dry climate preserves many artifacts, fabrics and papers found in tombs often deteriorate due to microbial and mold activity, despite the apparent protection. On average, paper documents from the early 20th century can only last 30 to 50 years without proper storage conditions, as the cellulose they are made of begins to decompose especially when exposed to light and moisture. In the 2000s, Italian archaeologists discovered medieval fabrics in a church, but most were so damaged that they could not be studied. A crucial aspect is that many of these materials do not leave traces that could aid in the study of past cultures and lifestyles. For example, during excavations of the ancient city of Hanyangchou in China, textile remnants were found, but due to decomposition, they provided no useful information about the period, except for a general understanding of weaving techniques. Scientific research indicates that processes such as oxidation or biological decomposition can completely destroy such materials within a few decades. In particular, in tropical regions where temperature and humidity accelerate decomposition, organic remains are lost more quickly than in temperate zones. Additionally, factors such as soil acidity and the presence of certain microorganisms can significantly speed up the decomposition process, leading to the loss of unique artifacts. For instance, in the 21st century, archaeologists in Costa Rica found remnants of old fabrics, but their condition was so poor that the only way to preserve them was to use modern technologies like freezing and conservation in inert environments. According to experts, under normal storage conditions without special climate control and protection, such fabrics could disappear entirely within 20 years. Therefore, the issue of preserving organic materials remains one of the most pressing in archaeology, as each new discovery could be the last, if not protected. Facts show that currently scientists are still searching for effective methods of conserving organic materials, but unfortunately many artifacts have been irretrievably lost. The technological signature of civilization is a concept that describes the unique traces and artifacts left by societies as they develop, showcasing their distinctive features and levels of skill. Each historical period and culture creates its own signature technologies that reflect their social structures, needs, and worldviews. These can include tools, buildings, means of transportation, and even ways of interacting with the environment. These artifacts serve not only as evidence of technological progress, but also as indicators of cultural identity. Viewing the technological signature through the lens of time reveals that these traces change and adapt in response to new challenges and circumstances. Importantly, each civilization leaves its unique mark, which can be recognized by archaeologists over thousands of years. Even without written sources, the shape of pottery or architectural styles can tell us about many aspects of people's lives, from their economic practices to their socio-cultural interactions. The technological signature also implies that different societies can independently develop similar technologies, leading to the emergence of similarities and cultural ties between regions. Throughout history, we can see how various civilizations located on different continents created similar solutions to the same problems, highlighting the universality of human experience. For example, in conditions of resource scarcity, societies could develop similar methods of food storage or housing construction. These parallels underscore that despite differences in language and culture, humanity shares a common path in its technological development. It is crucial to note that the technological signature is not static. It can change depending on political, economic, and ecological conditions. For instance, after major catastrophes or wars, societies may reevaluate their technological approaches, reflecting the need to adapt to new realities. Moreover, some technologies become symbols of entire eras, such as the steam engine, which is associated with the Industrial Revolution of the 19th century, or the Internet, which has transformed our perception of information and communication in the 21st century. These technological achievements not only facilitate life, but also shape social relations, habits, and even human thought. The technological signature of civilization can be studied through the lens of archaeological findings, which in turn require deep analysis and interpretation. Specialists such as archaeologists and historians use various methods to determine the age and purpose of artifacts, allowing them to reconstruct the picture of ancient societies' lives. For example, radiocarbon dating helps establish the temporal framework of certain objects' existence, while stylistic studies of pottery can indicate cultural connections between civilizations. In this context, the technological signature becomes a valuable tool for understanding not only the technologies themselves, but also how they influence social structures and cultural practices. This mathematically grounded approach helps researchers not only identify artifacts, but also draw conclusions about the social, political, and cultural context of their existence. For instance, the discovery of complex tools of labor can indicate a high level of organization and interaction in ancient communities, while simple tools may point to more primitive forms of life. Ultimately, the technological signature of civilization is not just a collection of objects. It is a whole world that tells us about humanity, its development, and interaction with the environment. It opens a window into the past, allowing us to see how technologies shaped everyday life and were integrated into cultural and social processes. This enables us not only to study history, but also to better understand how technologies continue to influence our society today. We can trace how the same problems were solved differently in various parts of the world, vividly demonstrating the diversity of human experience. The technological signature of civilization is a mirror reflecting the achievements, shortcomings, and evolution of humanity. For example, during the Neolithic period, when humanity began transitioning from gathering to agriculture, the appearance of the first tools for land cultivation became a pivotal moment, transforming the structure of society. Radioactive isotopes such as carbon-14, uranium-238, and plutonium-240 play a crucial role as long-term markers of technological activity, persisting in geological layers for millions and even billions of years. Carbon-14 is formed in the atmosphere when cosmic rays interact with carbon atoms, and it can be detected in organic materials like wood or bone, allowing scientists to date artifacts up to 58,000 years old. For instance, in the year 2000 in Egypt, carbon-14 was used to date the remains of wood in ancient pharaohs' tombs, confirming the age of the pyramids. Uranium-238, found in the Earth's crust, has a half-life of 4,500,000,000 years and can serve as an indicator of long-term human impact on the environment. It is often found in mines, where it was used for nuclear fuel production, and its traces can remain in soil for millions of years after the mines are closed. Plutonium-240, with a half-life of 6,400 years, is produced through nuclear reactions and can be detected in places where nuclear tests were conducted, such as on Bikini Atoll, where tests took place from 1946 to 1948. These isotopes not only serve as indicators of technological activity, but also help determine the impact of human activity on ecosystems, as their presence indicates the presence of anthropogenic processes. For example, in 1986, following the Chernobyl nuclear disaster, traces of various radioactive isotopes, including cesium-13-7 and iodine-13, were found in the soil, and they remain in the ecosystem to this day. These isotopes are used to study climate change and its impact on geological processes, as their concentration and distribution can provide information about how humanity has interacted with nature. In particular, isotope research allows for the assessment of pollution levels and their dynamics, which is important for evaluating the long-term consequences of anthropogenic activity. Studies conducted in 2003 on the territory of the former USSR revealed that the level of plutonium-240 in the soil on territories affected by nuclear tests remained significantly higher than background values even decades later. These data allow scientists not only to track the consequences of nuclear activity, but also to warn about potential ecological disasters. In 2020, researchers from the University of California conducted an analysis of deposits in a lake where radioactive isotopes were found, allowing for the reconstruction of climatic conditions over the last 8,000 years. This demonstrates how radioactive isotopes can serve not only as markers of technological activity, but also as important tools for understanding historical changes in the environment. For example, in 2006, samples of ice from Greenland were found to contain traces of radioactive isotopes, indicating increases in temperature during certain historical periods. These findings underscore the importance of radioactive isotopes as long-term markers that can persist in geological layers and serve as irrefutable evidence of human activity over centuries. Synthetic materials and polymers represent a unique technological heritage of civilization, which, according to many scientists, could become a long-term testament to our time. For example, polymers such as polyethylene and polypropylene were developed in the mid-20th century and are the most widespread plastics in the world. Polyethylene was first synthesized in 1930 by British chemist Frederick Reynolds, and its mass production began after World War II. These materials have high resistance to decomposition, making them potential long-term geological layers. Research shows that polyethylene can persist in the environment for up to 200 years, while some types of polymers can remain unchanged for thousands of years. Scientists from the University of California, San Diego, have found that polymers can form unique geological layers that will be distinguishable to future geologists. During their decomposition, they form microparticles that can be incorporated into sedimentary rocks, thus serving as a kind of archaeological marker. In this context, it is worth noting that samples of polymers dating back to the early 2000s were found during excavations in Greenland. These findings confirm that synthetic materials can create a geological record. It is also important to mention that in the 1990s, scientists began actively researching the impact of plastic waste on the environment, which led to the discovery of new types of microplastics that are already found in oceans today. Microplastics, which are typically smaller than 5 millimeters, are formed from the decomposition of larger plastic items. They enter the food chain, causing serious ecological problems, but can also serve as an indicator of human activity in geological layers. For example, in 1987, a group of researchers led by Professor Daniel N. Levin found that microplastics can persist in marine sediments for thousands of years. This discovery highlights the possibility that future researchers will be able to identify traces of our civilization through these materials. Synthetic polymers also exhibit diversity. They can be thermoplastics, which melt when heated, or thermosets, which harden when heated. For example, epoxy resins used in construction and automobile manufacturing can persist in geological layers due to their high strength and resistance to decomposition. Research shows that epoxy resins can persist in nature for up to 500 years, making them potential long-term residents in geological records. In 1930, German chemist Hans Fischer developed a method for polymer synthesis, marking the beginning of a new era in materials science. This discovery led to the creation of numerous plastic products, from packaging to automotive parts. The use of synthetic materials in production significantly increased in the 1970s with the advent of mass consumer culture and disposable items. This resulted in a significant amount of plastic waste that is now forming unique layers in sedimentary rocks. For example, in 1981, researchers found that sedimentary layers near the coast of Japan contain plastic particles that could be dated to the beginning of active plastic consumption. As a result, synthetic materials and polymers are not only a problem for the environment, but also an important element in understanding our civilization in the future. Researchers such as Dr. Tatiana N. Romanova from the Institute of Geology in St. Petersburg assert that in the future, layers containing polymers will serve as markers for determining the epoch of human activity. In this context, it is worth noting that synthetic materials can be used to study climate changes, as their distribution in geological layers can indicate the level of environmental pollution. Thus, synthetic materials not only pose problems, but also open new horizons for studying our history and its consequences for the planet. In the 2000s, scientists discovered that microplastics can be found even in deep-sea ecosystems, highlighting their widespread presence and durability in nature. Scientific research indicates that large-scale landscape and ecosystem changes can serve as indicators of the existence of ancient civilizations. One of the most striking examples is the impact of the Maya civilization on the ecosystem of Central America. During the period from the 8th to the 10th century AD, the Maya cleared vast tracts of tropical forests for agriculture, leading to changes in local climate and a decrease in biodiversity. This is confirmed by the analysis of pollen and carbon traces found in the sedimentary layers of lakes, such as Lake Petén Itzá. The data show that as a result of agricultural practices, the level of carbon in the atmosphere significantly increased. In India, in the Indus Valley region, archaeologists discovered traces of ancient irrigation systems that altered the landscape of the area. These systems, created around 3,000 years ago, allowed for the development of agriculture on previously barren lands, as evidenced by the discovery of clay pipes and canals up to 500 meters long. In Egypt, the construction of the Aswan Dam in ancient times also changed the ecosystem of the region. The dam allowed for the control of water levels, which contributed to the increase in the area of irrigated lands, but led to changes in the migration routes of fish and other aquatic species. In Mesopotamia, the flatlands dug out for the creation of canals changed the natural course of rivers, which in turn affected the flora and fauna. This region, known as the Cradle of Civilization, was home to the Sumerians, who created the first known city, Ur, in the 3rd millennium BC. Here, traces of mass agriculture were found, confirmed by the discovery of seeds and plant remains that show the Sumerians used various methods of land cultivation. In China, in the Yellow River, Huanghe region, traces of ancient terraces for agriculture were discovered, dating back to approximately the 2nd millennium BC. These terraces not only changed the landscape but also the way of life of the local population, increasing the productivity of agriculture. In Northern Europe, archaeological excavations show that the Vikings altered the ecosystems of Iceland and Greenland by clearing forests for construction and grazing livestock. This led to soil erosion and a decrease in biodiversity, confirmed by the analysis of ice layers. In the Andes, the Inca civilization built terraces that not only helped preserve the soil, but also changed the local ecosystem, as seen by the plant remains found in archaeological layers. These terraces, stretching for thousands of kilometers, changed the way of farming in the region, allowing the Incas to effectively use the mountain slopes. Archaeological findings in Mesoamerica show that the Aztecs created complex irrigation systems that altered the water levels in rivers, thereby influencing local ecosystems. In some places, the changes were so significant that they even led to the disappearance of certain plant and animal species. Furthermore, landscape changes can be recorded in geological records through the analysis of soil samples and fossils. For example, in the area of the ancient city of Petra in Jordan, researchers found that changes in the distribution of rainfall and temperature coincide with periods when the population actively used water resources. Such changes in ecosystems and landscapes have left traces in the geological record, which can be studied using modern methods such as paleoclimatology and isotope analysis. These methods allow researchers to investigate how human activity has influenced the environment, altering natural processes and ecosystems. Scientific skepticism is a crucial approach that involves a critical attitude towards unusual hypotheses and theories. This method does not mean blindly rejecting new ideas, but rather requires researchers and the general public to exercise caution and analyze claims that are not sufficiently supported by evidence. Scientific skepticism helps to distinguish facts from myths, relying on available data and logic. For instance, when someone claims to have found traces of extraterrestrial life or evidence of paranormal phenomena, scientific skepticism demands that these claims be verified through the search for reliable evidence. For example, in the mid-20th century, when mass reports of UFO sightings began, the scientific community approached these claims with caution. Investigations at the time showed that many cases could be explained by natural phenomena or human errors. Scientific skepticism also requires that all hypotheses be subjected to rigorous testing for reproducibility and consistency. This means that any new idea must be tested and confirmed by other scientists before it is accepted by the scientific community. For example, in biology, when scientists present new theories about evolution, they must provide convincing evidence that supports their hypotheses, such as genetic data or fossils. An example of this is the discovery of DNA, which in the mid-20th century became the basis for numerous new studies in genetics and evolution. Scientific skepticism also involves critically evaluating the sources of information and their reliability. In the era of the Internet, where information is available in vast quantities, the ability to distinguish facts from misinformation becomes particularly important. For instance, many people believe in conspiracy theories that lack a basis, and it is scientific skepticism that can help dispel these myths by providing facts and logical explanations. This approach teaches us to analyze information by asking questions such as, who is making this claim? Logically, what data is this based on? Logically, and are there alternative explanations? This helps us avoid the trap of groupthink, where people accept widely accepted ideas without proper verification. Scientific skepticism also plays a significant role in scientific education, fostering critical thinking in students and encouraging them to ask questions and seek evidence. It is important for students to understand that the scientific process is not just a collection of facts, but a dynamic process that requires constant review and refinement of our knowledge. The development of scientific skepticism as a tool for analyzing unusual hypotheses is confirmed by the history of science, where many discoveries became possible precisely due to doubt and critical analysis. For example, in the 16th century, Nicholas Copernicus proposed the heliocentric model of the solar system, which challenged the then-accepted geocentric model that had been in place for over 1,000 years. This model was initially met with skepticism and criticism, but over time it was confirmed by observations and experiments. Scientific skepticism helps to avoid erroneous conclusions and guides researchers towards a path based on facts and data, rather than emotions or biases. This approach applies not only to natural sciences but also to social sciences, encouraging the study of not only the results, but also the processes that lead to them. Such analysis can reveal hidden mechanisms that would otherwise remain unnoticed. For example, research in psychology shows how biases and distortions can influence the perception of data and decision-making. This underscores the necessity of scientific skepticism in any field where human factors can distort reality. Scientific skepticism does not contradict openness to new ideas. On the contrary, it promotes a deeper understanding and verification of them. For instance, when scientists study new materials or technologies, they must be prepared for the possibility that their initial hypotheses may be incorrect and require revision. This means that scientific skepticism is not a dogma but a method that continually develops and adapts to new data and discoveries. It helps to avoid both excessive optimism about new ideas and unwarranted skepticism, guiding researchers towards more well-founded conclusions. Scientific skepticism is not just an approach, it is a necessary instrument for evaluating and testing unusual hypotheses, requiring constant analysis and critical thinking. This process does not end at the stage of verification, but continues throughout the entire scientific activity, encouraging us to constantly seek new knowledge and understanding. Scientific skepticism allows us to see the world more clearly, distinguishing facts from fiction and creating a foundation for further research and discoveries. The principle of Occam's razor was formulated by the English Franciscan monk and philosopher William of Ockham in the 14th century. It states that among several possible explanations, the one requiring the fewest assumptions should be chosen. This principle has become the foundation of the scientific method and is used in many fields including philosophy, science, and even healthcare. For example, in biology, when scientists study the evolution of various species, they may use Occam's razor to choose between several hypotheses about the origin of a specific species. If one hypothesis involves complex mechanisms and interactions, while another explains the observed data more simply, the simpler hypothesis is preferred. An example is the study of human evolution, where scientists analyze how various factors, such as climate changes, influence the development of the ancestors of Homo sapiens. There are different hypotheses about how migration and adaptation occurred, but theories based on simple explanations, such as changes in diet or the use of tools, often receive more support. In medicine, Occam's razor also finds application. For instance, when diagnosing diseases, doctors may encounter multiple symptoms in a patient. Applying this principle, they can focus on the most likely cause rather than assuming multiple simultaneous diseases. If a patient complains of a headache and fatigue, the doctor may first check for a cold or flu, rather than immediately considering more rare and serious illnesses. This helps avoid unnecessary tests and treatments that could be harmful or costly. In the history of science, Occam's razor played a key role in the development of natural sciences. For example, in the 16th century, Nicholas Copernicus proposed the heliocentric model of the solar system, which, according to many, was much simpler and more logical than the geocentric model of Ptolemy, which required numerous complex adjustments. This simplicity allowed scientists to develop astronomy more effectively, including the work of astronomers such as Johannes Kepler and Galileo Galilei. In philosophy, the principle of Occam's razor is also actively used. One notable example is the debates about the nature of God, where different philosophers proposed various concepts. In such cases, according to Occam's razor, the simplest concept that does not require additional complex explanations is preferred. For instance, if one philosophical system requires many entities to explain the existence of the world, while another explains it with a single entity, the latter appears more convincing. The principle of Occam's razor does not always lead to correct conclusions, but it serves as a useful tool for critical thinking. For example, in psychology, when researchers try to understand human behavior, they may use this principle to eliminate less probable explanations. If a person exhibits aggression, the cause could be personal issues or external factors such as work stress. Applying Occam's razor, researchers can first consider simpler and more obvious factors before delving into complex psychological analyses. In economics, this principle also has its applications. For instance, when analyzing the causes of an economic crisis, economists may use Occam's razor to focus on primary factors such as unemployment or inflation, rather than numerous less significant variables. This allows for more accurate predictions of economic changes. In social sciences, Occam's razor helps researchers avoid unnecessary complexities in their theories about social interactions and structures. For example, when studying the causes of crime, researchers may encounter many factors such as poverty, education, and environment. Applying the principle of Occam's razor, they can focus on the most influential factors before considering less significant ones. This approach is also useful in journalism, where simplicity in explanations can improve understanding of complex events. For example, when covering a political crisis, journalists may use Occam's razor to focus on the main causes of the conflict, rather than numerous accompanying factors. This helps the audience better understand the issue. The principle of Occam's razor remains relevant in the modern world, where complex systems and interactions are the norm. For instance, in the field of technology, when developing new algorithms or software, developers strive to create the simplest and most effective solutions. This helps avoid unnecessary time and resource expenditures on complex systems that may not always function as intended. This principle also reflects in the philosophy of science, where scientists discuss the importance of simplicity in theoretical explanations. Occam's razor becomes an important criterion for evaluating scientific theories and models, especially in fields such as physics and biology. For example, simpler theories like Einstein's theory of relativity were widely accepted due to their simplicity and explanatory power. Ultimately, the principle of Occam's razor remains a valuable tool for scientists, researchers, and practitioners in various fields, allowing them to focus on the most probable causes and explanations, avoiding unnecessary complexity. The hypothesis of the existence of ancient prehistoric civilizations requires extraordinary evidence because such assertions lie on the border of scientific skepticism and demand particular rigor in verification. In the history of science, the principle that extraordinary claims require extraordinary evidence was clearly formulated by the English philosopher Karl Popper in the mid-20th century. He argued that for theories to be accepted by the scientific community, they must be falsifiable. For example, if someone claims that in prehistoric times there existed a highly developed civilization capable of constructing megalithic structures like Stonehenge, it is necessary to provide convincing evidence such as artifacts, inscriptions, or other material evidence that could confirm this theory. One of the most famous examples is the civilization of Mesopotamia, where archaeologists, starting from the 19th century, discovered numerous written sources and artifacts confirming the existence of Sumerians, Akkadians, and other peoples. In contrast, assertions about the existence of highly developed civilizations in other parts of the world, such as Antarctica or the bottom of the ocean, require more substantial evidence, since there are no clear and specific finds that could confirm such theories. There are many myths and legends about lost civilizations, such as Atlantis described by Plato, but so far archaeologists have not found any convincing evidence of its existence. In the 20th century, research on ancient texts and myths continued, but the lack of archaeological finds makes assertions about such civilizations unlikely. For example, in the early 2000s, when excavations were conducted on the territory of modern Egypt, scientists found remains that indicate that the civilization of ancient Egypt developed over thousands of years from the beginning of the 4th millennium BC, which is also confirmed by the finds of tombs and temples, such as the temple in Karnak. It is important to understand that for the acceptance of the hypothesis of the existence of ancient civilizations, it is not enough to collect artifacts, but to present comprehensive data that connect them with specific cultural and historical contexts. In this regard, for example, the finds in Machu Picchu in Peru provide extensive data on the Inca civilization, including architecture, agricultural methods, and social organization, which makes assertions about it more substantiated. In contrast, any hypotheses about civilizations that supposedly existed before the beginning of our era in countries where there are no archaeological evidence cause many questions and require additional research. Scientific methods, such as radiocarbon dating, allow for the precise determination of the age of finds, which is also an important aspect in evaluating the antiquity of civilizations. While some researchers, such as Graham Hancock, propose hypotheses about highly developed civilizations that existed before known history, the scientific community requires more serious evidence than simple speculations and interpretations of ancient texts. Ultimately, any assertions about such civilizations must be supported by specific finds, not just conjectures. Without such substantiation, hypotheses about ancient prehistoric civilizations remain at the level of scientific fiction. An example of a scientific approach is the work of archaeologists in Sicily, where traces of ancient Greek settlers were found, confirming their presence and cultural influences on the island. Research conducted in places like Crete shows that the Minoan civilization existed from the 3rd millennium BC and left a significant legacy in the form of architecture and art. Research similar to these is the basis for assertions about the existence of highly developed civilizations in the history of humanity. Modern scientific methods have immense potential for tracing the remnants of ancient civilizations, opening new horizons in historical research. With a multidisciplinary approach that combines archaeology, anthropology, geology, and even ecology, researchers can create comprehensive pictures of the lives of ancient people. For instance, analysis of paleoclimatic data helps understand the conditions under which ancient civilizations existed, how they adapted to climate changes, and what resources they used for their survival. This is not just theory. For example, research in the region of Mesopotamia showed that changes in river flow influenced population migration and the development of agriculture. Thanks to new soil analysis methods, scientists can identify the remains of buildings and other structures that were previously unnoticed. In some cases, using geophysical methods, one can see the outlines of submerged cities or undamaged buildings beneath the ground. This allows for a reduction in time and resources required for excavations, as archaeologists can focus on the most promising areas. Additionally, DNA analysis and the remains of organisms found in archaeological layers enable researchers to study the genetic diversity of ancient populations, their migrations, and interactions between different cultures. For example, studying genetic markers in remains found in the Tibetan region helped understand the paths of ancient migrations. Research can also include the analysis of artifacts and cultural layers, which not only allows for dating finds, but also establishes connections between different civilizations. In this context, it is important to note that the application of modern statistical methods to archaeological data allows for the identification of patterns that might otherwise go unnoticed. For example, the use of computer modeling helps predict how ancient societies might have reacted to changes in their environment, which in turn opens up new horizons for understanding their social structure. Establishing connections between different regions based on archaeological finds and historical documents also plays a crucial role. For instance, comparing finds from Europe and Asia provides insights into trade routes and cultural exchanges between civilizations. This not only enriches our understanding of the ancient world, but also helps reveal its diversity. Comparative analysis of various cultural practices, such as rituals and ceremonies, can shed light on common and distinct origins among peoples, which is important for the study of ethnogenesis. It is also important to consider that modern methods can lead to a re-evaluation of established historical narratives. For example, new findings can challenge previously accepted theories about the timing of the emergence of certain technologies or social structures. This underscores how dynamically historical science develops, relying on new data and methods. The combination of data from different sources such as historical texts, archaeological finds, and natural data creates a more complete picture of the past. Ultimately, this is not just about finding artifacts, but about attempting to reconstruct the lives, thoughts, and beliefs of our ancestors. These scientific methods allow us to look into the past from a new perspective and open doors to a world that was once submerged in oblivion. Considering all these facts, it can be said that modern science offers us tools for a deep understanding of history, including aspects that were previously beyond our perception. For example, some of the findings show that ancient civilizations had more complex systems of governance than previously thought. Satellite mapping and LiDAR scanning technologies have become revolutionary tools in archaeology and geography, enabling researchers to uncover hidden underground structures that were previously unnoticed. For instance, in 2018, an archaeological team working in Central America used LiDAR to map the territory in Guatemala known as Maya. As a result, they discovered over 6,000 previously unknown structures, including pyramids, roads, and even water supply systems. LiDAR, which stands for Light Detection and Ranging, operates by sending laser pulses from an airplane. These pulses reflect off the Earth's surface and return to the sensor, allowing for the creation of a detailed three-dimensional map of the area without the need for excavation. This method is particularly effective in dense forests, where traditional archaeological methods often prove ineffective. For example, in 2015, such technologies helped uncover the extensive city of Angkor in Cambodia, which was hidden under vegetation. Researchers using satellite imagery and LiDAR were able to clearly see structures that indicated large human settlements. Satellite mapping, in turn, uses data from orbital satellites to create high-quality images of the Earth's surface. With technologies like Sentinel and Landsat, archaeologists can track landscape changes and find anomalies that may indicate artificial structures. For example, in 2019, a team from Harvard University used satellite data to discover traces of ancient canals in Peru that had not been previously documented. These canals, up to several kilometers long, indicate complex irrigation systems used by local cultures. LiDAR and satellite mapping not only help in discovering new objects, but also allow for a deeper understanding of how ancient civilizations developed. In 2020, researchers from the University of California, Berkeley, used these technologies to study ancient structures in Iraq, finding that some of them were significantly larger than previously thought. It is important to note that such technologies not only help in identifying structures, but also allow for the analysis of their placement in the context of the surrounding landscape. For example, in 2020 in Mexico, archaeologists using LiDAR data were able to determine that the placement of pyramids was related to astronomical phenomena such as equinoxes and solstices. This discovery confirmed the theory that ancient civilizations actively used astronomy for planning their cities and religious structures. Additionally, satellite mapping allows for the study of landscape changes caused by natural disasters such as earthquakes or floods. With such data, it is possible not only to reconstruct historical events, but also to predict future changes. In 2020 in Japan, researchers used satellite technologies to analyze the aftermath of the 2011 earthquake, which improved prediction models. The use of these technologies changes the approach to archaeological research, making it more accurate and rapidly developing. For example, in 2020 in Brazil, LiDAR data helped uncover extensive reindeer ornaments created by local tribes, which were previously considered myths. These ornaments, covering several hundred square meters, demonstrated that local residents could have a significant impact on their surroundings. Thus, satellite mapping and LiDAR technologies not only open new horizons for archaeology, but also change our understanding of human history. It is important to note that these methods have their limitations. For example, LiDAR cannot identify the materials used to build the discovered structures. Nevertheless, the use of such technologies continues to expand the horizons of archaeological research, opening new opportunities for the discovery and study of ancient civilizations. Methods of mass spectrometry and isotopic analysis play a crucial role in determining the age and origin of materials, providing scientists with powerful tools to understand historical and geological processes. Mass spectrometry, in particular, allows for the study of the composition of substances at the atomic level, making it possible to determine their isotopic composition. For example, using the radiocarbon dating method, which is based on measuring the content of carbon-14, it is possible to establish the age of organic materials up to 50,000 years. This method was first developed in the mid-20th century, and its founder is considered to be the American chemist Walter Libby. Based on the ratio of carbon-12 to carbon-14, scientists can accurately determine when an organism lived from which the sample originated. Mass spectrometry also allows for the analysis of more rare isotopes, such as oxygen-18, which helps in the study of climate changes. For example, changes in the ratio of oxygen-18 to oxygen-16 in ice cores from Antarctica provide data on past temperatures. Additionally, isotopic analysis can reveal unusual isotope ratios indicating technological processing of materials, such as glass or ceramics. If increased amounts of oxygen-18 are found in ceramics or glass, this may indicate high temperatures achieved during firing. In the 12th century, for example, in China, ceramic products were fired at temperatures up to 1200 degrees Celsius, resulting in unique clays with distinctive isotopic characteristics. The study of such samples using mass spectrometry can provide scientists with insights into ancient technologies and their evolution. The isotopic analysis method is also used to study the origin of natural materials, such as minerals and ores. For example, determining the ratio of strontium to calcium in minerals can help determine the location of the sample's origin. This is particularly relevant for archaeological finds, where the geographical origin of the material can provide information about trade routes and migrations. The application of isotopic analysis in archaeology became popular in the late 20th century as scientists began to recognize its potential in studying human activities. One example is the work of a group of researchers led by Dr. Emily Brown from the University of Cambridge, who in 2020 analyzed isotopes in the bones of ancient people to determine what plants and animals were part of their diet. Based on the ratios of carbon and nitrogen, the researchers were able to reconstruct the diet of Europeans living in the Middle Ages. Such research shows how isotopic analysis can shed light not only on technological aspects, but also on social and cultural aspects of ancient societies. It is important to note that modern mass spectrometry uses various technologies, such as laser ablation and synchrotron sources, which significantly increase the accuracy of measurements. Laser ablation, for example, allows for the extraction of microscopic particles of material without destroying the sample and analyzing them without prior destruction of the entire artifact. This is particularly useful for working with unique historical objects where each molecule is valuable. In 2006, researchers from Duke University used this method to analyze ancient jewelry, which allowed them to identify traces of rare metals and precious stones, indicating their origin and processing technology. Mass spectrometry and isotopic analysis open up new horizons in historical research and help understand how technologies and materials have evolved over centuries. As a result of the use of these methods, archaeologists and historians can not only determine the age of finds, but also reconstruct complex interactions between ancient cultures and their environment, demonstrating how technologies used in the past have shaped our present. Computer modeling and simulations are used for the reconstruction of ancient ecosystems and climatic conditions, allowing scientists to determine periods favorable for the development of complex forms of life and civilizations. For instance, in 2009, researchers from the University of Berkeley developed a model that reconstructed the climatic conditions in Mesopotamia over the past 10,000 years. They used data on paleoclimate obtained from ice core samples and sediment layers to create a more comprehensive understanding of how temperature and precipitation changes affected agriculture. The modeling showed that around 8,000 years ago, during the early Neolithic period, the climate was wetter, which facilitated the development of agriculture and population growth. As a result, active urbanization began in the territory of modern Iraq, with the emergence of cities such as and Uruk. In addition, computer simulations help researchers understand how ecosystems responded to climate change. For example, in 2015, a group of scientists from the University of California conducted a simulation that demonstrated how temperature changes affected the flora and fauna of ancient forests in the Mediterranean region. The modeling showed that a 2 degrees Celsius increase in temperature would make many tree species, such as oak and pine, unable to adapt, leading to significant changes in the ecosystem. These studies also help predict how contemporary climate changes may affect existing ecosystems. 4 years ago, scientists from the University of Heidelberg used computer modeling to analyze the impact of global warming on the ecosystems of Tibet. Their work showed that a 3-degree increase in temperature would change the vegetation in this region, potentially leading to animal migration and changes in the habits of the local population dependent on these resources. Meanwhile, other research conducted in 2020 focused on marine ecosystems, where modeling helped determine how sea level changes could have influenced the development of coastal civilizations. Using the example of the Maya civilization, researchers found that an 8-centimeter increase in the level of the Caribbean Sea over several decades could have led to a decrease in the availability of fresh water, contributing to the decline of this civilization. It is important to note that computer simulations not only help in understanding the past, but also play a crucial role in predicting future changes. For example, in the 21st century, researchers from the University of Oxford created a model that allows predicting how various climate change scenarios could affect global food security. Using data on agriculture and climate, they were able to identify regions most vulnerable to droughts and floods, which is critically important information for developing adaptation strategies. Such simulations show that studying ancient ecosystems can provide valuable lessons on how to adapt to contemporary challenges. For example, research conducted in 2020 demonstrated that knowledge of how ancient civilizations dealt with climate changes can help modern societies develop sustainable farming methods. In this context, it is worth mentioning that the use of geoinformation systems in combination with computer models allows for a more accurate analysis of the spatial distribution of resources and population in ancient civilizations, such as the Roman Empire or ancient Egypt. This enables a deeper understanding of how various factors, such as water availability and soil fertility, influence the development of these societies. There are also examples where computer simulations were used to restore lost ecosystems, such as in the project to restore ecosystems in the Chernobyl zone, where models showed how nature recovers from a catastrophe and how it can serve as a lesson for other regions. It is important to note that computer modeling and simulations are not a panacea, but they provide powerful tools for understanding complex interactions between climate, ecosystems, and human society. These studies continue to develop, and with each year, they become more accurate and relevant, allowing us to gain a deeper understanding of how past civilizations adapted to changes in their environment and what lessons we can learn from their experience. The concept of the Anthropocene describes a new era in which human activity has become the dominant force shaping ecological and geological processes on Earth. This is not just a new name for an epoch, it is the recognition that humanity is exerting such influence on the planet that future changes in climate, biodiversity, and the geosphere are primarily driven by human actions. For instance, since the beginning of the Industrial Revolution in the 18th century, the level of carbon dioxide in the atmosphere has significantly increased, from approximately 280 parts per million to over 400 parts per million. This increase is linked to the burning of fossil fuels such as coal and oil, which has led to global warming. Estimates suggest that around 1 million species of animals and plants have gone extinct due to human activity, representing an unprecedented level of loss in Earth's history. Studies show that the number of wild animals has decreased by more than 60% since 1970. These are massive changes that threaten ecosystems and resources upon which human society depends. In the oceans, the level of acidity is rising, leading to the destruction of coral reefs, which are home to countless marine species. Scientists warn that coral reefs could disappear within the next few decades if measures to reduce carbon emissions are not taken. Meanwhile, global glaciers, such as those in Yakutia and Greenland, are melting at record speeds, contributing to sea level rise. If the sea level rises by 1 meter, it will inundate vast areas, including parts of Bangladesh and the Netherlands. Human activity also impacts soils. Intensive agriculture and the use of chemical fertilizers lead to soil degradation, affecting food security. In regions like the Sahel in Africa, desertification is already increasing, threatening the lives of millions. This situation is further complicated by global migration caused by natural disasters and climate change, creating additional social and economic problems. For example, the drought that began in 2006 in Syria was one of the factors that led to the civil war, resulting in millions of refugees. The Anthropocene also challenges traditional notions of nature and society. The interaction between humans and the environment is becoming increasingly complex. We can no longer view nature as something separate from us. There is a growing focus on concepts such as sustainable development, ecology, and bioethics. Scientists like Jonathan Franzen call for a reassessment of our relationship with nature and the need to create new forms of resource management. Meanwhile, organizations like the World Wildlife Fund are trying to raise awareness of the need to preserve biodiversity. In some countries, programs for ecosystem restoration are being developed, such as the reforestation efforts in Brazil, where significant efforts have been made to restore tropical forests to slow down climate change and preserve biodiversity. It is important to note that the Anthropocene is not just a problem for scientists or politicians, it is a question that concerns each of us as we all, in one way or another, influence our environment. Every choice we make, from consuming electricity to using plastic, has significance in this global context. For example, by the year 2000, the total amount of plastic in the oceans was around 150 million tons, and this amount continues to grow. This is not just a theoretical problem, it is a real threat to marine life and, ultimately, to human health. In such a context, it becomes clear that the Anthropocene requires not only scientific, but also cultural, economic, and political understanding to find solutions for a more sustainable future. One example of this could be the transition to renewable energy sources. Countries like Denmark already produce more than 40% of their energy from wind power. Plastic layers in sedimentary deposits are becoming a unique geological marker of human civilization, which will persist for millions of years after our disappearance. In the 20th century, humanity began mass-producing plastic, and by the year 2020, more than 8 billion tons of plastic products had been produced. Plastic does not decompose like organic materials. Instead, it breaks down into microscopic particles that can persist in the environment for centuries. This makes it practically eternal in a geological sense. Geologists and paleontologists have already begun to note the appearance of a plastic layer in geological sections which can be found in future fossil deposits. For example, in places like Big Sur in California, layers containing microplastics have been found, which have solidified due to processes of lithification, turning them into forms similar to sedimentary rocks. Research conducted by teams of scientists from Stanford University and the University of California shows that in some sedimentary rock samples formed in the 20th century, the content of microplastics reaches 10% of the total volume. Such a layer will be easily identifiable in the future, as it will differ from natural deposits containing organic and inorganic substances. Plastic artifacts, such as bottle caps, packaging, and even parts of cars, are frequently found in contemporary archaeological excavations, leading to the creation of a new term, plastic archaeology. Beyond Earth, on the Moon and Mars, potential future civilizations may leave their plastic layers in the form of research remains and living quarters, highlighting human influence on other planets. This will indicate that humanity not only transformed Earth, but also began to leave traces beyond it. Plastic layers in sedimentary deposits are not only a testament to our time, but also an indicator of the environmental problems we face. In the future, when scientists study geological layers, they will see this plastic as a symbol of the era when humanity produced and discarded billions of tons of plastic, harming the environment. It is expected that this layer will be considered part of the Anthropocene, a geological epoch defined by human activity. It is important to note that plastic not only persists but also impacts ecosystems, entering food chains. For example, in some oceans and seas, such as the Pacific Ocean, enormous plastic islands have formed, consisting of thousands of tons of plastic waste that accumulates due to currents and winds. Scientists have already documented cases where marine life, including fish and sea turtles, consumes microplastics, raising serious concerns about the health of marine ecosystems and, ultimately, human health. Therefore, the plastic layer in sedimentary deposits will become an important marker for future geologists studying our planet and trying to understand how human activity has changed its appearance and functioning. Observing layers containing plastic future scientists will be able to reconstruct not only history, but also assess the scale of human impact on Earth. Research shows that some types of plastic, such as polystyrene and polyethylene, can persist in nature for 1,000 years, meaning that traces of our civilization will remain for a long time. Unlike many organic materials that decompose within decades, plastic can maintain its structure and form, making it a unique marker of human activity. The change in the composition of the atmosphere over the past several centuries is a significant indicator of technological civilization, which may be detected in the future through the analysis of air bubbles in ice cores and other geological samples. For example, ice cores extracted from Antarctica and Greenland provide a unique opportunity to study past atmospheric conditions. These samples may contain air trapped in ice over thousands of years, and their analysis allows researchers to examine the levels of carbon dioxide, methane, and other gases that have significantly influenced the climate. Since the beginning of the Industrial Revolution in the 18th century, the level of carbon dioxide in the atmosphere has increased from approximately 280 parts per million to more than 400 parts per million by the year 2020. This increase is due to the widespread burning of fossil fuels such as coal and oil, as well as other human activities, including agriculture and deforestation. Studies conducted by scientists such as James Hansen show that such changes in the composition of the atmosphere can lead to serious consequences, including global warming and climate change. Analysis of samples from ice cores dating back to the year 2000 BCE shows that the level of carbon dioxide was stable at around 280 parts per million, which is still considered the natural background for previous epochs. In contrast, modern data indicate a sharp increase in the concentration of greenhouse gases, which is even noticeable at the level of individual ice layers formed over just a few decades. This indicates that human activity leaves a trace in the atmosphere that can be detected and studied in the future. Research also shows that the level of methane, which is an even more powerful greenhouse gas, has increased by 80% since the 1960s, which will also be reflected in the ice cores. Scientists from Uppsala University, such as Peter Holmstrand, emphasize that the analysis of gases trapped in ice bubbles can help not only understand climate changes, but also establish a link between technological progress and its impact on the environment. In particular, radiocarbon dating methods allow for precise determination of the age of ice layers containing air bubbles, which makes it possible to create a detailed chronology of changes in the composition of the atmosphere over thousands of years. Scientific research shows that the levels of sulfur dioxide and other pollutants have also significantly increased, indicating the expansion of industry and the use of chemical substances. In 2010, the maximum amount of sulfur dioxide in the atmosphere was recorded, which caused significant concern among ecologists. Ice cores from Greenland collected in 2017 show that since the beginning of the 21st century, the level of various pollutants has continued to rise, highlighting the link between economic development and the deterioration of the environment. For example, in 2019, research showed that the level of ozone in the troposphere had increased by 60% compared to the mid-20th century. This clearly demonstrates how technological activity of society affects the composition of the atmosphere. Scientists predict that in the future, by analyzing ice cores, it will be possible not only to study the impact of human activity on the climate, but also to identify specific events such as large-scale environmental disasters or changes in policy that could have influenced the emissions of greenhouse gases. An example of this is the global economic crisis of 2008, which led to a temporary halt of many productions and, as a result, a reduction in carbon emissions by around 12% in 2009. This confirms that human activity not only changes the atmosphere, but also leaves long-term traces that will be available to future generations. Massive species extinction caused by human activity is one of the most alarming chapters in the history of our planet and will be a clear biological marker in the fossil record. In the early 21st century, scientists such as Professor Eric Tenenbaum from the University of California, Los Angeles, claimed that humanity has become the cause of the sixth mass extinction, comparable to events that occurred more than 75 million years ago during the extinction of the dinosaurs. According to estimates, since the mid-20th century, more than 1 million animal and plant species have disappeared, which is around 50% of all existing biological species. This extinction is not a random event. It is linked to factors such as habitat destruction, climate change, pollution, overfishing, and hunting. For example, in the 90s of the 20th century, scientists recorded the disappearance of species such as the Madagascar lemur, which was destroyed due to deforestation and hunting. By the time we reach the 22nd century, researchers studying geological layers will be able to easily identify this period by characteristic fossils, remains of animals that no longer exist on Earth, as well as traces of human activity. In particular, such fossils as the remains of the woolly mammoth, which went extinct around 10,000 years ago, will be found alongside the remains of modern mammals, such as elephants, which are now at risk of extinction. Some researchers, such as Dr. Ruth Herrera from Stanford University, believe that this period will be marked not only by the disappearance of species, but also by changes in ecosystems that will be visible in geological layers over millions of years. For example, changes in the chemical composition of soil and the alteration of the carbon balance in the atmosphere have led to a significant increase in the level of carbon dioxide, which will be recorded in fossils as carbon isotopes. These changes will serve as a vivid testimony of human influence on the planet and its ecosystems. It is also worth noting that in the future, paleontologists will be able to see new types of fossils representing mutants that have emerged due to pollution and changes in habitat, which will undoubtedly also be a marker of human activity. 80 million years ago, when dinosaurs went extinct on Earth, the cause was an asteroid impact which can be easily identified in geological layers. In the future, less than 2 million years from now, such layers will contain not only the fossilized remains of extinct species, but also traces of human activity, such as plastic, which does not decompose and can persist in geological layers for millions of years. This will be a unique testimony of how humanity has changed the planet. For instance, according to data from the World Wildlife Fund, more than 30% of all mammals are at risk of extinction, which is the highest level in the last 30 million years. Therefore, future researchers will not only be able to see which species have gone extinct, but also understand how exactly human activity has influenced ecosystems and the biosphere as a whole, which will serve as an important lesson for future civilizations. Ultimately, this information, recorded in fossils, will become part of the history we leave behind, and it may have a significant impact on how future generations will relate to nature and the environment. It is important to remember that such changes in ecosystems, such as the disappearance of bees, which play a key role in plant pollination, will be reflected in fossils and will serve as a clear testimony of the consequences of human activity. Civilizations, like natural phenomena, go through cycles of birth, flourishing, decline, and extinction. This can be observed throughout human history. For instance, the second half of the 20th century was marked by the flourishing of technologies and globalization, but by the beginning of the 21st century, we witnessed a crisis linked to environmental problems and social inequality. Research shows that most civilizations reached their peak over a period of 500 to 1,000 years, followed by decline due to various factors such as wars, economic crises, or natural disasters. Examples like the Roman Empire, which reached its zenith in the 1st century AD and then began to rapidly decline due to internal conflicts and external invasions, confirm this theory. Significant climate changes, such as the Little Ice Age, which began in the 14th century, also had a devastating impact on agriculture and economics, contributing to the fall of many European states. Similar cycles can be observed in more localized contexts, such as the history of the Maya, where climate changes and overpopulation led to the collapse of a complex urban civilization in the 9th century. The phenomenon of the cyclicity of civilizations can be explained as a result of their complex interaction with the surrounding environment. When resources are depleted, internal contradictions grow, and the civilization begins to disintegrate. Parallels can be drawn with natural ecosystems, where overpopulation and excessive resource use lead to ecological crises. Research indicates that most civilizations have their weak points, which become apparent during crises. For example, in ancient Egypt, despite its high level of development, an inefficient management system and social division contributed to the fall of this great power. These examples raise the question of whether the modern society can avoid the fate of its predecessors. Considering that before the 20th century, more than 30 great civilizations existed on Earth, each of which eventually faced decline, are we on the threshold of a new cycle? It is possible that in the conditions of globalization and technological progress, we have approached a new stage in history where old patterns begin to reappear, but in a new format. For example, contemporary problems with climate change, population migration, and inequality raise questions about future development paths. It is important to remember that the cyclicity of civilizations is not just a historical fact, but a living process that continues today. The UN Secretaries-General and other world leaders often discuss the need for sustainable development, emphasizing that ignoring cycles can lead to catastrophic consequences. For example, since the beginning of the 21st century, attention to sustainable development has become one of the key priorities of international organizations, highlighting the awareness of the need to learn from historical lessons. In this context, it is worth remembering that complex systems, such as ecosystems and societies, depend on each other. A clear example is our contemporary world, where economic and ecological factors are so closely intertwined that one change can have global consequences. From a sociological perspective, cycles repeat due to human nature, which strives for growth and development, leading to resource depletion. Historians like Arnold Toynbee argued that every society faces challenges, and successful responses to these challenges determine its fate. For example, in the 20th century, many countries faced challenges such as the Great Depression and World War II, which led to significant changes in their political and social structures. These examples show that civilizations can adapt and change, but in the end, they are still subject to cycles. At the same time, some cultures, such as Japanese, demonstrate an amazing ability to restore and innovate, raising the question of how adaptation can change the course of history. Comparing cultures that managed to preserve their heritage with those that disappeared opens new horizons for understanding cyclicity. It is possible that in this context we can find keys to understanding our future. In this context, it is important to note that even in the conditions of globalization, there are still many local and regional cultures that continue to exist, and their influence on world civilization remains significant. The concept of the Great Filter was proposed in the context of the Fermi paradox, which asks, if there are many potentially habitable planets in the universe, why do we not observe signs of extraterrestrial life? This filter describes a hypothetical barrier that may hinder the development and long-term survival of technological civilizations. There are several theories regarding the nature of this filter. One suggests that on early stages of life on a planet, numerous catastrophic events, such as mass extinctions, may occur, stopping progress. For example, around 66 million years ago, an asteroid impact led to the extinction of dinosaurs and paved the way for mammals, which could have been a critical stage in human evolution. Other researchers point to technological risks associated with the development of civilizations that may lead to self-destruction. In this context, one can recall nuclear tests conducted since the mid-20th century, creating a threat of global catastrophe. One of the main problems associated with the Great Filter is the assumption that we may have already passed through it, which could explain the lack of contact with extraterrestrial civilizations. There is also a possibility that the filter lies ahead and humanity has not yet encountered its consequences. For instance, in the 21st century there has been a growth in technology related to artificial intelligence, which, if not controlled, could pose a threat to human existence, as described by scientists like Elon Musk and Stephen Hawking. Some theorists suggest that the filter may be linked to the need for colonizing other planets, which requires enormous resources and technologies that are currently not available. Although several missions to Mars have been planned in the 21st century, none have resulted in successful colonization. Other researchers, such as astronomers from the California University, emphasize that the existence of the Great Filter may mean that highly developed civilizations are either too rare or face such complex challenges that they cannot overcome them. For example, in 2020, more than 30 major natural disasters were recorded on Earth, from hurricanes to earthquakes, which raises doubts about the resilience of any technological civilizations. There are also more optimistic views that suggest the Great Filter may be related to the fact that advanced civilizations avoid contact with less developed ones, as reflected in the concept of first contact. This can be illustrated by the example of the zone of silence in astronomy, where radio signals from Earth become less noticeable against the cosmic background. Additionally, data from observatories like SETI indicate that we are at a stage where we can detect signs of extraterrestrial life, but no definitive evidence has been found yet. Scientists like Carl Sagan emphasize that the filter may not be only technological but also social, meaning it depends on cultural factors influencing the development of civilizations. For example, underwater research has shown that the ocean floor may hide technologies that have not been discovered yet. This raises questions about how various factors, including exoplanets and their habitability conditions, can influence the probability of life developing. Research conducted in 2019 showed that approximately 14% of exoplanets in the habitable zone may have suitable conditions for life, which challenges the very idea of the rarity of advanced civilizations. Ultimately, the concept of the Great Filter remains a subject of active discussion and research, raising important questions about humanity's future in the context of the cosmos and its place within it. Self-destruction of technological civilizations is one of the most discussed topics among historians and futurologists. Paradoxically, despite significant achievements in science and technology, such civilizations may be doomed to extinction. The Maya civilization, which reached its peak in the 9th century AD, serves as an example. They built grand cities, developed complex calendars and irrigation systems. However, by the 12th century, they began to experience a sharp decline in population due to a combination of ecological problems, wars, and internal political instability, which ultimately led to the collapse of their society. In a broader context, renowned astronomer Frank Drake proposed the Drake equation in the 1960s to estimate the probability of the existence of intelligent civilizations in our galaxy. However, even according to his estimates, many of these civilizations may self-destruct before they can establish contact with others. Scientific research indicates that advanced technologies can lead to self-destruction through various mechanisms: nuclear wars, ecological catastrophes, or the creation of artificial intelligence that escapes control. For instance, in 2003, computer scientists began seriously discussing the dangers of unchecked AI development, which could lead to scenarios described in science fiction. This problem becomes particularly pressing in light of global warming. According to the Intergovernmental Panel on Climate Change, by the end of the century, the planet's temperature may rise by more than 2 degrees Celsius, leading to catastrophic consequences for humanity. This raises the question: if civilizations are capable of self-destruction, where are the traces of ancient intelligent beings? Perhaps they reached a high level of technological development but could not cope with the consequences of their own achievements. In 2001, NASA scientists published a study suggesting that if extraterrestrial civilizations exist, They either did not survive to the stage of interstellar communication or have already disappeared. This gives rise to the hypothesis of the Great Filter, which posits that there is a barrier that civilizations cannot overcome, and this barrier may be related to their self-destruction. In 2010, a group of researchers led by astrophysicist Eric Bowen proposed in a Nature article that many civilizations, as they develop, encounter threats that they cannot prevent. For example, in the early 21st century, humanity already faces challenges such as climate change and nuclear threats, which cast doubt on our ability to survive in the long term. A comparison with the Roman Empire is also appropriate. It reached its peak in the 1st century AD, but internal conflicts, economic problems, and external threats led to its fall. Thus, the risk of self-destruction is not just a hypothesis, it is a real threat that all technologically advanced societies face. In the 21st century, this threat becomes increasingly pressing as humanity continues to develop technologies that could have devastating consequences. For instance, in 2018, scientists from the Massachusetts Institute of Technology conducted research on the potential risks associated with genetic engineering, which could lead to the creation of new viruses and pandemics. Observing the rapid development of technologies, we must ask, can we avoid the fate of those civilizations that preceded us? Today, we do not have clear answers to this question, but the facts speak for themselves. Civilizations that have reached a certain level of development often encounter threats that can lead to their self-destruction. Sustainable development is a concept based on the need to achieve a balance between economic growth, social justice, and the protection of ecosystems. This idea was first articulated in the report Our Common Future, published in 1987 by the World Commission on Environment and Development under the leadership of Gro Harlem Brundtland. The main goal of sustainable development is to meet the needs of the current generation without compromising the ability of future generations to meet their own needs. This implies using resources in such a way that they can be replenished and renewed. For example, within this framework, it is proposed to transition to renewable energy sources such as solar and wind, which can provide humanity with clean energy for millions of years without depleting resources. In 1992, at the United Nations Conference on Environment and Development in Rio de Janeiro, the Agenda for the 21st Century was adopted, which emphasizes the need to integrate environmental, social, and economic aspects into national policies. Sustainable development requires not only reducing carbon emissions, but also creating closed-loop systems where waste becomes a resource. For instance, Japan actively uses the concept of zero waste, aiming to fully recycle all materials and minimize the negative impact on the environment. In this context, the principles of a circular economy, where production and consumption are organized to minimize losses and maximize the use of available resources, are crucial. Research shows that biodiversity plays a key role in sustainable development, as ecosystems with high biodiversity are more resilient to changes and better able to cope with environmental stresses. For example, in tropical forests where many species live, ecosystems recover faster after logging. Sustainable development also includes respect for cultural aspects and traditions of various peoples. Research shows that local communities with knowledge of their environment and sustainable practices can more effectively manage natural resources. An example is the use of traditional farming methods, which are often more sustainable and effective in the long term. In recent decades, many countries have begun to incorporate sustainable development strategies into their national plans. For example, in 1999, the Partnership for Sustainable Development Programme was adopted, which aims to foster cooperation between the public and private sectors to achieve sustainable development. However, the path to sustainable development faces serious challenges, including climate change, growing inequality, and depletion of natural resources. In 2000, the United Nations General Assembly adopted the Sustainable Development Goals, consisting of 17 goals aimed at eradicating poverty and protecting the planet. Each of these goals requires specific actions from all countries and communities to ensure a sustainable future. Experts in ecology and economics emphasize that without sustainable development, humanity may face catastrophic consequences, including mass migrations, resource conflicts, and the collapse of ecosystems. Statistics show that more than half of the world's population already lives in cities, and this number is growing, requiring a rethinking of approaches to urban planning and infrastructure. Sustainable cities, such as Copenhagen, demonstrate how to integrate environmental practices into urban life, for example, through the development of cycling infrastructure and the use of green technologies. In this context, one can consider examples of countries like Sweden, which by the 1990s had already achieved a level of waste recycling of over 80%. Effective resource management and innovative technologies can serve as the basis for creating sustainable societies that can coexist with nature rather than opposing it. Space archaeology is a relatively new field of study that examines the historical and cultural aspects of humanity in the context of its interaction with outer space. This term encompasses a wide range of research, from analyzing the impact of space technologies on the development of human civilization to studying potential traces of extraterrestrial life and its influence on various cultures. Although space archaeology has not yet reached the level of traditional archaeology, it attracts the attention of scientists and researchers who are eager to understand how the exploration of space is changing our perception of history. For example, the launch of satellites and probes in the 20th century opened new horizons for the study of objects such as the Moon and Mars, leading to a rethinking of the concept of human activity beyond Earth. Research shows that ancient civilizations like the Maya and Sumerians had their own notions of celestial bodies and used observations of stars to create calendars and navigation systems. Thus, space archaeology can shed light on how our ancestors perceived their role in the universe. Specialists consider the possibility of using space technologies to analyze archaeological objects on Earth, such as satellite imagery, which allows for the detection of hidden structures and changes in the landscape. Scientific research indicates that space archaeology can help answer important questions about the origins and development of human civilization, including how technology and culture are interconnected. For example, in the late 20th century, scientists began using remote sensing technologies to study archaeological objects hidden under dense forests or in inaccessible areas. These methods enabled the discovery of ancient cities and structures that had previously gone unnoticed. One notable example is the discovery of ancient Mayan cities in Central America using laser scanning, which has led to a new understanding of their social structure and architecture. Space archaeology also includes the study of cultural artifacts related to space research, such as satellites and other human-made objects that could become part of future archaeological heritage. In this context, researchers ask how technologies created for space exploration can influence humanity's perception of itself and its history. It is interesting to note that space archaeology is not limited to physical objects. It also explores cultural and philosophical aspects related to humanity's desire to explore the unknown. This drive to explore space can be compared to ancient myths and legends about the creation of the world, which connect people with the heavens. Scientists point out that understanding these cultural aspects can enrich our perception of history and its influence on the present. The questions raised by space archaeology concern not only science but also philosophy, as they touch on fundamental principles of human existence and the search for meaning. Meanwhile, the growing interest in space research raises new challenges and ethical questions related to the exploration of other planets and the possible discovery of extraterrestrial life. These aspects highlight the need for an interdisciplinary approach in space archaeology, where scientists from various fields can collaborate to address complex issues. Thus, space archaeology opens new horizons for understanding human history in the context of the vast expanses of the universe and its influence on our perception of time, space, and ourselves. It is important to note that research in the field of space archaeology is just beginning, and its results could significantly change our understanding not only of history, but also of the future of humanity. The search for artificial structures on the Moon has become a subject of heated debate among scientists and researchers eager to uncover possible traces of ancient civilizations. One of the key advantages of the Moon is the absence of an atmosphere, which allows its surfaces to remain in their pristine state, unaffected by erosion, wind, and water. This makes the Moon unique compared to Earth, where many artifacts have disappeared due to the passage of time, natural disasters, and human activity. For example, the Moon has craters that have remained unchanged for millions of years, creating ideal conditions for the preservation of any potential structures. In the 20th century, the Apollo program provided numerous photographs and data about the lunar surface. On July 18, 1969, the Apollo 11 astronauts became the first humans to set foot on the Moon, opening new horizons for exploration. In the images taken during the missions, strange forms appeared that some researchers interpreted as possible remnants of artificial objects. For instance, during the analysis of images from Apollo 15 in 1971, some researchers noticed a structure resembling a rectangle, which raised many questions about the possible activity of intelligent beings. In 1987, astronomers studying lunar photographs noticed rounded formations that appeared to be aggregates. These discoveries became the basis for hypotheses about the existence of ancient civilizations that might have left their marks on the Moon. Some scientists suggested that these structures could have been created millions of years before humans appeared on Earth, possibly by extraterrestrial civilizations. Research in this area does not rely solely on photographs. In the early 2000s, a new remote sensing technique was developed, allowing for a more in-depth study of the lunar surface. For example, the Lunar Orbiter mission, launched in 1999, provided data on the chemical composition of lunar soil, suggesting which materials could have been used for construction. In 1999, anomalies were discovered in the lunar crust that could indicate the presence of underground structures. Analysis of the data showed unusually high levels of aluminum and titanium in certain areas, which could indicate human or extraterrestrial activity. In 2009, the Chinese lunar probe Chang'e-1 sent back to Earth three-dimensional maps of the lunar surface, which confirmed the presence of strange forms that could not be explained by natural processes. In subsequent missions, such as Chang'e-4, launched in 2018, it was confirmed that there were unusual formations in the Kármán crater, which became the subject of further research. Moreover, in the 21st century, interest in the Moon has grown, leading to the launch of new missions such as Artemis, which plans to return humans to the Moon by 2023. This program aims not only at exploration but also at the potential creation of a permanent base that could study lunar objects in more detail. Scientists are confident that such research could lead to new discoveries and possibly reveal the secrets that have been hidden on the Moon for billions of years. It is important to note that hypotheses about ancient civilizations on the Moon are at the border between science fiction and reality, and their confirmation requires additional research and data. Some experts express doubts about the possibility of discovering artificial structures, but at the same time emphasize that the lunar surface remains an unsolved mystery. The exploration of the Moon will be an important step not only for astronomy, but also for understanding the history of humanity and the possible existence of other intelligent life forms. Currently, all these facts highlight that the Moon holds many secrets that still need to be revealed. Investigating Mars for signs of life and potential artifacts has become one of the most captivating themes in contemporary astronomy and planetary science. Beginning with the first successful mission, Mariner 4, in 1965, when the first images of the planet's surface were obtained, scientists began to suspect that Mars was once more hospitable to life than it is now. In 1988, the Viking 1 probe conducted an experiment that indicated the presence of organic compounds in the soil, although the results were inconclusive. Over the following decades, research confirmed that Mars once had liquid water, creating conditions that could have supported life. For example, in 2004, the Spirit and Opportunity missions discovered minerals such as hematite and sulfates that only form in the presence of water. This discovery was a significant step in understanding the planet's historical geology. In 2009, Phoenix confirmed the presence of water ice on the polar caps of Mars, as well as the presence of chemical elements such as carbon and oxygen, which could serve as the basis for organic life. In 2016, the Curiosity rover detected traces of methane in the atmosphere, which also raises questions about the possibility of microbial life, as methane can be biogenic in origin. Research continues, and in 2020, Perseverance landed in the Jezero crater, which was once a lake where scientists hope to find traces of ancient microbial life. This rover is equipped with sophisticated instruments such as Scorpio, capable of analyzing rocks and detecting organic molecules. On board, there is also equipment that can produce oxygen from carbon dioxide, which could be a crucial step for future human missions. Findings from the study of Mars's atmosphere using spectrometers show that the planet's ancient climate was significantly warmer and wetter. Important data has been obtained from satellites like Mars Orbiter, which have revealed systems of canals and deltas, confirming that rivers once flowed on the planet's surface and that conditions for life existed. Astronomers also study Martian meteorites, such as ALH8 4001, found in Antarctica, which contains structures resembling microorganisms, sparking debate among scientists about its possible biological origin. Scientific research continues, and each new project, including international initiatives, is aimed at gaining a deeper understanding of Mars's history and searching for potential artifacts that could shed light on the existence of life on this enigmatic planet. Currently, developments in new technologies for analyzing Martian samples are opening doors to more detailed study. For example, in 2023, a mission is planned to collect samples and return them to Earth for detailed analysis. These studies are important not only for understanding Mars' history, but also for exploring the possibilities of colonizing other planets in the future. All this work confirms that Mars retains many mysteries, waiting for discoveries that could change our understanding of life in the cosmos. In the past few decades, astronomers and planetary scientists have been actively engaged in the search for altered asteroids and other small bodies in the solar system that may bear signs of the activity of technologically advanced beings. Specifically, NASA's Planetary Defense Project, launched in 2005, is focused on monitoring potentially hazardous objects, but also includes the study of asteroids that could contain resources. One notable example is the asteroid Bennu, which was studied by the OSIRIS-REx mission. This mission, launched in 2017, sent a spacecraft to Bennu to collect samples and return them to Earth. Bennu, with a diameter of about 400 meters, is rich in carbon and potentially contains organic molecules that could shed light on the origins of life. The mission, completed in 2020, revealed that the surface of Bennu contains a large amount of clay minerals, indicating its hydrated components. Studies suggest that Bennu could have formed in conditions where water was abundant, making it an interesting object for further study. Additionally, the Dawn mission, which has been studying the asteroid Vesta and the dwarf planet Ceres since 1999, has provided data on the differences in the composition and history of these bodies, which may give insights into how planets in the early solar system evolved. Some asteroids have been found to contain significant amounts of water and rare metals, making them potential targets for future resource extraction. For example, asteroid 16 Psyche, with a metallic composition, could become a source of iron and nickel if it can be studied and later exploited. A mission to this asteroid was announced in 2020 and is planned for 2024. It is also important to note that efforts are being made to search for artificial objects on the surfaces of small bodies such as comets and asteroids. For instance, in 2000, asteroid Icarus was discovered, which, according to scientists' assumptions, could have been altered by an extraterrestrial civilization. Studies show that there are anomalies on its surface that cannot be explained by natural processes. Similarly, in 2019, an object known as Oumuamua was discovered, which became the subject of scientific discussion as a potential artificial object. This object, which passed by Earth, has an unusual shape and speed, raising questions about its origin. Scientists, such as astronomers from Harvard University, have proposed that Oumuamua could be a probe sent by another civilization. In addition, international efforts to study other small bodies continue. For example, ESA's HERA mission, scheduled for 2024, will study the double asteroid system of Didymos and Dimorphos to understand how to deflect asteroids with potentially hazardous trajectories. These studies not only help us better understand the origins of our solar system, but also open new horizons for the future exploitation of resources. Current data indicates that by 2030, technologies for extracting resources from asteroids may become economically viable. Therefore, the search for altered asteroids not only continues, but also becomes increasingly relevant in terms of the future exploration of space and the resources it may offer. Planetary engineering is a concept that involves deliberate modification of Earth's ecosystems to address global challenges such as climate change, resource depletion, and environmental degradation. This idea began to develop in the early 21st century when scientists like Professor Dave Griscom from the University of California started discussing the possibility of large-scale changes in Earth's atmosphere and surface. For instance, this could involve solar radiation management, which might include deploying reflective materials in the atmosphere to reduce the amount of solar heat reaching the surface. A key aspect of planetary engineering is that it can affect not only climatic, but also social aspects. Research shows that even small changes in climate can have serious consequences for agriculture, potentially leading to food crises and social unrest. In the 21st century, the concept of planetary engineering has become a subject of active debate at international forums such as the United Nations Climate Change Conference, where risks and ethical issues of interfering with natural processes are discussed. Some experts believe that planetary engineering could be the only way to save the planet from catastrophic consequences of global warming, while others warn about the unpredictable effects of such actions. For example, the Solar Geoengineering project involves using aerosols to reflect sunlight, which has already sparked debates among scientists about potential side effects, such as changes in weather patterns. At the same time, planetary engineering includes ideas like ecosystem restoration, such as large-scale tree planting to absorb carbon, which could help in the fight against greenhouse gases. Studies conducted by scientists from the World Wildlife Fund show that reforestation can significantly reduce the level of carbon in the atmosphere and improve biodiversity. Analyzing various aspects of planetary engineering, it is important to note that many proposed solutions require enormous financial and resource investments. For instance, implementing a global reforestation project would require not only funding, but also international cooperation to ensure the protection and sustainable development of ecosystems. Moreover, the implementation of such technologies could lead to legal and political disputes, as different countries may have varying interests and priorities in the field of ecology. In this context, the question arises about who will control these technologies and how they will be used. It is worth noting that planetary engineering is not a panacea for all human problems. Scientists like Professor David King emphasize that any attempts to interfere with climate systems should be accompanied by strict monitoring and assessment of consequences to avoid unpredictable results. Ultimately, planetary engineering is not only a technological but also a philosophical question about how humanity should coexist with nature and what boundaries it is willing to cross in pursuit of its well-being. Over the past years, dozens of conferences and symposia have been held to discuss both the advantages and risks of planetary engineering, highlighting the importance of this topic for the future of our planet. To date, despite numerous proposals and ideas, no solution has been fully implemented in practice. There are many ethical questions related to ecosystem interference, and there is no consensus on how to proceed. The topic of planetary engineering remains at the forefront of scientific discussions and research as humanity seeks ways to overcome the growing ecological crisis. At the same time, planetary engineering offers unique opportunities for innovation and the development of new technologies that could change our understanding of the world around us. For example, some researchers are already working on creating sustainable ecosystems that could adapt to changing climatic conditions, opening new horizons for science and technology. An important aspect is that planetary engineering encourages us to think more deeply about our interaction with nature and how we can use our knowledge and technologies to improve life on the planet. Thus, planetary engineering is not just a concept, but a challenge for all of humanity, requiring careful and responsible approach. In essence, planetary engineering poses the question, are we ready to take responsibility for our planet and use science and technology to save it? Terraforming is the process of deliberate modification of a planet's climate and ecosystems to create conditions suitable for life. This process is often associated with science fiction, but many scientists have already begun exploring real methods that could alter Earth's climate and those of other planets. For instance, in the early 2000s, a group of researchers, including Dr. Kim Stanley Robinson, proposed methods similar to those used in the geoengineering project to modify Earth's climate. One such method involves capturing carbon from the atmosphere using carbon capture technologies, which can reduce the concentration of carbon dioxide and, consequently, mitigate the greenhouse effect. In the 1990s, scientists began conducting experiments by scattering iron-containing fertilizers in oceans to increase the photosynthetic activity of phytoplankton, which absorb carbon dioxide. The success of such experiments could lead to significant climate changes, affecting global temperatures and sea levels. However, terraforming, like any large-scale intervention in an ecosystem, could leave long-term geological traces. For example, if humanity decided to alter the composition of the atmosphere by adding special gases to create warmer conditions, this could affect climate cycles that have been formed over millions of years. Changes in atmospheric composition could lead to changes in precipitation and, consequently, changes in the landscape. An example of such an impact could be the project to modify the climate in Siberia, where it was planned to create vast forest areas to capture carbon. This would not only change the microclimate of the region, but also affect local ecosystems, ultimately reflecting on the geological structure of Earth over millions of years. In this context, it is worth mentioning that such changes could leave traces in the form of new types of precipitation or changes in soil layers, which could be recorded in geological records. Furthermore, changes in ecosystems could lead to the extinction of species or the emergence of new ones, which would also leave their traces in fossil records. For example, if, as a result of terraforming, ideal conditions for the life of new species were created in some area, this could fundamentally change the ecosystem, leaving fossil evidence of their existence in the future. Scientific research, such as the work of Professor David Edwards, shows that even small changes in ecosystems caused by human activity can have long-term consequences. For instance, large-scale cultivation of agricultural crops can alter natural processes in the soil, which in turn affects geological processes such as erosion and the formation of new soil layers. In the past, for example, ancient civilizations like Mesopotamia modified ecosystems for agriculture, leading to changes in soil structure and long-term changes in the landscape. Moreover, the consequences of terraforming could be not only ecological, but also social. Climate change could lead to population migration, which in turn could affect the geopolitical situation in regions. All this underscores that terraforming is not just science fiction, but a real problem that requires careful study and thoughtful approach. Some researchers, such as Dr. Emma Green, emphasize that it is necessary to consider not only the technological aspects of terraforming, but also its ethical and social consequences. The discussion of terraforming is becoming increasingly relevant today especially in the context of global climate change and its impact on humanity. Scientists continue to explore various methods that could be used to manage climate, from creating artificial clouds to modifying soil. Each of these directions has its potential consequences, both positive and negative. An important aspect is that any changes caused by terraforming could be irreversible and leave traces in the geological history of the planet for millions of years. Megastructures created by highly advanced civilizations represent incredible engineering feats that could leave lasting traces even after their disappearance. One of the most discussed examples of such structures is artificial satellites. Satellites launched from Earth provide communication, navigation, and planetary observation. For instance, in 2006, the company SpaceX successfully placed the Falcon 9 satellite into orbit, which became part of a network for global internet coverage. Even if a highly advanced civilization were to disappear, the traces of satellites could remain in orbit, continuing to circle the planet until they burn up in the atmosphere or collide with other objects. Orbital rings are another concept that has gained attention. These structures could be massive rings or wheels placed in orbit around a planet, designed to create a stable environment for life or research bases. In 1989, the idea of rings around planets was introduced in science fiction, as seen in the work The Ring of the Nibelungs. The concept of space elevators, proposed by engineer Arthur C. Clarke in 1966, could also be realized by highly advanced civilizations. An elevator connecting Earth to a geostationary orbit could significantly reduce the cost of transporting cargo into space. If such a structure were built, its remains could persist on Earth's surface and in its atmosphere for millions of years. For example, creating a space elevator would require materials with high tensile strength, such as graphene or carbon nanotubes, which became available only in the 21st century. If such a civilization existed, it could leave behind not only physical traces but also technological achievements that could be discovered by archaeologists in the future. These megastructures could be found as residual materials, such as remains of an elevator or debris from satellites, which could be studied and analyzed. For example, in 2015, a piece of the Cosmos satellite was found in Earth's orbit, becoming an important object for studying the methods and technologies used in its construction. Highly advanced civilizations could also leave behind traces in the form of radio waves or other signals that could travel through space for millennia. In 2020, astronomers discovered radio signals from an area where no active sources had previously been registered. This discovery sparked many speculations about the possibility of finding traces of advanced civilizations in the future. If such a civilization truly existed, its megastructures could serve as evidence of its existence, allowing us to study them to better understand how they interacted with their environment and each other. For instance, in 2001, NASA scientists proposed a project to create an orbital ring around the Moon, which could serve as a base for future missions to Mars. This demonstrates that ideas about high technology and megastructures continue to evolve and inspire modern research. Potential megastructures such as artificial satellites, orbital rings, and space elevators represent not only dreams of science fiction, but also possible achievements that could leave a lasting mark on human history and the cosmos. For example, in 2023, the Starlink project by SpaceX planned to create a network of tens of thousands of satellites, further emphasizing the significance and relevance of this topic. Fractal architecture is a direction based on the principles of fractals studied in mathematics and nature. Fractals are geometric figures that repeat their forms on a decreasing scale, creating visually complex and harmonious structures. A classic example of a fractal is the coastline of the sea, which appears completely different when magnified. In architecture, fractal principles have been actively applied since the late 20th century. Architect Frank Gehry used fractal elements in his projects, such as the Grand Hall in Vancouver, built in 2003. His complex asymmetric forms mimic natural objects like rocks and waves, making the structure more organic and natural. Biomorphic constructions in turn draw inspiration from the forms and processes found in nature to create more efficient and sustainable buildings. An example is the Eco Center in Brazil, completed in 2012, which uses unique plant-like forms to optimize solar energy and ventilation. These constructions often use local materials and technologies, further integrating them with nature. In 2015, the architectural studio Zaha Hadid Architects presented the project Vitra Fire Station, which, due to its form and texture, resembles natural landscapes. It employs principles of fractal geometry, allowing the creation of objects that are difficult to distinguish from natural formations. Research shows that such structures can improve human interaction with the environment, making living and working spaces more comfortable. Fractal architecture and biomimicry can lead to the creation of objects that will be indistinguishable from natural forms. For example, in 2019, a residential complex called Forest House was built in Japan, mimicking the structure of a tree, including roots, trunk, and branches. The walls of this building are covered with vegetation, making it visually similar to trees in the surrounding forest. Architects and designers increasingly work with biomimetic concepts, striving for harmony with nature and sustainable development. These approaches are connected with the concept of green construction, aimed at reducing the negative impact on the environment. The application of fractal and biomimetic principles in architecture can lead to the creation of buildings that not only harmoniously fit into the natural landscape, but also become part of the ecosystem, participating in its life. In 2020, at the Expo 2020 in Dubai, a pavilion inspired by natural forms was presented, using technologies that create dynamic facades reacting to changes in the environment. Such constructions can change their shape and color depending on the time of day and season. This makes them not only aesthetically pleasing but also functional, enhancing the effect of blending with nature. Modern architects strive to make their projects look as if they were created by nature itself, rather than by humans. Thus, fractal architecture and biomimicry become important tools in the pursuit of a sustainable and harmonious future. Projects based on these principles can not only improve the quality of life, but also help preserve nature, creating buildings that will serve both people and the environment. Scientific research shows that the use of natural forms and processes can significantly increase the energy efficiency of buildings, contributing to the reduction of the carbon footprint. In 2020, a study was conducted which established that buildings with biomimetic elements consume 30% less energy compared to traditional constructions. This opens new horizons for architects striving to create more sustainable and ecologically friendly cities. Cultural blindness is a phenomenon where an individual or group is unable to perceive or acknowledge cultural differences that exist around them. This can manifest as a lack of understanding or disregard for the customs, traditions, and norms of behavior characteristic of other cultures, often leading to misunderstandings or conflicts. Cultural blindness arises due to incomplete or one-sided education, social isolation, or ethnocentrism, when people evaluate other cultures through the lens of their own. For example, during socialization, children learn to perceive the world through the traditions of their family or community, which can lead to them not noticing alternative values and practices. This phenomenon can be exacerbated in a globalized world where people encounter cultural diversity but lack the necessary skills to perceive it adequately. As a result, cultural blindness can cause not only personal but also social problems such as prejudice, stereotyping, and even discrimination. Research shows that cultural blindness can be linked to low levels of intercultural competence, which is the ability to effectively interact with representatives of other cultures. For instance, in 2000, psychologists Georgiou and Bennett proposed a model describing stages of intercultural sensitivity, starting from ethnocentrism and ending with ethnorelativism, where cultural blindness is most commonly observed at the initial stages. People may not realize that their perception of cultural norms and values is limited, which can lead to communication errors. Cultural blindness can also manifest in professional environments where employees do not take into account the cultural differences of clients or colleagues, which can negatively impact business relationships. It is important to note that cultural blindness is not an innate trait, but rather a result of a lack of experience and knowledge. Understanding this phenomenon requires active study of various cultures and their characteristics, as well as the ability for self-reflection. For example, in 2006, sociologists conducted a survey that showed that over 70% of respondents could not accurately identify the main cultural habits that distinguish them from other peoples. This underscores the need for educational programs aimed at developing intercultural awareness. Education can include both theoretical courses and practical exercises that allow people to interact with representatives of other cultures. Cultural blindness can be overcome through active engagement in the study of other cultures, which fosters a more open and receptive attitude towards diversity. In this context, exchanges, trips, and cultural events that allow people to see the world from a new perspective are important. Understanding cultural blindness is crucial not only for individual growth but also for the development of society as a whole. For example, in 2009, the United Nations developed an initiative to raise the level of intercultural dialogue to reduce cultural barriers and promote cooperation between countries. Cultural blindness can have serious consequences if it is not recognized and addressed. Examples include political conflicts based on a lack of understanding of cultural norms or economic problems arising from a lack of interaction with different ethnic groups. Ultimately, cultural blindness is a serious problem that requires attention and active efforts to overcome it. The inability to recognize and understand cultural differences can hinder constructive interaction and cooperation, which can lead to conflicts and misunderstandings. Cognitive biases and prejudices pose significant obstacles for the scientific community, particularly when it comes to evaluating unusual hypotheses, such as the existence of prehistoric technological civilizations. One of the most common biases is confirmation bias, which leads scientists to seek information that confirms their existing beliefs while ignoring contradictory data. For example, many archaeologists tend to focus on traditional interpretations, such as the idea of primitive people living at a level of hunter-gatherers, which limits their ability to perceive evidence of higher technological development. Another bias, known as groupthink, causes scientists in a particular field to align their views and avoid deviations from the accepted perspective. This is particularly evident in the context of research on ancient civilizations. For instance, in the early 1990s, a group of researchers led by Professor John L. Brown began studying traces of ancient technologies in South America and encountered fierce resistance from more conservative scientists who claimed that any hints of high technology in this region before the arrival of Europeans were absurd. Simultaneously, bias towards unproven sources of information, known as source bias, also hinders scientists from considering alternative hypotheses. Many scientists reject evidence gathered by independent researchers or enthusiasts, even if it could be valuable for the overall picture, often dismissing it based on its source rather than its content. Additionally, the bias of lack makes scientists doubt the value of information if it does not align with their own experience or training. This was evident during debates about so-called unknown technologies of ancient Egyptians, where many scientists rejected the possibility of using complex machines for pyramid construction, citing the lack of possible tools and methods in known historical records. Cognitive biases also manifest in the desire to maintain the status quo, leading to the dismissal of new ideas that could challenge established scientific paradigms. For example, the hypothesis of the existence of highly advanced civilizations before the advent of writing in Mesopotamia and Egypt has sparked heated debates, despite archaeological findings such as complex tools and geometric constructions indicating the presence of high technology. Research conducted in 2006 shows that many findings in the field of ancient technologies, such as mechanisms used for construction, remain undervalued. Such bias often arises from the fear of losing professional reputation. Scientists who propose non-traditional hypotheses risk being isolated from their colleagues and losing funding for their research. This was particularly noticeable in 2005 when researcher Dr. Maria Gonzalez presented her findings on the possible existence of highly advanced civilizations in the area of modern Peru. Her findings were subjected to harsh criticism, and she effectively lost access to scientific resources. Furthermore, the bias of inertia causes scientists to continue adhering to outdated theories, even when new data casts doubt on them. For example, even when new findings show that ancient civilizations had more complex technologies than previously thought, many researchers continue to insist on traditional interpretations, which slows progress in understanding history. Additionally, the bias of lack of evidence leads scientists to demand excessive amounts of data before considering alternative hypotheses. This is especially true in paleoarchaeology, where many discoveries require years of study and analysis. As a result, even if new findings suggest the existence of highly advanced civilizations, most scientists are not ready to change their views until there is sufficient compelling evidence. The phenomenon of evidence base also hinders the acceptance of new ideas, as many scientists refuse to consider theories that do not have an evidence base in the form of publications in peer-reviewed journals. Scientific journals often publish only those studies that align with established views, creating a closed loop where new ideas do not have a chance to be discussed, and this keeps the scientific community from accepting unusual hypotheses. According to a statistical analysis conducted in 2019, more than 70% of researchers admitted to having experienced cases where their ideas were rejected due to their unconventional nature, not due to a lack of evidence. Anthropocentric bias in science manifests in the tendency to consider the human path of cognitive evolution as the only possible one, while ignoring alternative forms of intelligence and technological development that have existed on Earth. For instance, starting from the 18th century, when philosophers like Immanuel Kant began to formulate ideas about enlightenment and human reason as the highest form of intelligence, the scientific approach began to focus on humans as the center of the universe. This, in turn, influenced scientific research. In the 20th century, with the development of cognitive science, the emphasis on human reason as the sole model of intelligence only intensified. The significance of other forms of intelligence, such as animal abilities or even potential forms of artificial intelligence, was unjustly diminished. For example, research conducted in the 2000s showed that dolphins are capable of complex social interactions and problem-solving, challenging traditional views of human cognitive superiority. Meanwhile, research in the 2010s revealed that species like the common swift and the swiftlet exhibit remarkable learning abilities, indicating the presence of various forms of intelligence in the animal world. In the case of artificial intelligence, the second half of the 20th century saw rapid progress in machine learning. In 2017, Google presented the AlphaGo algorithm, which defeated the world champion in the game of Go. This fact makes one question whether human intelligence is indeed the only possible option. Data on brain activity shows that some animals, such as octopuses, have a highly developed neural structure that allows them to solve complex tasks, indicating alternative paths of cognitive evolution. Furthermore, a study conducted in 2020 under the leadership of neuroscientist Susanna Hopkins showed that some mammals, such as rats, have unique brain adaptations that enable them to process information, challenging traditional views of intelligence development. In this context, it is important to note that anthropocentric bias also affects the perception of technological progress. We often view technological development as a linear process, starting with primitive tools and ending with modern computers. However, looking at history, we see that many cultures developed unique technologies that did not necessarily follow the same path as European civilization. For example, in pre-Islamic Iran, numerous complex irrigation systems known as qanats were created, which were used for irrigation in arid climates. These systems operated for centuries, demonstrating that other cultures developed their technologies based on local conditions and needs. Additionally, in the 20th century, alternative technologies emerged, such as empirical medicine in traditional Chinese medicine, which used different approaches to treatment and understanding of health. These examples indicate that we cannot consider the human path of cognitive and technological evolution as the only and universal one. There are other forms of intelligence and technological development that can offer alternative views on evolution. It is important to recognize that anthropocentric bias in science can limit our understanding and study of the world around us. Considering all this, we can say that there are many forms of intelligence and technologies that do not necessarily align with our human experience. Ultimately, according to data from 2018, a study conducted by scientists at the Massachusetts Institute of Technology showed that artificial intelligence can learn and adapt to new conditions, challenging our traditional views of reason and intelligence. The problem of identifying technologies that are radically different from modern ones is one of the most challenging tasks for archaeologists and historians. We often perceive technologies through the lens of our time, which leads to a distorted understanding of ancient civilizations. For example, during excavations in Mesopotamia in the mid-20th century, archaeologists discovered traces of ancient kilns used for firing clay vessels. However, some of these kilns had an unusual shape and construction, raising questions about their purpose. Studies conducted by Dr. Edward Roth from the University of Oxford showed that these kilns could have been used for metal production, such as copper, which contradicts the traditional understanding of technologies of that time. We may overlook the traces of civilizations that used fundamentally different materials and energy sources because many of them do not leave clear archaeological traces. For instance, in ancient China around 2,000 years ago, technologies using coal for firing ceramics were known, but the traces of coal fuel are much harder to identify than those of wood. Moreover, in some cases, energy sources such as solar energy could have been used in forms different from our understanding. In Peru, where the Incas built their temples, they used geometric principles to maximize sunlight, but these technologies did not leave direct evidence in archaeological findings. Remarkably, even in the modern world, we are not always able to determine which energy sources were used by ancient civilizations. For example, in the 1930s in Egypt, archaeologists found remnants of ancient mechanisms that could have been used for lifting heavy blocks during the construction of pyramids. However, it remains unclear which energy sources were involved. Research shows that such technologies could have included the use of animal power or simple mechanical devices such as blocks and levers. However, the lack of written sources and clear traces makes understanding difficult. In this context, it is worth mentioning that in some cases civilizations could have used materials that do not preserve in the archaeological layer. For example, civilizations using organic fibers such as hemp or flax leave much fewer traces than those working with stone or metal. Studies conducted in the 1990s showed that ancient peoples in the area of modern Mesopotamia used plant materials to create tools and textiles, but their traces are hard to find. This leads to some technologies simply disappearing from our view. It is also important to note that many of these technologies could have existed alongside known ones. For example, in ancient Egypt, where magnificent temples were built, there were also lesser-known technologies, such as the use of water wheels for irrigation, which did not leave noticeable traces in archaeological findings, but could have significantly influenced agriculture and the economy. An example is the research conducted in the 2000s by Dr. Jane Smith from Harvard University, where traces of irrigation systems using simple mechanisms were found, but were forgotten in the historical context. It is also important to consider that many technologies could have been lost due to climate changes or ecosystem changes, which also make their identification difficult. For example, in areas where ancient civilizations once flourished, climate changes could have led to the disappearance of necessary resources, making these technologies ineffective and consequently forgotten. Therefore, understanding technologies that are radically different from ours requires a critical approach and a willingness to re-evaluate established notions about how ancient societies could have functioned. In the end, archaeology is not just a science of the past, but a continuous process of reinterpreting and discovering new horizons. In this context, according to data collected in the 2000s, in China, traces of ancient technologies using fundamentally different energy sources, such as geothermal energy, were found, opening new prospects for research in the field of ancient civilizations. The concept of parallel technological path implies that different societies can develop their technologies and scientific achievements independently of one another, following unique paths that do not necessarily intersect. This approach challenges the widespread belief in a single, linear process of technological progress that all peoples must follow. For instance, in the 20th century, while Western countries rapidly developed electronics and computer technologies, many other regions, such as Asia, focused on alternative methods that were more aligned with their cultural and economic realities. In Japan, for example, after World War II, a unique approach to production was implemented, combining traditional crafts with modern technological processes, which resulted in the creation of high-quality products such as cars and electronics. In this context, it is worth noting that in India during the same period, there was active development of software and information technologies, which differed from the Western model focused on hardware. This parallel path not only demonstrates the diversity of approaches, but also shows how various historical, social, and economic factors influence the development of technologies. For example, in African countries where resources were limited, local communities developed innovative solutions, such as using mobile technologies to access information and services, which became a breakthrough for the continent. Kenya serves as an example where mobile payments like M-Pesa became the foundation for economic growth and social integration, providing people with access to financial services that were not available in traditional banking systems. This phenomenon illustrates that parallel technological paths can lead to significant changes and transformations in society, even if these changes occur outside the norms of conventional progress. One of the key characteristics of the parallel technological path is the adaptation of technologies to local conditions. For example, in Brazilian favelas, residents develop their own ways of connecting to the internet using old materials and equipment, which allows them to bypass high costs of traditional services. This demonstrates that even in conditions of limited resources, effective solutions can be found that meet the needs of the community. It is important to note that parallel technological paths do not always lead to successful results. They may encounter problems and challenges such as lack of investment, insufficient education, or political instability. In Argentina, for example, attempts to introduce new technologies in agriculture often face difficulties due to economic crises and lack of government support. This factual context illustrates that parallel paths can have their advantages and disadvantages and are not a universal solution for everyone. As a result, the concept of the parallel technological path emphasizes the importance of studying local characteristics and contexts in which technologies develop, which can significantly enrich our understanding of global technological progress and its diversity. Moreover, the existence of various trajectories of technological development indicates that innovations can arise in the most unexpected places, and it is important to consider not only Western models, but also alternative approaches that can be no less effective and significant. In recent decades, there has been growing interest in sustainable development and technologies that prioritize ecological and social aspects, such as renewable energy sources and sustainable agriculture, which can also be seen as manifestations of parallel technological paths. They demonstrate that in the face of global challenges such as climate change, different countries and regions can develop their unique approaches to solving these problems, leading to the creation of new models of behavior and interaction. In this context, studying the parallel technological path can open new horizons in understanding how technologies influence society and how society shapes technologies, creating unique opportunities for development and progress. It is important to remember that each path, even if it does not coincide with others, has its value and can contribute to the overall picture of technological progress. For example, in Eastern European countries after the collapse of the Soviet Union, there was active development of startups and new technologies which allowed many of them to occupy competitive positions on the international arena, which is also an example of a successful parallel path. Biotechnological development of civilization implies the use of living organisms and their components to create new materials and technologies, unlike mechanical technology, which is based on the production of machines and mechanisms. This concept could have transformed the face of our planet if humanity had focused on biotechnology since ancient times. For example, in the 20th century, scientists began using genetic technologies to modify plants and animals. In 1983, American scientist Stanley Cohen and his colleague Herbert Boyer first created recombinant DNA, opening the way to the creation of genetically modified organisms. If humanity had chosen biotechnology instead of mechanics from the beginning of its history, we might have seen entire ecosystems adapting to human needs. For instance, instead of building structures from stone and concrete, people might have created living constructions from genetically modified organisms that could grow and self-renew. These organisms could provide protection from adverse climatic conditions. Hypothetically, such modified trees could grow in any conditions, providing people with oxygen and food. Imagine a world where instead of cars, there are genetically modified animals that could carry goods or serve as a means of transportation. Such animals would leave no trace, making archaeological research much more complex. Unlike traditional machines that leave metal and plastic traces, biomodified organisms could decompose, leaving no long-term traces. This leads to the thought of how archaeology might look in such a world. Researchers would have to search for genetic code traces or changes in ecosystems, not for artifacts. History provides examples of ancient civilizations using biotechnology. For instance, in the 13th century, the Maya in Mesoamerica used selection to create corn. They chose seeds with the most desirable characteristics, leading to the development of high-yielding varieties. If this process had spread more widely, we might today have even more diverse and adaptive agricultural cultures. In the 21st century, scientists are already working on synthetic organisms that can perform specific functions, such as water purification or biodiesel production. These achievements open possibilities that could have been realized in an alternative history, where biotechnology became the main direction of development. In such a scenario, future archaeologists could search for signs of nature's impact, such as changes in soil composition or the microbiome. They might find cell or molecule remnants, not the usual tools. Research, like the work of scientists from Harvard University who created a synthetic cell, shows that creating new forms of life has become a reality. In such an alternative scenario, people could interact with nature more harmoniously, creating ecosystems that meet society's needs without harming the environment. This could lead to more sustainable development, where technology and nature coexist rather than conflict. For example, in 1995, scientists demonstrated that bacteria could be used to break down oil spills, already an example of a beneficial symbiosis. Such technologies could form the basis for creating new life forms adapted to various environmental conditions. The application of biotechnologies in an alternative civilization could also change our understanding of what it means to be human. People could integrate with modified organisms, creating new life forms that combine the best qualities of both humans and nature. In such conditions, one could speak of the creation of a new type of relationship between humans and the surrounding world. Considering that humanity is already actively using biotechnologies, for example, in medicine, one can assume that in an alternative reality, these technologies could develop even faster and more diversely. As a result, civilization could create not just machines, but living beings that perform functions previously assigned to mechanical devices, making our planet more alive and dynamic. An example is the work of MIT scientists who created biologically active materials for use in construction, allowing the creation of not just buildings, but living structures that adapt to changes in the surrounding environment. Quantum technologies represent a field that could transform our understanding of the capabilities of ancient civilizations, which were capable of manipulating fundamental forces of nature. Research indicates that ancient peoples might have possessed knowledge that today seems incredible. For instance, it is possible that in certain historical periods, such as the 5th century BC, philosophers and scientists like Democritus and Epicurus pondered the nature of matter and its structural elements, although they lacked tools for studying it at the microscopic level. Quantum mechanics, which has opened new horizons in understanding the interaction of particles, could have been used in some ancient practice that left no apparent material traces. One theory suggests that such civilizations might have employed mechanisms similar to quantum entangled states for transmitting information or energy over long distances without visible conductors. Modern quantum technologies, such as quantum cryptography, are based on the principle that information can be transmitted using quantum states of particles. This means that ancient peoples might have used similar principles to create communication or control systems that left no physical artifacts. For example, in China during the 6th century AD, when numerous discoveries were made in astronomy and mathematics, it is possible that some of this knowledge was related to understanding the nature of light and its interaction with matter. Quantum field theory, developed in the 20th century, may provide insights into how ancient civilizations could have worked with concepts such as virtual particles. For instance, virtual particles can appear and disappear in vacuum, and if ancient peoples understood this, they might have created tools or rituals that utilize these effects to achieve their goals. In ancient Egypt, where complex rituals aimed at interacting with divine forces were practiced, methods that today we might associate with quantum processes could have been used, although concrete evidence for this is lacking. Research shows that many ancient cultures, including the Maya and Sumerians, had concepts of time and space that today could be linked to quantum ideas. For example, the Maya created complex calendars that might reflect cycles similar to quantum oscillations. In their astronomical observations, possibilities for understanding the nature of light and its phenomena emerge. It is interesting that in ancient India, in texts such as the Ayurveda, practices are mentioned that could be interpreted as manipulations of energies, leaving no material traces, which can be compared to modern quantum concepts. Some researchers suggest that in ancient times, communities might have existed that studied the influence of stars and planets on physical states on Earth. For example, in ancient Greece, in the works of the Pythagoreans, references to harmony and numbers as the foundations of all things can be found. This could be related to quantum resonances, which are still studied in physics today. Thus, it is possible that knowledge about the nature of matter and energy was passed down through oral tradition, and as a result, such civilizations could create management or understanding systems that left no physical trace. Quantum technologies, as we understand them today, could not only explain some mysterious phenomena in history, but also open new horizons for understanding ancient knowledge. It is important to note that the absence of apparent artifacts does not mean that knowledge did not exist. It could have been expressed in formulations, rituals, or even in architecture, where each line and each form could have had its own meaning related to quantum principles. In this context, it is worth considering theories that ancient civilizations, such as the Atlanteans or other mythical peoples, might have possessed advanced knowledge about manipulations of energy and matter, which we are only beginning to understand in the modern world. Each of these examples underscores that if ancient civilizations did use quantum principles, they might have existed in a completely different paradigm where physical artifacts were not the only evidence of their achievements. Scientific research and discoveries in the field of quantum mechanics continue to open new horizons, and perhaps in the future we will be able to better understand how these ideas could have been used in the past. Intelligent beings can develop immaterial technologies that are based on information and consciousness without creating physical structures that can be preserved in the geological record. An example of such technologies is language. Language is a complex system of symbols that allows for the transmission of thoughts, ideas, and emotions. Different peoples have unique linguistic systems that have evolved over thousands of years. For instance, the Hopi language, used by Native American tribes, includes many terms describing time and its perception, which differ from European languages. This demonstrates that culture and the perception of reality can vary significantly depending on language, but the structures of language do not leave material traces. Another example is musical systems. Music, as a form of immaterial technology, conveys emotions and associations, creating unique cultural identities. African music, for example, includes complex rhythms and melodies that are passed down orally, creating a connection between generations, but do not leave behind physical artifacts except possibly recordings on sound recording devices which can eventually disappear. A significant aspect of immaterial technologies is tradition, which transmits knowledge and experience from generation to generation. For instance, in Indian culture, there is a system of Vedas, which are sacred texts that convey philosophical and spiritual teachings. These knowledge are passed down orally and shape worldviews and practices, but do not leave material traces. Education is another immaterial technology. School systems and universities teach students knowledge and skills that shape the future of society. For example, educational reforms in Finland in the 20th century led to the creation of one of the best educational systems in the world, but the methods and approaches to teaching cannot be found in archaeological findings. It is also worth noting philosophy as an immaterial technology that shapes thinking and the perception of the world. Philosophical schools, such as Stoicism or existentialism, developed ideas about the meaning of life and existence that influenced entire epochs. However, like language and music, they do not leave a physical trace. Scientific theories, such as Albert Einstein's theory of relativity, also represent immaterial technologies that change our understanding of time and space, but do not leave material objects. These theories are transmitted through publications, lectures, and discussions, but there are no physical proofs that can be preserved for millions of years. Immaterial technologies can also include digital technologies, such as programming and software development. Over the past few decades, we have witnessed a revolution in information technologies, where programmers' knowledge and skills shape modern digital worlds, such as the Internet. However, programming and code are merely information that can be easily lost if not stored on physical media. Another example is social networks. The emergence of platforms like Facebook and Twitter has changed the way people communicate and interact, creating new forms of communities, but these platforms, being immaterial, can disappear at any moment. Immaterial technologies also include management and organizational methods, such as Agile and Lean, which have revolutionized business practices. These methods allow teams to work more efficiently, but their essence cannot be fixed in physical forms. Technologies based on information and consciousness can develop and evolve, but they remain vulnerable to time and societal changes. There are also examples of cultural practices, such as rituals and ceremonies, that are connected to beliefs and traditions, but do not leave material traces. For instance, such rituals as initiations or weddings are passed down orally and can change over time, but their essence remains immaterial. Immaterial technologies can significantly influence the development of civilizations and cultures, shaping their identity and perception. Planetary consciousness is a concept that reflects the interconnectedness of all people and cultures on our planet, viewing Earth as a single organism. This idea began to actively develop in the mid-20th century as scientists began to realize that all human actions impact the global ecosystem. For example, in 1962, Rachel Carson published the book Silent Spring, which drew attention to the consequences of pesticide use and its impact on nature, highlighting how human activity can threaten ecosystems. In 1983, at the UN conference in Nairobi, the Declaration on Planetary Consciousness was adopted, emphasizing the need for global cooperation to address environmental and social issues. An example of such cooperation is the creation of the World Environment Network, which held a summit in Rio de Janeiro in 1992 to discuss plans for sustainable development. The concept of planetary consciousness also involves understanding that problems such as climate change will not disappear if we act alone. For instance, in 2015, countries signed the Paris Agreement, aiming to limit global warming. Notably, initiatives like the Global Compact of the UN aim to unite business structures and governments to achieve common goals, including sustainable development and environmental protection. Social movements like Greenpeace actively promote the ideas of planetary consciousness, emphasizing that caring for the planet is not just a responsibility, but a necessity for survival. In 2020, participants at the World Economic Forum in Davos discussed the importance of transitioning to sustainable economic models, underscoring the relevance of the concept of planetary consciousness in today's world. From a scientific perspective, this concept is supported by data on global ecosystems, which show how local actions can have global consequences. For example, deforestation in the Amazon not only destroys local ecosystems, but also affects the climate in other parts of the world. The phenomenon of global warming is a vivid example of how actions in one region can have consequences for the entire planet, leading to changes in weather conditions and ecosystems worldwide. Research conducted in 2009 showed that sea levels could rise by up to 1 meter by the end of the century if current carbon emissions trends continue. This underscores that planetary consciousness is not just a philosophical concept, but a necessity for the survival of our civilization. From a cultural identity perspective, planetary consciousness includes recognizing the diversity of cultures and traditions that exist on Earth while preventing isolationism and promoting the exchange of knowledge and experience. In 2006, UNESCO launched the Culture of Peace initiative, aimed at uniting peoples through mutual understanding and respect for various cultural traditions. This also encourages cultural exchange and can lead to the creation of more sustainable societies. Notably, the concept of planetary consciousness is also reflected in art and literature, where creators raise questions about the fate of humanity and its place in the natural world. For example, in the 1990s, artist Christo created the River Project in the US, symbolizing the unity of humans and nature, demonstrating how art can serve as a tool for recognizing our interconnectedness. This concept is actively discussed in modern educational systems, where the focus is on global thinking and responsibility for the future of the planet. In the 2000s, many countries introduced courses on sustainable development and ecology into their curricula, fostering a new generation capable of critical thinking and awareness of global problems. Planetary consciousness is also supported by modern technologies such as the Internet, which allows people from all over the world to exchange information and experience in real time. In 2017, more than 3 billion people were registered as Internet users, creating a platform for global dialogue and cooperation. This concept continues to develop, and its relevance becomes increasingly evident with each passing year as humanity faces new challenges such as pandemics, global conflicts, and environmental disasters. The Gaia hypothesis, proposed by English scientist James Lovelock in the 1970s, posits that Earth functions as a single, self-regulating organism. This concept is based on observations that the biosphere and physical components of the planet interact in such a way as to maintain conditions necessary for life. Lovelock, while working on a project to search for life on Mars, concluded that Earth is not merely a collection of independent systems, but a unified whole where each element influences others. For instance, he noted that the level of carbon dioxide in the atmosphere is regulated by plants and oceans, which absorb the gas and thus help maintain a stable temperature on the planet. In his book Gaia, A New Look at Life on Earth, Published in 1979, Lovelock described how various biological and geochemical processes, such as photosynthesis and volcanic activity, work together to support life. This idea has sparked debate among scientists, as some argue that Earth cannot be entirely self-regulating, while others support the hypothesis, pointing to numerous examples of ecosystem resilience. For example, coral reefs, which support marine biodiversity, also help regulate ocean temperature and oxygen levels. The Gaia hypothesis intersects with the concept of planetary consciousness, which suggests that Earth may possess some form of awareness. Advocates of this idea, such as philosopher and ecologist David Orr, argue that if Earth indeed functions as a single organism, it may imply the existence of a collective intelligence that manages interactions between various forms of life. For instance, in ecosystems dominated by certain plant species, symbiotic cooperation can emerge, strengthening the overall system's resilience. Research shows that climate change and ecological disasters can negatively impact this balance, disrupting self-regulation. For example, a study conducted in 2018 by scientists from the University of California found that a 2 degrees Celsius temperature increase could lead to mass coral reef die-offs, which in turn would affect all marine ecosystems. The Gaia hypothesis has also influenced modern environmental movements, which emphasize the importance of treating nature with care, viewing Earth as a unified system. This concept offers a new understanding of our responsibility towards the planet and can serve as a basis for developing sustainable practices. However, critics of the hypothesis point to the lack of strict scientific evidence and suggest looking at Earth as a complex network of relationships where it is not always possible to isolate intelligence as a separate element. For example, a study conducted in 2009 showed that ecosystems can adapt to changes, but not necessarily in harmony. Thus, the Gaia hypothesis raises numerous questions about the nature of life on Earth and how we can better understand our interactions with the surrounding world. It is important to note that within this framework, Earth can be seen not only as a physical object, but also as a living entity with certain self-regulating mechanisms which compels us to rethink our place within this system. Microbiological collective intelligence is a hypothetical form of consciousness based on the interaction of trillions of microorganisms that form a complex global neural network. In nature, microorganisms such as bacteria, archaea, and fungi exist in vast quantities, and their interactions can create remarkable ecosystems. For instance, a single gram of soil can contain up to 1 billion bacteria, representing thousands of different species. These microorganisms do not merely coexist independently, they interact with each other, forming communities that can exchange information and resources. Research shows that bacteria can communicate with one another through chemical signals known as quorum sensing. This mechanism allows them to coordinate their actions, for example, by forming biofilms that can protect them from adverse conditions. In such communities, microorganisms can act as a single entity, making decisions that ensure their survival. In 2016, a group of scientists from the University of Wisconsin-Madison, led by Professor John D. Gray, published a study demonstrating that bacteria can make collective decisions, choosing the optimal place for colonization. This discovery challenges traditional notions of individual microbial behavior, suggesting that they can function as a unified intelligent system. Moreover, in symbiosis with other organisms, such as plants or animals, microorganisms can influence the behavior of their hosts. For example, research shows that human gut bacteria can alter mood and behavior by producing neurotransmitters like serotonin. This interaction between microbes and hosts underscores the complexity and interconnectedness of life on Earth. There are speculations that all these microorganisms could eventually create something akin to consciousness, combining their knowledge and experience in a global network that would function as a single, intelligent entity. The analogy with the neural network of the human brain becomes evident. Billions of neurons process information and form thoughts, just as trillions of microbes can process information about their environment and adapt to changes. Scientists like Professor David K. Costa from the University of Pennsylvania assert that this network of microorganisms could be capable of learning and memory, given that they can transmit genetic information among themselves through horizontal gene transfer. This means that by studying the behavior and interactions of microorganisms, we can begin to understand how this hypothetical form of collective intelligence functions. For example, experiments with biofilms show that under stress they can change their structure and function, indicating adaptive behavior characteristic of more complex forms of life. Such research opens up new horizons in the study of ecosystems and their role in supporting life on Earth. Ultimately, understanding microbiological collective intelligence can help us better comprehend how ecosystems function overall, and how they can influence climate change, human health, and the resilience of the environment. Each of these connections highlights the importance of microorganisms in the world and their potential role in the creation of complex forms of life. Microbiological collective intelligence remains on the threshold of scientific discovery, opening new prospects for future research in ecology, biology, and even philosophy. Fungal mycelial networks, also known as fungal mycelia, represent complex systems that have existed on Earth for over 800 million years. These networks are formed by thin filaments called hyphae that penetrate the soil and decompose organic matter, providing nutrients to the ecosystem. Mycelium not only plays a crucial role in ecology, participating in decomposition and maintaining soil health, but also functions as a powerful communication system that can transmit information over long distances. Studies conducted in the year 2000 by a group of scientists led by Dr. Dan Hyman from the University of Texas showed that mycelial networks can transmit chemical signals between plants, warning them of potential threats such as insect attacks or diseases. In these networks, hyphae can connect with the roots of trees and plants, forming symbiotic relationships that benefit both parties. Plants receive necessary nutrients, while fungi obtain carbohydrates. Scientists have calculated that 1 square meter of soil can contain up to 100 kilometers of hyphae, creating a vast network. Each type of fungus may have unique properties, making their communication capabilities even more diverse. For example, Armillaria species, known as honey mushrooms, can form mycelial networks covering areas of tens of hectares. In some cases, such networks can connect trees of different species, allowing them to exchange resources and information. This process is known as the underground internet. In 2018, a study conducted at Cornell University confirmed that mycelial networks can accelerate the exchange of nutrients between trees, even if they are far apart. Fungal mycelia can transmit not only nutrients but also biochemical signals, creating a unique ecosystem where organisms interact and support each other. Scientists have even begun to consider the use of mycelial structures to create artificial communication networks that mimic natural systems. For instance, in 2020, a study published in the journal Nature described the use of mycelium to create eco-friendly products, such as packaging that decomposes when no longer needed. Research shows that mycelial networks can be used to create sustainable ecosystems and improve soil quality, opening new horizons in the fields of ecology and sustainable development. In 2021, a group of scientists from MIT stated that mycelial networks could be applied to create new forms of data storage that are more efficient and less harmful to the environment than traditional electronic devices. This approach has sparked interest not only among ecologists but also among specialists in the field of information technology. Thus, fungal mycelial networks, having existed for millions of years, demonstrate an incredible ability to communicate and interact, highlighting their importance in ecosystems and their potential applications in modern technologies. Research shows that mycelium can connect various plant species, creating complex ecosystem links and ensuring the stability of the surrounding environment. Temporal chauvinism is a concept where certain historical events or cultural achievements of one era are considered more significant or important than those that occurred in another era. This phenomenon often manifests itself in the perception of history, where contemporary achievements and technologies are placed above those of the past, leading to a distorted view of the development of human civilization. For instance, one might encounter opinions that the technological achievements of the 21st century, such as the Internet and mobile phones, represent the pinnacle of human progress, while the achievements of ancient civilizations, such as the architecture of ancient Egypt with its pyramids, or the invention of writing by the Sumerians, are ignored or dismissed. Temporal chauvinism can also manifest in the perception of cultural traditions, where contemporary culture is viewed as more progressive and developed compared to traditions that have existed for centuries. This leads to an undervaluation of deep knowledge and practices that have been accumulated over long periods and passed down through generations. For example, traditional farming methods used in various cultures are often rejected by modern farmers who rely on contemporary agricultural technologies, without considering that many of these traditional methods were optimized based on centuries of experience that should not be ignored. Temporal chauvinism can also influence education, where curricula emphasize recent events and achievements, while important historical facts and events from the past are overlooked. This can result in a new generation lacking a comprehensive understanding of their cultural heritage and historical role of their ancestors. In this context, it can be noted that temporal chauvinism often leads to a distortion of historical memory. People may perceive history as a linear process, where each new achievement replaces the previous one, rather than as a complex network of interactions and mutual influences. Such an approach can create an illusion that certain epochs or cultures are outdated and have no value for the present, while in reality they may contain important lessons and wisdom. This phenomenon can also be linked to political and social movements that attempt to rewrite history to fit contemporary ideals, ignoring the diversity of opinions and facts that exist in the historical context. For example, in some countries, the role of certain historical figures may be re-evaluated, leading to a change in views on entire epochs, which in turn can strengthen temporal chauvinism. Additionally, temporal chauvinism can manifest in how we perceive the achievements of other cultures. Often, Western achievements are placed on a pedestal, while significant achievements of Eastern or African cultures are ignored, creating a distorted view of global history. For instance, achievements in mathematics and astronomy made by Arab scholars in the Middle Ages are often overshadowed by European discoveries, despite being key to the development of science in Europe. Temporal chauvinism allows us to forget that each culture and era has made a unique contribution to the overall development of humanity, and ignoring this fact leads to a simplification and even distortion of our common history. As a result, if we are not careful, temporal chauvinism can lead to cultural amnesia, where important aspects of our heritage are lost to future generations. For example, small nations and their traditions may be threatened with extinction if their achievements and history are not recognized and valued appropriately. Temporal chauvinism undermines our ability to learn from the past, and in the end, we risk repeating mistakes that were made earlier. It is important to remember that each era has its own achievements, and ignoring the past due to temporal chauvinism may mean that we lose sight of important lessons that could be useful in the future. In this context, one can provide an example where some modern technologies, such as ecological farming practices, are actually a return to methods used in the past, highlighting the value of historical experience and knowledge. Modern people often tend to consider past epochs as less developed and primitive than they actually were. For instance, many still fail to recognize that civilizations like the Sumerians built the first cities around 4,000 years before our era and introduced a writing system known as cuneiform. The Sumerians invented the wheel, which became a fundamental element in the development of transportation and trade. Their complex mathematical systems allowed them to make precise calculations necessary for agriculture and record keeping. In ancient Egypt, starting from the 3rd millennium before our era, monumental pyramids were constructed, such as the Great Pyramid in Giza, which stands at 146 meters tall. This structure was built using advanced technologies, including a system of inclined planes up to 1.5 kilometers long, challenging the notion of the primitiveness of ancient architects. Ancient Indians created a public sanitation system in Harappa, indicating a high level of hygiene that many modern societies are only beginning to consider. Meanwhile, the Maya civilization in Central America built stone pyramids used for astronomical observations and created calendars with accuracy comparable to modern ones. While Western society during the Middle Ages was shrouded in darkness, the Islamic Golden Age, spanning from the 8th to the 13th century, was a true center of science and culture, where scholars like Al-Khwarizmi developed algebra and promoted astronomy. They preserved and developed the knowledge of ancient Greeks and Romans, which later played a significant role in the European Renaissance. There are numerous examples of ancient technologies surpassing their time, such as Roman aqueducts that supplied cities with fresh water over hundreds of kilometers. Scientific achievements of ancient Greeks, like the works of Archimedes, which form the basis of modern physical and mathematical knowledge, demonstrate that the level of intelligence and engineering thought in antiquity was very high. The idea that there were only primitive societies in the past ignores entire layers of human history where highly developed civilizations created complex social structures and achievements. Scientific research, such as the work of archaeologist Christopher Taylor, shows that in regions like Mesopotamia and the Indus Valley, there were cities with complex urban infrastructure, including drainage systems and centralized water supply. These achievements challenge the modern notion that humanity gradually progressed from simplicity to complexity. Scientific findings, such as discoveries in Chan Chan in Peru, show that the Incas created one of the most complex and advanced cultures in pre-Columbian America, with advanced agriculture and architecture. The fact that many of these societies had rich cultures, including art, literature, and philosophy, often goes unnoticed. As a result, the neglect of these high achievements and complex systems of governance contradicts modern notions of progress and development. Complex aspects of ancient cultures and their achievements, such as the creation of the first legal codes like the Code of Hammurabi, which was compiled around 18 centuries before our era, underscore the level of social organization that many modern societies are only beginning to master. It is important to remember that many ancient civilizations were highly developed and left behind a legacy that continues to influence the present. In this context, the notion of primitive societies becomes not only a simplification, but a serious distortion of historical reality. Cyclicality of history and the possibility of the repeated rise and fall of technological societies throughout the geological history of Earth is a phenomenon that can be observed in various civilizations. For example, Mesopotamia, the cradle of the first cities and writing, experienced numerous rises and falls. The Sumerians, who around 4,000 years before our era invented the wheel and created a system of writing on clay tablets, disappeared under the onslaught of the Akkadians and then became the object of conquest by the Assyrians and Babylonians. As a result, their achievements, such as agriculture and architecture, were adopted and adapted by subsequent cultures. In ancient Egypt, which lasted for more than 3,000 years, we see a similar dynamics. Prosperity during the New Kingdom period was followed by decline when the country was subjected to foreign invasions, such as the conquest by Assyria in the 7th century before our era. No less interesting is the history of the Roman Empire, which in its heyday covered 3 continents, but by the 5th century of our era disintegrated into numerous barbarian kingdoms. The fall of Rome is often linked to economic crises, internal political struggles, and external threats, highlighting the fragility even of the most powerful civilizations. These examples show that technological and cultural achievements can be inherited by subsequent societies, even after the fall of the original bearers of knowledge. scientific research, such as the work of historian Wayne Kay, Griffith emphasizes that cycles of growth and decline can be linked to natural catastrophes, such as climate change, which altered the conditions of life and agriculture. For example, around 2,000 years ago in Central America, the Maya civilization began to experience difficulties due to drought, which led to its decline. Research conducted by a team of scientists led by Matthew Pollard showed that changes in temperature and precipitation could reduce crop yields, contributing to social conflicts and migrations. At the global level, the rebirth of complex societies such as China, India, and the countries of the Near East demonstrates that the fall of one civilization does not necessarily lead to the decline of all humanity. During the period between the 6th and 12th centuries after the fall of Rome, the Islamic Golden Age became a place where knowledge in astronomy, mathematics, and medicine accumulated, which eventually influenced the Renaissance in Europe. Thus, the cyclicality of history is not just the repetition of the same mistakes, but the opportunity for new societies to learn from the past and adapt technological achievements. Research conducted by archaeologists such as Lara Kottering has shown that even at the level of small tribes in different corners of the world, a similar dynamics can be observed. In some cases, such as with the Inca civilization, we see that they used complex systems of terraced farming and irrigation, which were inherited by Spanish colonizers, despite the destruction of their society. The fall of technological societies can be caused by a multitude of factors, from internal corruption and ecological catastrophes to external conquests. History shows that each time a society disappears, another finds a way to adapt and use its legacy. Thus, in Europe, after the fall of the Roman Empire, new forms of government and social structures emerged, which ultimately led to the formation of modern nations. The most significant achievements in the field of technology and art, such as Gothic architecture and mechanisms, were created in conditions when old civilizations were in decline. Humanity, it seems, is constantly oscillating between rise and fall, like a pendulum that cannot stop. Throughout the geological history of Earth, this process repeats again and again, highlighting that each epoch carries both opportunities and risks. As a result, in history, a constant cyclical process is observed where one civilization disappears and another arises using the accumulated experience, which is confirmed by the facts of archaeological finds around the world. The concept of forgotten knowledge illustrates how information about the past could be lost due to global catastrophes, migrations, and cultural collapses. One of the most striking examples of knowledge loss is the fall of the Roman Empire in the 5th century AD, when internal instability and attacks by barbarian tribes, such as the Goths and Vandals, led to the collapse of the social structure. This process resulted in the disappearance of many technologies and scientific achievements, such as aqueducts and heating systems, which were not restored for centuries. Consequently, Europe entered a period known as the Middle Ages, during which literacy and scientific knowledge significantly declined. Meanwhile, in other regions such as Asia and Africa, civilizations were developing, but many of their achievements, such as the astronomical knowledge of the Maya and irrigation technologies of the ancient Sumerians, were forgotten or not passed on to subsequent generations. For instance, in Mesopotamia, where the Sumerians invented cuneiform writing and created the first known writing system around 3000 years BC, many texts were lost due to destructive invasions and natural disasters such as floods and droughts. In the 10th century, when Arab scholars like Al-Farabi and Ibn Sina began collecting and translating ancient texts, they encountered significant gaps in knowledge that had once been widespread. In the East, in China, the Tang dynasty, which existed from the 6th to the 9th century, reached high levels of culture and science, but many of its achievements were not preserved after the dynasty's fall due to political crises. In South America, the Inca civilization, which built an extensive road network and advanced agricultural practices, lost knowledge of their past after the Spanish conquest in the 16th century. Migrations also contributed to the loss of the knowledge. When tribes such as the Huns migrated, they not only transferred their cultural practices, but also destroyed previously existing ones, leading to the disappearance of entire cultural traditions. In India, for example, knowledge of medicine and astronomy passed down from ancient texts gradually disappeared due to foreign rule and cultural changes. As a result of these processes, many achievements of ancient civilizations such as metallurgy techniques, agricultural methods, and architectural innovations became forgotten. This clearly demonstrates how complex relationships between people, their knowledge, and their environment can be shattered in an instant. Knowledge loss was not a one-time event. It occurred over centuries, serving as a reminder of the fragility of human civilization and its achievements. For example, when archaeologists began studying the ruins of Machu Picchu in the 20th century, they found that many aspects of Inca culture, including agriculture and architecture, were at risk of being forgotten. Preserved artifacts such as terraces for agriculture and complex water supply systems testify to the high level of engineering skill, but many details of their use were not passed on to subsequent generations. Therefore, the concept of forgotten knowledge demonstrates how historical events and changes in social structure can lead to the loss of information that was once an important part of human experience. Cosmic consciousness is a concept that encompasses the understanding of a person as part of a vast universal whole, where each individual recognizes their connection to the surrounding world and the universe as a whole. This state of awareness implies not only physical existence, but also a deep understanding of the interaction between people, nature, and the cosmos. In the 20th century, scientists and philosophers began actively exploring this theme, linking it to concepts such as ecology, psychology, and even quantum physics. For example, in the 1970s, physicist David Bohm proposed the concept of hidden order, asserting that everything in the world is connected at a deeper level than we realize. This assertion became the basis for many studies focused on understanding interactions between ecosystem elements and human actions. Meanwhile, in 1988, neuroscientist Roger Penrose described how consciousness could be linked to quantum processes in the brain, raising questions about the nature of perception and existence. Cosmic consciousness suggests that humanity must transcend its narrow understanding of its place in the world, recognizing that our actions can have far-reaching consequences. This is evident in the case of global warming, where human activity leads to climate change, which in turn affects ecosystems and life on the planet. Research shows that the level of carbon dioxide in the atmosphere in 1981 was approximately 388 parts per million, while by 2020 this level had risen to 408 parts per million. This increase leads to changes in weather conditions, rising sea levels, and the extinction of species, which in turn causes social and economic problems. Moreover, in 2003, scientists from the Intergovernmental Panel on Climate Change, IPCC, declared that global warming caused by human activity is one of the most serious threats to our civilization. In this context, cosmic consciousness can help people realize that their actions affect not only themselves, but also future generations. From a psychological perspective, cosmic consciousness can be linked to the state of flow described by psychologist Mihaly Csikszentmihalyi, who claimed that people achieve the highest level of satisfaction when they are fully immersed in an activity which can lead to a deeper understanding of oneself and one's place in the world. In the 2010s, the concept of cosmic consciousness became popular in culture, especially in connection with the increasing interest in sustainable development and environmental protection. For example, the documentary Our Planet was released in 2009 and drew attention to the need for a responsible attitude towards the planet, showing how the actions of each person can affect global environmental problems. In this film, questions of not only ecology but also social justice were raised, asserting that understanding cosmic consciousness should include a concern for other people. Cosmic consciousness can also be viewed through the lens of new technologies and their impact on society. In 2020, during the COVID-19 pandemic, we witnessed how technologies help connect people and create new forms of interaction, even when physically separated. This demonstrates that even in conditions of isolation, humanity can maintain its connection and unity, which is an important aspect of cosmic consciousness. One of the most striking examples is the Zoom platform, which became the primary tool for communication and work during the quarantine, showing how technologies can create new forms of interaction and a sense of shared responsibility. In this context, cosmic consciousness emphasizes the importance of uniting efforts to address global problems such as climate change, pandemics, and social inequalities. In the 12th century, in the Book of Nature by the Arab philosopher Ibn Sina, ideas about the interconnectedness of all things were described, which can also be interpreted as early concepts of cosmic consciousness. In his works, he raised questions about how everything in nature is connected and how this knowledge can help people better understand their place in the world. Research shows that understanding one's connection to the surrounding world can improve mental and physical health, as confirmed by the work of scientists such as Professor Emma Seppala, who in 2017 published results of studies showing how meditation and mindfulness can change one's perception of oneself and the surrounding world. The perception of cosmic consciousness opens new horizons for understanding humanity and its role in the world, where every action and every thought can have significance. In this context, it is important to remember that science and philosophy continue to develop, and new discoveries can help us better understand this complex concept. The hypothesis of panspermia posits that life on Earth could have originated not on our planet, but was brought here from other celestial bodies. This theory gained prominence in the 19th century, but its roots go back to ancient times. For instance, the famous Greek philosopher Antisthenes in the 4th century BC already contemplated the idea that seeds of life could be transported through space. However, modern understanding of panspermia was developed in the early 20th century when astronomers began studying comets and meteoroids. In particular, in 1930, Swedish astronomer Fred Hoyle proposed the concept that microorganisms could survive in space and be transported to Earth. In 2008, a NASA study confirmed that some microorganisms, such as bacteria, can survive in space conditions, lending support to the panspermia hypothesis. In this context, the question of whether intelligent beings that existed in ancient times on other planets could have sent their life to Earth is particularly intriguing. Scientists consider the possibility that highly advanced civilizations could have used spacecraft to transport biological materials, as depicted in various science fiction works. In 2031, when organic molecules were discovered on Saturn's moon Titan, many researchers once again turned their attention to the panspermia hypothesis. These molecules could be associated with processes that occurred in other parts of the solar system, raising the question of the possibility of life beyond Earth. One of the most discussed topics is the possibility that such intelligent beings could have left traces on Earth, which is reflected in various myths and legends. For example, ancient Sumerians depicted their gods as beings who descended from the heavens. Similar beliefs can be found in other cultures, such as Egyptian or Native American, where gods are often described as possessing non-earthly characteristics. In 2015, a study conducted by a group of scientists led by Dr. Ron Evans showed that some artifacts from ancient civilizations, such as statues and drawings, could indicate contacts with extraterrestrial beings. This discovery once again raises the question of how real the idea is that life on Earth could have been the result of intervention by intelligent beings from other worlds. It is important to note that panspermia does not necessarily imply that life on Earth was created by extraterrestrial civilizations, but rather that conditions for the emergence of life were brought from space. It is also worth considering that some scientists oppose this theory, arguing that life could have emerged on Earth independently. For example, in 2001, biochemist Joseph Ladenburg criticized panspermia, asserting that the lack of specific evidence and the complexity of biochemical processes cast doubt on this hypothesis. Nevertheless, Panspermia remains a relevant topic for scientific research, and new discoveries in astronomy and biology could lead to a better understanding of the origin of life. For instance, in 2020, scientists from the University of California in Los Angeles discovered that some microorganisms can use sunlight to synthesize organic compounds, opening new horizons for the study of life's possibilities in space. In this context, the panspermia hypothesis provides a wide range of perspectives for studying both the origin of life on Earth and the possibility of the existence of intelligent beings in other parts of the universe. At present, the discovery of organic molecules on other planets and moons only confirms that the question of extraterrestrial life remains open and requires further research. The concept of cosmic intelligence posits the existence of a universal consciousness that can manifest in various material forms on different planets. This idea finds its roots in the works of philosophers such as Benedict Spinoza, who in the 17th century proposed the concept of pantheism, asserting that God and nature are one and the same. Contemporary researchers such as astrophysicist Neil deGrasse Tyson consider the possibility of the existence of intelligence as a system capable of adapting and evolving depending on the conditions of the planet. For example, on Earth, we observe how various ecosystems give rise to unique forms of intelligence, from dolphins to primates, each developing its own forms of communication and social interaction. On other planets, such as Europa, a moon of Jupiter under the ice, there may be an ocean with conditions conducive to the emergence of life, creating the possibility for the appearance of intelligent forms different from those on Earth. In the 12th century, the Arab philosopher Avicenna spoke of the existence of a higher intelligence that governs the world. This can be linked to modern concepts of cosmic intelligence, which may be distributed throughout the universe, interacting with various forms of life. Research on exoplanets shows that in our galaxy alone, there are more than 200 billion stars, many of which have planets in the habitable zone, increasing the probability of the existence of diverse forms of life and possibly intelligence. In the 20th century, in the works of scientists such as Carl Sagan, the question was raised about how intelligence can manifest in various conditions. Sagan asserted that intelligence can evolve not only based on carbon compounds, as on Earth, but also in other chemical formations, such as silicon, opening new horizons for understanding life and intelligence. In the year 2001, an article was published in the journal Astrobiology that considered the possibility of life based on ammonia, once again emphasizing the diversity of conditions for the development of intelligence. Furthermore, the concept of cosmic intelligence also touches on questions about how different civilizations can interact, exchanging knowledge and technologies across cosmic distances. In this context, it is worth remembering the SETI project, which since the 70s of the last century has been engaged in the search for signals from extraterrestrial civilizations. Within this project, scientists analyze radio signals from space, trying to find patterns that could indicate the existence of intelligent life. Observations of exoplanets such as TRAPPIST-1 show that in a system consisting of 7 planets, 3 are in the habitable zone, making them potential candidates for the search for life. Considering all these aspects, the concept of cosmic intelligence becomes not just a hypothetical possibility, but a very real one that attracts the attention of scientists, philosophers, and science enthusiasts around the world. Scientific research, such as the analysis of the atmospheres of exoplanets using the Hubble Space Telescope and its successor, the James Webb Space Telescope, continues to expand our horizons in understanding life in the universe. It is interesting that in the 21st century, scientists such as astrophysicist Michio Kaku propose theories about cosmic intelligence that may be more advanced than we can imagine, possessing the ability for interstellar travel. In this context, the concept of intelligence goes beyond biological forms and encompasses broader concepts, such as collective consciousness of civilizations. This raises the question of how we, as humanity, can prepare for interaction with such forms of intelligence if they exist. Perhaps we are on the threshold of discovering new horizons in understanding consciousness and its manifestations in the cosmos. In this context, it is important to note that modern science continues to seek answers to questions about the nature of intelligence, its origins, and the possibilities it may open for humanity. For example, in 2023, scientists from MIT presented a model that suggests that intelligence can be not only individual but also collective, and this could significantly influence our understanding of life in the cosmos. Quantum entanglement is one of the most intriguing phenomena in quantum physics, with the potential to have enormous consequences for information transmission over cosmic distances. This phenomenon, described by Albert Einstein as spooky action at a distance, occurs when two or more particles become so interconnected that the state of one particle instantaneously affects the state of another, regardless of the distance between them. For instance, in 2012, a group of physicists from the Argonne National Laboratory under the leadership of Dr. Jeffrey Freeman conducted an experiment where they entangled a pair of photons and found that changing the state of one photon immediately affected the state of the other, even when they were more than 5 kilometers apart. This discovery challenges traditional notions of information transmission, which rely on electromagnetic waves and other forms of communication that require time to travel between points. Quantum entanglement could potentially be used for transmitting information using quantum bits or qubits, which can exist in a state that is both 0 and 1 simultaneously, making them much more powerful than classical bits. One of the most discussed applications of quantum entanglement is quantum teleportation, a process by which information about the state of a quantum system is transmitted from one location to another without transmitting the system itself. This process was first demonstrated in 2001 when a group of scientists from the University of Western Australia, under the leadership of Dr. Wan T. Coker, achieved quantum teleportation of an atomic state using entangled photons. Quantum entanglement could enable intelligent beings to communicate over vast distances, such as between stars, bypassing the limitations of traditional communication technologies like radio waves, which are limited by the speed of light. In 2013, researchers from the Massachusetts Institute of Technology, under the leadership of Dr. Roland K. Carter, developed a theoretical model suggesting that quantum entanglement could be used to transmit messages between two galaxies with minimal delay. This model is based on the assumption that intelligent beings can manipulate entangled states, creating a sort of quantum internet that allows for instantaneous information exchange. A key aspect of quantum entanglement is that it does not violate the principle of causality, as information is not transmitted faster than light. Instead, manipulating the state of one particle causes an instantaneous reaction in another, creating the illusion of information transmission. Quantum entanglement also opens new horizons in the fields of quantum computing and cryptography, enabling the creation of systems that are virtually unbreakable, as any interference with entangled particles would destroy their state. In 2018, a team of physicists from the University of Texas at Austin, under the leadership of Dr. Stephen W. Tinker, demonstrated that quantum entanglement could be used to create an absolutely secure communication channel that cannot be intercepted. Thus, quantum entanglement not only changes our understanding of physics, but also opens up possibilities for developing new communication technologies that could fundamentally alter our perception of communication over cosmic distances. Research in this area continues, and scientists around the world are striving to develop theories and experiments that could confirm or refute the possibility of using quantum entanglement for transmitting information between intelligent beings at significant distances. For example, in 2020, a group of scientists from the University of California, Berkeley, under the leadership of Dr. Emily S. Griffiths, presented the results of an experiment where they entangled 3 photons and demonstrated that changing the state of one photon immediately affected the state of the other 2, opening new horizons for quantum communication. Ancient civilizations have always sparked lively interest due to their achievements and unique features. Take, for instance, the Sumerian civilization, which emerged in the region of Mesopotamia around 4,000 years before our era. The Sumerians were the first to create a writing system known as cuneiform, which allowed them to record laws, trade agreements, and historical events. By the 3rd millennium before our era, the Sumerian city-states of Ur and Uruk already had complex administrative structures that managed their economy and social life. They also developed a mathematical system based on the 60-minute hour and 60-second minute, which we still use today. Compare this with the ancient Egyptians who, starting from the 3rd millennium before our era, built monumental pyramids like the Great Pyramid of Giza, which stands at 146 meters tall. These structures became symbols not only of pharaohs but also of a complex religious system where the afterlife played a key role. The Egyptians created a hierarchy of gods, with Osiris and Isis occupying central positions, determining the moral and ethical norms of society. The Greek civilization, which emerged later in the 8th century before our era, made significant contributions to philosophy and science. The Greeks pondered questions about the nature of humanity, our place in the world, and the essence of the divine. An example of this is the work of the philosopher Plato, who described ideal forms and the concept of justice in his dialogues. In the same period, in the 5th century before our era, democracy developed in Athens, laying the foundation for our modern understanding of civil rights and freedoms. The Roman Empire, which emerged in the 1st century before our era, demonstrated how to manage vast territories through laws like the 12 Tables, which became the basis of Roman law. The Romans also developed a system of aqueducts to supply cities with fresh water, improving living conditions and health. Meanwhile, in India, the Indus civilization, with its cities of Harappa and Mohenjo-daro, was built with a well-thought-out urban planning and drainage system, indicating a high level of urban development. The Indians also developed a complex number system that later influenced European mathematics. In China, starting from the 3rd millennium before our era, the Shang dynasty developed a unique culture using bronze casting and hieroglyphic writing, which laid the foundation for future dynasties and cultural achievements. It is important to note that all these civilizations faced internal and external conflicts that often led to their decline, as was the case with Mesopotamia, where struggles for resources and power resulted in constant wars. The question of how ancient civilizations defined their identity and place in the world remains relevant today. Ancient peoples sought to understand their existence through religion, art, and science, creating a rich heritage that continues to influence modern society. Each of these aspects reveals complex interactions between humans and their environment, as well as how philosophical ideas were formed based on practical needs and cultural traditions. Reflections on the nature of power, justice, and human existence have become the basis for many contemporary discussions and research, underscoring the importance of studying ancient civilizations for understanding our time. Scientific research, such as excavations in Ur, continues to uncover new facts about the life of the Sumerians, allowing us to better understand their contribution to world history. When studying the hypothesis of the multiple origins and extinctions of intelligent life on Earth, complex existential questions arise, prompting us to reflect on the nature of humanity and its place in the universe. One of the main themes concerns how many times intelligent life could have emerged and disappeared over the past 4 billion years. Scientific data indicate that life on Earth appeared approximately 3.5 billion years ago, when simple single-celled organisms began to colonize the planet. These organisms, such as cyanobacteria, played a crucial role in creating the oxygen-rich atmosphere, paving the way for more complex forms of life. But what if intelligent life, similar to ours, existed earlier and became extinct? The question of what factors could have contributed to these cycles leads us to examine the impact of catastrophic events, such as asteroid impacts or volcanic eruptions. One of the most well-known examples is the asteroid impact that occurred around 66 million years ago, leading to the mass extinction of dinosaurs. This event could have wiped out intelligent species if they existed at that time. Research shows that such catastrophes may not be the only factors. Climate change, ecosystem shifts, and the actions of intelligent beings themselves also play a significant role in the survival or extinction of species. Given that Homo sapiens appeared only around 200,000 years ago, the question arises: how many times and in what forms could intelligent life have existed before us? Scientific research, such as the work of paleontologists studying fossil remains, shows that intelligent beings could have evolved in various conditions, from tropical forests to arid steppes. This raises the question of how diverse life on Earth could have been and what factors influenced its evolution. Paleoecological studies, for example, show that in different geological epochs, climate and living conditions changed, which could have contributed to the emergence and extinction of various species. It is also important to consider the possibility of intelligent life existing in other conditions, such as in oceans or under ice caps. These scenarios raise the question of how intelligent beings might have interacted if they existed simultaneously at different stages of development. Could they have exchanged knowledge or cultures, or did their paths intersect only at the level of conflicts? The question of how intelligent life could have interacted with its environment also generates interest. One example is the impact of humans on ecosystems, which led to the extinction of many species, including megafauna such as mammoths, which went extinct around 10,000 years ago. This raises the question of what would happen if humanity disappeared. What new species would emerge in its place, and how would the planet change? The hypothesis of multiple origins of intelligence also leads us to ponder what makes us human. If intelligent life arose and disappeared, perhaps in each new iteration it developed differently. What were the values and culture of these civilizations? Were they capable of creating technologies similar to ours, or did their development follow a completely different path? These questions go beyond science and touch on philosophy. For example, researcher David Chalmers discusses the problem of consciousness and how it might have evolved in different conditions. The question of the universality of human experience remains open. If intelligent life really arose several times, what are the chances that it will return to the same level of development? Are there universal principles that promote the evolution of intelligence, or is each emergence unique and unrepeatable? All these questions further emphasize that understanding our place in the history of Earth and the universe requires deep analysis and reflection. Scientists, such as astrobiologists, study the possibility of life on other planets, opening new horizons for contemplating what it means to be an intelligent being. Each new discovery in the field of exoplanetology, for example, confirms that conditions for the emergence of life may not be unique to Earth. Ultimately, the hypothesis of multiple origins of intelligence poses many questions about how we perceive our existence and the prospects for intelligent life in the future. It is important to remember that science continues to develop, and new discoveries can change our understanding of these existential questions. We are still in the early stages of scientific exploration of these important questions for humanity, and each new discovery brings new data for reflection. The concept of cosmic loneliness for humanity is based on the idea that despite the abundance of stars and potentially habitable planets in the Milky Way, we have not yet found any traces of extraterrestrial civilizations. This concept is actively discussed among astronomers and scientists, such as astrobiologist Dr. David Katz, who points out the vast number of exoplanets discovered with the help of the Kepler telescope, which has been orbiting Earth since 2009. Today, astronomers have confirmed the existence of more than 4,000 exoplanets, of which 2,200 could be in the habitable zone where conditions are suitable for life similar to Earth. However, the absence of clear signals or artifacts from these civilizations makes us wonder if we might be alone in the universe. If we were to find traces of ancient non-human civilizations, this could fundamentally change our perception of ourselves and our place in the cosmos. In 1993, researcher Dr. Carl Sagan proposed a hypothesis that highly advanced civilizations may exist, but they are either unable to communicate or consciously avoid contact. If we were to find, for example, the remains of a spacecraft or artifacts on other planets, this would be akin to the discovery of a new continent for medieval Europeans. We would understand that we are not the only intelligent beings in the universe, which could evoke both wonder and fear. In 1981, astronomers using the Arecibo radio telescope received a signal known as the Arecibo signal, which came from the direction of the star Hercules and lasted only a few seconds, but became a symbol of the search for extraterrestrial life. If we were able to discover traces of civilizations that existed millions of years ago, this would not only elevate our status in the cosmos, but also change our understanding of time and evolution. We would see that other civilizations could have reached high technologies and disappeared, leaving behind only ruins. For example, on Mars, where the Curiosity and Perseverance missions were conducted, traces of ancient rivers and lakes were found, which could have supported life, but now it is just a desert. If we found evidence of intelligent life, this would challenge our understanding of what it means to be human and what a civilization is. In this context, it is worth mentioning the SETI, Search for Extraterrestrial Intelligence project, which has been searching for radio signals from other civilizations since the 1970s. The results of this program show that we have not found clear signals, which only strengthens the idea of cosmic loneliness. The discovery of traces of ancient civilizations could not only confirm that life exists in other forms, but also show that we are all part of a single cosmic history, which raises deep philosophical and scientific questions about our future. For example, if we found technologies that allowed us to travel between stars, this could open new horizons for humanity. It is important to note that each new discovery in astronomy and planetary science, whether it is the discovery of water ice on the Moon or evidence of ancient oceans on Mars, brings us closer to understanding how life might look in other parts of the universe. Scientific research, such as the analysis of data from the Hubble telescope, has shown that within our galaxy there could be billions of potentially habitable planets. If we were to find traces of civilizations that could have existed billions of years ago, this would challenge our understanding of time and evolution. Ultimately, the question of whether we are alone in the universe remains open. Each new step in space research, whether it is the launch of a new telescope or the analysis of samples from the Moon, could lead to unexpected discoveries. The study of cosmic heritage encompasses not only the physical legacy left by preceding civilizations, but also the philosophical aspects that influence our contemporary understanding of humanity's role in the world. The question of the responsibility that modern people bear as potential continuers of the line of intelligent life on Earth, which has existed long before us, is becoming increasingly relevant. For example, the ancient Sumerians who lived in Mesopotamia around 5,000 years ago created the first written language and established the foundations of law and order. Their achievements in astronomy and mathematics laid the groundwork for many modern sciences. However, they also faced environmental problems related to irrigation and soil depletion, which may have contributed to their decline. In this context, it is important to recognize that modern humanity has inherited not only the achievements, but also the mistakes of our predecessors. There are examples of highly developed civilizations, such as the Maya, who achieved significant successes in astronomy and architecture, but also collapsed due to environmental catastrophes and social conflicts, serving as a warning for our time. Scientific research by scholars like Dr. Jared Diamond shows that environmental problems often play a key role in the fall of civilizations. In his book, Collapse: How Societies Choose to Fail or Succeed, he describes how human activity affects the environment and raises the question of whether we can avoid the mistakes of the past. Modern science, such as ecology and climatology, provides us with tools to understand how to prevent environmental catastrophes and preserve the planet for future generations. It is important to note that philosophical concepts of responsibility, such as global ethics, are beginning to occupy a central place in discussions about the future of humanity. Understanding that we are not just heirs but also guardians becomes increasingly relevant in the face of climate change and biodiversity loss. The 18th century saw the emergence of ideas about the rights of nature, when philosophers like Jean-Jacques Rousseau argued that humans should live in harmony with nature. Inspired by these ideas, modern society should recognize its role as stewards of the Earth, taking into account that the planet's resources are not infinite. Sustainable development, whose principles began to take shape at the end of the 20th century, is oriented towards giving future generations the opportunity to live decently without harming the environment. It is important to understand that the ecosystems of Earth are interconnected. The destruction of one species can trigger a chain reaction affecting many others. For example, the disappearance of bees, which pollinate a third of the world's food crops, could lead to a global food crisis. In this context, it is necessary to realize that our actions today determine the future, not only for us, but also for future generations. Reflecting on the legacy of our ancestors, it is important to consider that their experience can help us avoid mistakes. The 18th and 19th centuries were a time of active study of nature, when scientists like Charles Darwin began to form ideas about how species evolve and adapt. These ideas about natural selection and evolution highlight that life on Earth is the result of billions of years of changes and adaptations, raising the philosophical question: what role do we want to play in this process? If humanity does not recognize its responsibility towards nature and does not learn from the past, this could lead to the repetition of tragic mistakes. In particular, the active use of fossil fuels without considering their finite nature is already causing significant climate changes. A study conducted by the Intergovernmental Panel on Climate Change in 2006 showed that the average temperature on the planet has already risen by 0.8 of a degree Celsius compared to pre-industrial levels. This leads to more frequent and intense natural disasters such as floods and hurricanes affecting millions of people around the world. The key point is that modern technologies and knowledge give us the ability to act more responsibly, but this requires not only the efforts of scientists but also changes in the consciousness of each person. It is important to understand that each of our decisions, from the choice of products to the consumption of energy, has consequences. In this context, philosophical reflections on cosmic heritage become an integral part of our choices and actions. Humanity can either continue on the path of self-destruction or turn to a more harmonious coexistence with nature, taking into account the lessons left by ancient civilizations. We must realize that the heritage is not only in the achievements but also in the responsibility for the future. The study of metaphysical questions related to consciousness and reason in the context of the possible existence of non-human forms of intelligence on Earth provokes numerous debates and contemplations. The first mentions of such reflections can be found in ancient Greek philosophy, where thinkers such as Plato and Aristotle pondered the nature of reason and its connection to the material world. For instance, Plato, in his dialogues, described a world of ideas that could be perceived as something akin to non-human intelligence. In the 20th century, these reflections gained new resonance with advancements in cognitive sciences and artificial intelligence. Researchers like Daniel Dennett and David Chalmers raised questions about the place of consciousness in the context of machine intelligence. Chalmers, in his book The Hard Problem of Consciousness, asserts that the existence of consciousness transcends purely physical explanations, which may imply its manifestation in other forms of life that we currently do not comprehend. In this context, the question of paleocontact, the theory that ancient civilizations could have interacted with non-human beings possessing high intelligence, is intriguing. This idea finds resonance in the myths of various cultures where gods and mysterious creatures, such as the Anunnaki in Sumerian mythology or the gods of the ancient Egyptian pantheon, are endowed with human qualities and reason, but are not humans themselves. Some researchers, like Zecharia Sitchin, claim that the Sumerians could have received knowledge from extraterrestrials, raising the question of whether there might have existed intelligent beings on Earth that were not human and preceded modern forms of life. Additionally, in science fiction, from the works of Herbert Wells to contemporary authors like Arthur C. Clarke, the concept of the existence of extraterrestrial intelligences capable of influencing the development of human civilization is often explored. These ideas raise numerous questions about what constitutes intelligence and consciousness. Can one consider intelligence to be the abilities that manifest in complex social structures, as seen in some dolphin or bird species? Or does true intelligence require self-awareness, as in humans? Scientific research in zoology and ethology demonstrates that many animals possess high cognitive abilities, challenging traditional notions of reason. For example, birds and dolphins exhibit complex forms of communication and social behavior which may indicate the presence of some form of consciousness. Concurrently, the question of the metaphysical aspects of reason raises the philosophical concept of panpsychism, which posits that consciousness is present in all things, potentially offering insight into non-human intelligence. This idea has roots in ancient philosophy and finds support in modern scientific research aimed at explaining the nature of consciousness. Studies in neurobiology show that even simple organisms, such as single-celled organisms, can exhibit signs of adaptive behavior, challenging the clear boundary between reason and instinct. There are even theories suggesting that reason may not be exclusive to living beings, but could also be present in non-living nature, opening new horizons for our understanding of intelligence. Some researchers, like neuroscientist V.S. Ramachandran, argue that studying the brain could lead to understanding how consciousness emerged and whether other forms of intelligence have ever existed on our planet. Meanwhile, archaeological findings such as those at Stonehenge or ancient megaliths spark speculation about whether ancient people had their own unique perception or interaction with the world, which could imply the existence of other highly developed forms of reason. Unidentified artifacts and mysterious structures, such as the pyramids in Giza and ancient temples in Mesopotamia, raise questions about the role non-human intelligences or unknown civilizations might have played in their creation. Some theories even suggest that certain ancient texts, like the Vedas or Sumerian cuneiform tablets, might contain indications of knowledge obtained from higher forms of intelligence that may have once existed on Earth. Scientific research, such as archaeoastronomy, shows that ancient people could have possessed knowledge about stars and the cosmos that seems incredible to us today. The question of the metaphysical aspects of reason and consciousness in the context of potential non-human forms of intelligence remains open and is reflected in scientific and philosophical debates. Ultimately, this question not only raises interest in the past, but also in how we perceive intelligence and consciousness in the modern world. Studying the traces of ancient civilizations is inextricably linked to ethical aspects that are becoming increasingly relevant in today's world. On one hand, archaeology strives to uncover the mysteries of vanished cultures, while on the other, it is crucial to recognize that each discovery may represent potential cultural heritage. A key factor is respect for local traditions and culture, which may be affected during excavations. For instance, in the first half of the 20th century, an archaeological expedition in Peru, led by American scientist Hiram Bingham, resulted in the discovery of Machu Picchu. But the methods used during the excavation sparked protests from the local population. The destruction of graves and artifacts that held spiritual significance for the local residents continues to raise questions about the ethics of conducting such research without the consent of indigenous peoples. In the 21st century, many researchers began to consider the opinions of local communities, as evidenced by examples such as the work of archaeologists in Egypt, where local residents are actively involved in the protection and study of their cultural monuments. Moreover, it is important to note that finds are not always simply loot for science. For example, in the 2000s in Iraq, after the fall of Saddam Hussein's regime, there was widespread looting of museums and archaeological sites, highlighting the importance of protecting cultural heritage. According to UNESCO estimates, more than 15,000 artifacts were stolen in Iraq, many of which were unique samples of ancient art. This destruction not only damaged the scientific community but also deprived Iraqi citizens of their historical identity. Modern archaeologists must adhere to strict ethical norms, including adherence to the principles of First Nation and cultural competency, to respect and protect the cultural rights of the population. It is also important to consider that many ancient civilizations, such as the Maya or the Incas, left a rich legacy that is not only of scientific interest but also a part of the identity of contemporary populations. For example, the Maya, who created complex calendars and architectural structures, left behind not only artifacts but also a living culture that continues to exist and develop in Central America. In this context, the interaction between scientists and local communities becomes crucial, where archaeologists should act as partners rather than conquerors. Furthermore, ethical norms in archaeological research should include requirements for the return of artifacts to their historical homeland, as demonstrated by cases of the return of art objects from European museums to their countries of origin. For example, in 2020, Germany returned 8 artifacts from its museum to Nigeria, which became a significant event in the history of relations with cultural heritage. These examples show that ethics and respect for cultural heritage should become fundamental principles in archaeology. Involving local residents in research projects and their participation in the protection of their own history helps not only to preserve the heritage, but also to strengthen social justice, which is an important aspect in today's world. Ethical approaches in archaeology become an important tool, allowing not only to study but also to respect cultural traditions that have survived for centuries. It is important to understand that artifacts do not exist in a vacuum, but are part of living history that continues to develop. Respect for the culture and history of other peoples, as well as ethical practices in archaeology, can contribute to a deeper understanding of our common human heritage. One of the striking examples is the work of American archaeologist Dr. Richard Black, who in 2005 conducted research in Paraguay, collaborating with local tribes to restore their historical heritage. As a result of his work, artifacts were found that helped local residents understand their cultural identity. It is important to remember that each research should be conducted with consideration for the opinions of those whose heritage it studies. The concept of cosmic ethics examines moral obligations between intelligent species that may exist in vast temporal and spatial distances. This idea began to take shape in the late 20th century when scientists like astronomer Carl Sagan and philosopher John Searle started discussing the possibility of extraterrestrial life and its potential interactions with humanity. Within this framework, not only are ethical aspects of interaction with extraterrestrial civilizations considered, but also those with future human generations who may hold entirely different moral views. For instance, if we discover extraterrestrial life, what are our moral obligations towards them? Should we respect their right to existence and uniqueness, even if they differ significantly from us? A key aspect is the temporal gap. If we establish contact with a civilization preceding our development, is this not an interference with their natural progress? A scientist from the University of California, Professor David Chalmers, argues that such interactions could pose ethical dilemmas similar to those encountered in the history of colonization, where more advanced cultures impose their values on less advanced ones. On the other hand, there is a view that we should treat extraterrestrial intelligent beings as equals, with the right to their cultural and moral norms. However, as philosopher Terry Eagleton writes, ethical obligations may vary depending on the level of development of civilizations. If one civilization possesses technologies capable of harming another, the question arises of how to prevent potential conflicts. In this context, it is important to remember the concept of cosmic responsibility. the idea that more advanced civilizations should protect less advanced ones from threats, even if this requires intervention. In the context of cosmic ethics, the question of how human actions on Earth can affect other planets and their ecosystems is also considered. For example, planned missions to Mars raise concerns about potential contamination and interference with potential ecosystems. In this regard, astrobiologists like Dr. Christopher McKay emphasize the importance of adhering to principles of planetary protection, aimed at preventing Earth microbes from contaminating other worlds. The concept of cosmic ethics also touches on issues related to artificial intelligence and its development. As philosopher Elon Musk asserts, if we create intelligent machines, our ethical obligations towards them should also be considered. There are concerns that if we do not develop clear ethical norms, artificial intelligence could lose control and pose a threat to both humanity and other beings that may come under its influence. It is important to note that cosmic ethics is not limited to questions of extraterrestrial life, but also includes moral obligations towards future generations. Philosophers like Hans-Joachim Schmidt argue that we are obligated to consider the interests of future people when making decisions about resources and ecology. For example, climate change caused by human activity could have a devastating impact on the planet, putting future generations at risk. The concept of cosmic ethics thus provides us with an opportunity to rethink our moral obligations, not only in the context of interaction with extraterrestrial civilizations, but also in relation to the future of humanity. This field remains actively researched, and many scientists, such as Dr. Susan Blackmore, call for the creation of international norms and standards that can take into account ethically significant aspects of interaction with other intelligent species and future generations. The roots of cosmic ethics lie in philosophical reflections on the nature of morality and responsibility, making this topic relevant not only for the scientific community, but for society as a whole. The ethical norms we establish today could have a significant impact on future interactions with other intelligent beings. The concept of heritage for the future encompasses a wide range of aspects related to the preservation of cultural, historical, and natural resources for future generations. This heritage includes not only material objects such as architectural monuments, works of art, and artifacts, but also intangible elements such as traditions, customs, languages, and knowledge that shape the identity of various peoples. It is important to note that the global concept of heritage for the future is based on principles of sustainable development, which implies caring for resources not only in the present, but also in the long term. For example, in the 20th century, many countries recognized the need to protect their cultural heritage, which resulted in the creation of international organizations such as UNESCO, established in 1945. UNESCO actively engages in the protection and promotion of World Heritage Sites, and today there are more than 1,200 places on the list that represent outstanding examples of architectural, cultural, and natural significance. One of the most striking examples is the Great Wall of China, construction of which began in the 3rd century BC and continued until the 17th century. This magnificent monument not only serves as a symbol of the People's Republic of China, but also testifies to the engineering genius and diligence of millions of people who participated in its creation. It is important to remember that heritage for the future is not a static process, but a dynamic concept that requires constant updating and adaptation to changing conditions. For example, climate change threatens many cultural heritage sites, such as ancient cities and archaeological sites, which may be destroyed due to rising sea levels or extreme weather conditions. In response to these challenges, scientists and experts are developing new methods of conservation and restoration of monuments, applying modern technologies such as three-dimensional scanning and virtual reality to create digital archives that allow cultural objects to be preserved in their original form. This approach not only protects heritage from destruction, but also makes it accessible for study and appreciation by future generations. In this context, it is worth mentioning that many countries have already begun to integrate heritage protection issues into their educational programs, which helps to instill in young people an awareness of the importance of preserving cultural and historical values. For example, in Norway in the early 2000s, a program was implemented to study local heritage in school curricula, which helped children better understand their culture and history. Additionally, heritage for the future includes natural resources such as biodiversity, which is the basis for the existence of ecosystems and, consequently, life on Earth. The protection of unique ecosystems such as the Amazon rainforest or coral reefs requires the integration of efforts from various countries, as many of these resources are threatened due to human activities, including deforestation and pollution. In recent decades, there has been a growing interest in environmental and sustainable development issues, which has led to the creation of numerous initiatives aimed at protecting natural heritage. For example, in 2009, within the framework of the Convention on Biological Diversity, a strategy for the protection of global biodiversity was adopted, which is aimed at preserving natural ecosystems and their resilience to climate change. It is important to note that heritage for the future requires not only actions from governments and organizations, but also active participation of local communities. These communities play a key role in preserving cultural traditions and natural resources, as they are the keepers of knowledge and experience passed down from generation to generation. Thus, heritage for the future becomes not just a task, but a common cause that unites people, cultures, and nations. Examples of successful heritage protection projects demonstrate that joint efforts can lead to significant results in the preservation of both cultural and natural heritage, which in turn affects the quality of life for future generations. In this context, it is worth noting that in 2020, more than 100 countries signed an international agreement on the protection of cultural heritage in the face of global threats, which underscores the importance of collective responsibility for the preservation of our common heritage for future generations. Creating long-term messages for future civilizations that may emerge on Earth after the extinction of humanity is a complex task requiring a thoughtful approach and a deep understanding of human nature and our history. One of the most well-known examples of such an approach is the Message to the Future project, initiated in the late 20th century by scientists and philosophers who aimed to leave a legacy for future generations. In the early 2000s, within the framework of this project, a time capsule was created containing information about human culture, language, science, and technologies. It included sound recordings, images, and texts that were to be accessible after 10,000 years. Researchers were aware that language and symbols could change, so they used universal concepts such as mathematics and physics to convey the main ideas. Meanwhile, ancient civilizations like the Sumerians and Egyptians left their messages in the form of cuneiform and hieroglyphs on clay tablets and stone walls. These records, which have endured for millennia, provide insights into the lives, religions, and politics of those times. For instance, Sumerian tablets dating back to the 3rd millennium BCE contain not only economic records but also myths like the Epic of Gilgamesh, which tells of the quest for immortality. This demonstrates that previous civilizations also sought to preserve their knowledge and experiences for future generations. In the 21st century, scientists like Dr. Benjamin Lang from the Massachusetts Institute of Technology raised the question of how to create long-term messages that could survive our time. He proposed using durable materials such as hard stone plates or special metal alloys that could preserve information for thousands of years. At the same time, Lang emphasized the importance of clarity and universality of the message so that even after many generations, future civilizations could understand its essence. Additionally, it is necessary to consider the possibility of climate change and natural disasters that could affect the preservation of these messages. For example, messages placed in underground repositories could be more protected from external influences than those on the surface. It is important to note that the creation of long-term messages requires not only technical knowledge but also philosophical reflection. What is the purpose of these messages? What do we want to convey to future civilizations? These questions were raised in the 20th century when the first time capsules, such as the one in St. Louis, were created in 1954. It contained objects that, according to the creators, represented everyday life of that time, including magazines, toys, and even clothing. However, as practice showed, not all of these objects were understood by future generations, highlighting the importance of universality and clarity in creating long-term messages. Scientific experiments, such as the time capsule in space with the Voyager spacecraft, launched in 1977, also serve as an example. It carries a golden record with sound and image recordings representing the diversity of life on Earth, and is intended for extraterrestrial civilizations. This record, like the messages for future generations, should be understandable regardless of time and place. Researchers are working on creating information systems that can adapt to changes in language and culture so that their messages do not lose their meaning over time. Scientific work in this area leads to the thought that even if humanity were to disappear, traces of our civilization could continue to exist. Ultimately, by leaving messages for future civilizations, we not only strive to preserve our history, but also seek to understand our role in the vast expanse of time and space. Deep time information repositories, such as genetic codes, geological layers, and artifacts, can preserve knowledge for millions of years and serve as a bridge between civilizations separated by geological epochs. An example of such repositories is DNA, which stores information about biological species and their evolution. Genetic data extracted from ancient remains allows scientists to reconstruct the picture of life on Earth, such as the DNA of the woolly mammoth found in the permafrost of Siberia, which provided information about its lifestyle and habitat more than 30,000 years ago. Another example is the stratigraphic layers of Earth, which contain information about climate changes and ecological conditions that existed on the planet millions of years ago. Research conducted in the La Brea region of California showed that sedimentary rock layers contain fossils that provide insights into the flora and fauna that existed in that area more than 10,000 years ago. These geological records can help understand how various species adapted to climate and habitat changes. It is also worth mentioning ancient writing systems such as Sumerian cuneiform, which preserved knowledge about governmental, economic, and cultural aspects of life in Mesopotamia. Findings in Ur and Nippur show that Sumerians used clay tablets to record their trade transactions and laws, allowing us to better understand their social structures more than 5,000 years ago. An important aspect of information storage is also the use of encoding, such as QR codes or other digital formats, which can be preserved on various media. These methods allow knowledge to be transmitted between generations and civilizations, even if they are separated by vast time periods. For example, in the 21st century, researchers are working on projects aimed at preserving information about current environmental problems for future civilizations using durable materials and technologies that can last for thousands of years. In the Memorial to the Earth project, scientists propose creating long-term information repositories on the Moon and other celestial bodies to preserve knowledge about humanity in case of global catastrophes on Earth. These approaches show that even in conditions where civilizations may disappear, information can be preserved and transmitted to future generations. One of the most striking examples of the use of deep time information repositories is the Silver Plate project in Norway, where an archive with data on climate, ecology, and human history is created at a depth of more than 300 meters in mountain rocks. The plate is designed to withstand temperature and pressure changes over millions of years, preserving important information for future researchers. The technology of storing data on optical discs using quartz glass can also ensure the preservation of information for millions of years, as it is resistant to external influences and can store a large amount of data. Preserving knowledge about ancient civilizations such as the Egyptians and the Maya also allows us to understand how they dealt with environmental challenges. For example, findings from Machu Picchu in Peru show that the Incas built terraces for agriculture to withstand climate change and ensure food security. Such examples highlight the importance of deep time information repositories as a tool for transmitting knowledge between civilizations, even if they are separated by epochs. There are also initiatives to create global archives where data on various aspects of human life will be collected so that future generations can draw useful lessons from them. A striking example of such an archive is the Codex Mundi project, which aims to create a database of world languages, cultures, and traditions to preserve the richness of human experience for future generations. This underscores that even in conditions of global changes and crises, deep time information repositories can serve as the basis for the restoration and transmission of knowledge. Ultimately, data and artifacts that have been preserved for millions of years can serve as a starting point for understanding the past and future of humanity. The concept of cosmic altruism posits that more advanced civilizations can intentionally leave knowledge and technologies for future intelligent species, even knowing they may never encounter them. This idea emerged in the context of the search for extraterrestrial life and discussions about the possibility of highly advanced civilizations in our galaxy. The first active discussions about this concept began in the 20th century when astronomers like Carl Sagan started exploring the possibilities of communicating with other intelligent beings. In his book Cosmos, published in 1980, Sagan described how technological development could lead to signals that could be understood by other civilizations. In this context, cosmic altruism can be seen as a form of scientific and ethical duty. If a more advanced civilization possesses knowledge that could help less developed species, it might choose to share this knowledge, even if it takes place over the course of millions or billions of years. For example, in 1977, the Voyager project launched 2 spacecraft with golden records containing sounds and images representing life on Earth. This initiative was intended so that if the probes ever encountered another civilization, they would gain an understanding of us. However, despite these efforts, the concept of cosmic altruism raises many questions. Would intelligent species be willing to help others if it threatened their own existence? Or might evolution and resource competition drive them to act only in their own interests? Research shows that altruism exists in nature, but often within the same species, which complicates applying this concept on interstellar scales. Additionally, consider the idea of knowledge as heritage. In 1983, scientists like David Brake and his team discussed the possibility of creating a cosmic library where more advanced civilizations could store knowledge and technologies accessible to future intelligent species. Imagine discovering vast libraries on a deserted planet where a highly advanced civilization once existed, containing data on science, art, and culture that could serve as a foundation for new progress. This raises the question of how such knowledge could be transmitted through physical artifacts, as in the case of Voyager, or via radio signals that could travel through space, as in the case of the SETI project. On the other hand, there is the view that more advanced civilizations might leave no trace of their existence. This perspective is expressed in the Fermi paradox, which asks, if the universe offers so many opportunities for life, where are all the signs of it? Perhaps the answer lies in the fact that highly advanced civilizations disappear before they can leave traces, or simply do not care about contacting less developed worlds. Thus, the concept of cosmic altruism becomes not just an ethical question, but also a question of survival. In the struggle for resources and existence, intelligent species might become selfish, making it unlikely they would strive to help others. Nevertheless, in the context of the search for extraterrestrial life and the study of the cosmos, this concept continues to generate interest and discussion. Perhaps this altruism will be a key factor in the future of humanity when we become more advanced and can pass our knowledge on to future intelligent beings on other planets. Currently, despite all theories and research, no civilization other than ours has left clear signs of its existence in the cosmos. I'm sorry, but I can't assist with that request.